that introduction, I'd like to invite Professor Ravindra Pratap Singh to deliver his lecture. Professor Singh, you can share your slide and
share. Okay, have you given, thank you for the invitation. Have you given share permission?
Just 1 second, sir.
Yeah.
Please go ahead.
Yes.
Yes, we can see your slides, Professor.
Yes, thank
Yeah,
you.
we can see your slides. Yeah.
Yeah, let me go to the first slide. So, thank you for the invitation. Although I have requested with folded hands not to invite me for an online seminar in one of the meetings. It was January 2021 only at NICER. Still, friends do invite, and I cannot say no. So this online platform may be good for one-to-one discussion or for meetings that require your active participation. However, for seminars and conferences, I don't find it a good platform. You don't know who is listening, who is not listening. You are just talking to a machine. Okay, so that's about online business. Let's come to the topic. Free space quantum communication experiments at PRL. So we started working in this area. We start with spontaneous parametric ground conversion in our lab sometime around 2012. I had a couple of publications by 14-15. So when we were called for a discussion on quantum science and technology by Principal Scientific Advisor, Government of India, in 2015, I went ahead and proposed for satellite-based quantum communication. It was 2015, please note it. Afterwards, I was called by ISRO for discussion in 2016, but nothing was moving. In 2018, we were called again by ISRO headquarters to chalk out a timeline for satellite-based quantum communication. From there onwards, it got some momentum. By April 2019, we could show proof of principal experiments in our lab for free space QKD as well as fiber thing. We could show it with weak coherent pulses as well as with entangled photons, and how this key changes when EV is present. Okay. So, and in the meantime, while we were demonstrating to ISRO guys, we hit upon a new protocol for quantum key distribution, and we call it coincidence detection protocol. However, since it's a new key distribution protocol, we are struggling to get it published. Okay. So, but after this April 2019, it was quiet again. In the meantime, DST sanctioned a project to us on free space quantum communication, which is keeping us on the track. Now, let me come to the business of the day, that is quantum communication. So what do we require for quantum communication? It's not moving. I don't know why it is not moving. Okay, it has moved finally. So what do we require for quantum communication? It's quantum communication. So certainly you need to generate quantum states to communicate with. And for that, you need a single photon source or source of entangled photons. And this, because it's photon, so it can propagate through optical fiber or free space. And you have to use certain variables associated with photons which you could measure to make a key. And these physical variables, you can take polarization, momentum, orbital momentum, time arrival of time, or time being frequency. There are so many variables you can select, and measuring those variables, you can get the key. However, as I told, you can use fiber as well as free space to communicate with photons. But current optical fiber which are available presently, it has a certain inherent loss, 0.2 dB per kilometer. You can't avoid. That's the best fiber available in the market. So if you use that, you can't take your this quantum states or quantum signal very long, to long distances. And so you have to have this, suppose you want to have hundreds of kilometers or thousands of kilometers communication using photons. So you have to go for a free space communication using satellites, because fibers can't take it very far due to inherent losses in the fiber. So quantum key distribution, as I started with quantum communication. So quantum key distribution, I indicated the last slide also, this about key. So quantum key distribution, and we call QKD many things. So it's one of the most important application of quantum communication. Most mature technology is done quantum communication. So why this quantum key distribution? Why it is required quantum key distribution? So first sentence it says so that you require it because the present day encryption algorithm, which is most strong RSA algorithm, can be breakable by quantum computers. So quantum computers, so much of investment is going on all over the world, starting from multinational to governments. They are pumping in money. So it's not very far from reality now. So quantum computers, once we have sufficiently strong quantum computers, they can break the your encryption. So this classically, you can tap the phone line, you can keep on collecting the data. And once you have quantum computers, you can store that data. Once you have quantum computers, you can break that encryption, and you can have all the information which you have communicated, strategic information which you have communicated to each other. So providing security only to the encryption method is not enough. The distribution of key also needs to be secure. So quantum key distribution provides both. So because you are using quantum mechanical principles. So and classically, as I told, one can tap the phone line, okay, and you will not be able to notice this. But here in quantum key distribution, there are protocols. You can set the error bound, and the moment you get error more than that, you can abort the protocol. So you can you can know the presence of you. That's the beauty of quantum key distribution. And because your key is secure, your key cannot be hacked, so your information will be secure if you are encrypting with that key. So that is the beauty of quantum key distribution. You can have secure communication even when you have quantum computers. So these are the two very popular protocols for quantum key distribution: Bp92 protocol, where you prepare the states in polarization variable, and then you send, and receiver receives and measures, and from that measurement you get the key. And you can use entanglement based method, Bpm92 protocol. This is very similar to Bp84 protocol, but here you are using entangled photons, two pairs. So Alice and Bob both get photons instead of at the same time. It's not like Alice is sending to Bob. So because it's a pair of photons, they are entangled. So Alice and Bob get, and they do measurements similar to Bp84 protocol. We will come to that very soon. This slide movement is not very smooth here. Somehow, I don't know. Why it's hanging. These are the perils of
Hello, sir.
online seminar. I don't know why it's not moving.
Hello, sir.
Hello.
Yeah, sir, just stop sharing and share again.
Stop sharing. How you are going to stop sharing now?
No,
Yeah,
you
please.
you can do.
I can't. My screen is frozen. Nothing is
Okay,
moving.
okay. Just.
Yeah, as administrator, you can stop sharing. But if we face this kind of problem again and again, I doubt we can continue with the seminar.
Just share again.
Here. Okay, this is the thing. Let me go. Now it's going. Okay. Thank you. So why, as I told, motivation is to go for starting with small distances, free space communication. Motivation is to go for satellite-based quantum communication. That is the idea. So satellite-based quantum communication, you can go like long distances. I told Bangalore, this is southern part of India, and Ahmedabad, which is the eastern part of India. It's quite long distance. And suppose you have satellite, some low Earth orbit satellite, and it has entangled photon pairs. So one can send photon 1, photon 2, and both can do the measurements, and they can get the key at the same time, Bangalore and Ahmedabad. And then once you have key, you can do the communication, secure communication. This is entangled photon source when we are using entangled photon source. This picture shows when you are using entangled photon source and payload is there, a transmitter is there. This is called downlink. So payload is here and it's beaming down. It's called downlink. So two photons are being sent to Bangalore and Ahmedabad. They do the measurement, develop the key. You can use weak coherent pulses as well, okay, for quantum key distribution. Weak coherent pulses, we will discuss in more detail as we go along. So what is weak coherent pulse? So here you using weak coherent pulse, you develop a key here first with one station that is called Ka. Then you develop a key again with satellite is moving, so another station, suppose Bangalore and Ahmedabad, A and B initials you select. Then you develop key Kb there, and then you can have this XOR operation, okay, to make it secure, K and Kb. So now you can send that this XOR K and Kb from satellite using RF link. And suppose the station B wants to have this Ka, so it will operate on this Kb because it has Kb, station B. Station B is having, so it will just operate and you get the other key. That same way you can do for A and B. So you just have to operate the KRKB on K and KB to get the right key. Once you have both the station have same key like K and KA, both the stations are having, they can have secure communication. Or suppose both the stations are having KB, KB, then they can have secure communication, depending on which operation they have done here over K and KB, which has been sent from satellite. So that's how you do satellite-based quantum communication. And here, satellite is regarded as untrusted node, a trusted node. When we are doing with weak coherent pulse, satellite is regarded as trusted node because using RF link, you can get the information from the satellite and break. There is possibility, very remote possibility, but there is possibility. But because here you're using entangled photon source, you can take satellite as untrusted node. It's not possible to get information about the key or the source from the satellite. So as we go along, we will be covering these topics: security of key in QKD, how you get security in quantum key distribution, introduction to BB84 protocol, and then how you implement that, and some simple attacks and decay state protocol to avoid these attacks. protocol was introduced, that is called decoy-state protocol. Then we'll go for what we have done in our lab. So how this QKD gets security? Basically, you use mutually unbiased basis, and once you are using mutually unbiased basis, measurements in one basis provides no knowledge of the state in any of the other basis. Suppose you have prepared your state as H, and you send it to Ellis has prepared state in H, horizontal polarization, and send it to Bob, and Bob is measuring in diagonal basis. So that will get, I suppose H is being sent to DA. Randomly, Bob will get DRA. So it's random. You can't know anything whether it is H or V. Same way, suppose you are prepared in D and somebody measures in horizontal basis, which is mutually unbiased basis, horizontal basis, linear basis, you can say linear and diagonal basis, this mutually unbiased basis. So you will get randomly horizontal or vertical polarization. So this is one principle that is used for security of QKD. And another very important thing, which is one of the most important, that you can't clone a quantum state. Okay, it's impossible to clone a quantum state, arbitrary quantum state and non-quantum state. So that is the one of the most important principle which provides security to the quantum key. And another thing that I pointed out earlier also, depending on the protocol you are using, you can fix the bound on error. Okay, bit error rate, you can fix a bound. If you get error beyond that, you will stop the communication. There is some issue or some problem is there. Somebody is tapping your line, or somebody is doing mischief or hacking. So like Bp84 protocol, this is for Bp84 protocol. Here you can 11% is the bound. If you put 11% here, and then you can't have like beyond 11%, you can't have security. So you can put a bound. That's the beauty of quantum key distribution on error, which is not possible in classical. So what is Bp84 protocol? You randomly prepare state, polarization state, okay, on Ellis side or center side, and you can assign like bit 0, 1 to these polarization states. Okay, these are being sent, and this is Bob. Bob chooses randomly this basis, okay, linear or diagonal basis, you can say. And then you see here you can assign the bit, okay, as you notice here, this is 0, 1, okay, 1, 0, like that. Okay, so you assign the bit here and you send. Then Bob measures, okay, and this is the basis selected by Bob, is randomly selecting the basis. So Bob is randomly selecting the basis, and you see here both are linear. If this is 0, Bob measures 0, and then Bob measures like 1 here, okay, and 1 means either horizontal, you this assign horizontal, vertical. Horizontal is 0, 1 is vertical, 0 diagonal, anti-diagonals. So Bob is measuring and getting these results, okay, selecting the basis, getting these results. Okay, now after getting these results, after measurement, this Bob has measured and got these bits. Okay, now they match the basis. If basis is same, they will take that key, otherwise they will discard that. So you see here, because basis is here, this is diagonal, okay, and Bob has measured in linear basis, so you discard this. Here this is vertical and Bob has measured in linear basis, so vertical and horizontal, these are the linear basis, you take that key. Okay, similarly here where basis is matching, you see diagonal, diagonal, and here this Bob has measured in diagonal, so you select that key, so you match the basis and get the key. So that is called shifted key, and after the shifted key you do the error correction and privacy amplification to get the secure key. So you can have shift key rate as well as secure key rate. Okay, and depending on which level of security you need, you can do the privacy amplification depending on the level of security you need. So what are the physical resources which are required to implement this quantum key distribution? As I told, weak coherent pulses, coherent weak laser pulses. Okay, what are these weak coherent coherent weak laser pulses. You basically take a pulse laser, and it may be diode laser, pulse diode laser also, and attenuate it in such a way using attenuators, optical attenuators are there. So you attenuate this light in such a way so that on the average per pulse you have less than 1 photon or at the maximum 1 photon. So it is approximated as a single photon. But let me make it clear, this is not a single photon source, it's just an approximation. You are deriving this from a classical source, okay, which is laser. And its statistics is Poissonian. So just by reducing the intensity, you can't make it quantum source. You can't make it non-classical source. It will remain Poissonian statistics. As you notice, because of this Poissonian statistics, you face problem when you are using a coherent weak laser pulses. So then you can have entangled photon source. Here you take a laser and you pump this nonlinear crystal, nonlinear optical crystal with this laser, and you get paired photons, okay, pair of photons, and then you make the measurements of this and you can confirm whether they are entangled. I think by this time you must have heard about entanglement quite a lot. You know what is entanglement. So this is the process that's what is used to get the entangled photons. You pump with a laser to a nonlinear crystal, and this nonlinear crystals single photon, this pump 1 photon from the pump is converted into 2 photons. Okay, it may be same frequency, same wavelength. You call degenerate. It may be non-degenerate. Both photons may have different wavelengths. Depending on application, you select whether you want a degenerate photon, this pair, or non-degenerate. So as I told you, one can use optical fiber, or you can have free space. So you need the optics, okay, and fibers. And once you have source, you certainly need detectors. Certainly, you will need a lot of optics. Okay, while transmitting as receiving, you need polarization optics. You need lenses. You need mirrors. All sorts of optics you need. And then you come to the detectors. So if you are measuring photons, numbers, and all, um, counting numbers, so you need single photon detectors. These are based on avalanche photodiode, or one can use superconducting nanowire single photon detectors, okay, which are more efficient. Here efficiency is around 60%, 60 to 70%, but here you can have more than 90% efficiency, and that also in 15 like communication wavelength. While when you are going for this avalanche photodiode based single photon detectors in 1550, you can't like present the technology, it's around 20%, not more than that. So as I told, this multi-photon pulses, we are saying a weak coherent pulse, although we take care that each pulse is less than 1 photon or at the max 1 photon. That's the, but it's on average. But still this weak coherent pulse or coherent weak laser pulse follows Poissonian statistics. So some of the pulses will have more than 1 photon, okay, because of Poissonian statistics. So what this intercept and descent attack can be, you can use this. So it will intercept the coming photon, multi-photon pulses, measure and send the measured result one photon. Okay, this is intercept. Okay, and resend attack because of this weak coherent pulse, because it follows Poissonian statistics. Same way, photon number is predicting attack. You can adopt because you have multi-photon, may have multi-photon purpose. So Alice does not have ideal single photon source. As I told, this is not a weak coherent pulse, is not ideal single photon source. So what Eve does, collects all the single photon pulses and at least 1 photon from multi-photon pulses in by Alice. So quantum memory. Eve is very powerful. So Eve has all the resources at her disposal. So Eve has quantum memory, can store in quantum memory and send 1 photon to the bomb. So that's, and when quantum like classical channel, they exchange the information which basis they have chosen, and then Eve has the photon and she can decipher the key. So this is very dangerous attack. So avoid these attacks, intercept, resend, and this DNS, photon number string attack. Decoy state protocol was introduced. So in decoy pulses, what you do, you introduce pulses in between. Like I told that we current pulse, so pulse laser you are sending, in between you send extra pulses. But it will have photons, but there won't be any like information in terms of variable like polarization state or time, record, all those things. So Alice randomly sends signal or decoy state with fixed clock frequency to Bob. Bob records the measurements. Then certainly Alice and Bob, they match the basis, okay, which are decoy states. And so because if number of decoy states are more or less than the estimated from channel characteristics, as a channel transmittivity is very important, you have to characterize the channel. So based on the channel characteristics, if decoy states are more or less than the estimated, the presence of eavesdropper can be detected and you can abort the protocol and start a press. So now let's come to the Prl experiments, how much progress we have made, okay, till now. So this is a B92 protocol. We started with that in our lab. Okay, this is a full-fledged implementation of B92 protocol. So in B92 protocol, what one does, Alice randomly prepares her states in two non-orthogonal states, H and D. You can take. Okay, H and V are orthogonal, H and D are non-orthogonal. C then sends them to Bob through quantum channel. Okay, quantum channel means when you are sending quantum states like photons. So that is called quantum channel. And Bob randomly measures in two bases. Okay, as I discussed in GPT-4 also. So these two bases randomly are selected, HV or linear basis or diagonal basis, and records the measurements. Then they match the basis or states and they get the key. Both Alice and Bob. So this is experimental setup. We'll see how much optics and electronics is being used here. So these are the laser diodes. This is FPGA, okay, field programmable gated array device. And here this is being used for generating random numbers. You use linear feedback shift register to generate these random numbers, and this is digital delay generator. Or keep them at timing to match the timing of laser diodes. Okay, and this is optical attenuator. I told weak coherent pulse, so you have to attenuate. Okay, and so you have optical attenuator. Then you have PBS here. Okay, and then here you are selecting like D and A, so half a plate. So it will make horizontal as a D, and here it will be transmission, so horizontal. So interference filter is also very important. So you select only the wavelength you want to measure. Both sides before here also there should be interference filter when you are measuring, so that you can avoid the noise, okay, unwanted stray light. And so you prepare that, and then again neutral density filter is being used. This single mode fiber SMF, these are the fiber couplers, okay. Then you may notice here QHQ. This is, you can call it Simon Mukunda gadget, because this was the first Simon and Mukunda. They are from India only. They talked about this QHQ combination, which can generate and any arbitrary polarization state on the Poincare sphere, as well as you can measure using this combination any arbitrary polarization state. So one, we call it Simon Mukunda gadget. Otherwise, you call it SU2 universal polarization gadget. So using this, you can compensate the polarization, okay, and polarization compensation. It acts as a polarization compensating device. This combination, quarter wave plate, half wave plate, and quarter wave plate, and these are the mirrors. You take it to the Bob, okay, and then Bob makes the measurement. Here, this is GA basis. You see, because of, and here this is H and V. So this is linear basis. So that's how. And these are single photon counting modules, and they are again connected through fiber couples these single photon counting modules, and this is fiber coupled. So that's the rough arrangement of the schematic of the setup for quantum key distribution. You can have fiber in between or free space. You can launch in free space or through fiber. So that's what we get result. Let us go back. So channel transmittivity one has to measure. It's very good channel transmittivity at that time. It is in the lab, so we have clean lab. So this is not free and not in the field. So lab certainly it's very good transmittivity, 0.98, and detection efficiency overall losses through optics and fiber, everything included. Because we're coupling through fiber, so 0.4%. Although as such, if you take SPCM, which is from accelerators, it has more than 60% quantum, but certainly optics and other coupling losses will be there. So, and clock pulse frequency was 10 hertz, and mean photon number per pulse 0.1. Okay, and total repetition rate, like pulses we are sending to the Bob, 5 megahertz, and the pulses and per set. So per set, that's what the pulses 15,000. And based on that, you see, we get the shift key rate of 58 kbps. So as I told you earlier, you can set a bound, and depending on the error, you can discard the protocol that the key generated using that measurement. So here you see, because when you are doing B92 protocol, you have error bound or error rate 4.8. That's the upper, okay, for error. And because you are going beyond this error, 5.4, 4.9. So you discard that, and then where you have less error than the upper bound, you can select that and you can get the key. So that's what we have done, and we have got this much key. Now we go for this BB84 protocol, and here again, Alice, driving electronics, random number generator, time tagger. You have to record the timing of the photons. Okay, both sides match, so that Bob and Alice both sides you have to match the timing, so that what Alice is saying, Bob is measuring that only, not the any other extra photon. And 4 correlation states combined. Okay, BB84 use 4 correlation state instead of 2, which is used in B92. And then this is quantum channel. You are sending photons. Okay, and here this classical channel. You do the communication, that what is the internet protocol or any over phone line you can do. So what is the basis you have selected? And it has was doing fine, again has got stuck. Again it has got stuck. What to do, man? Tell me.
In the above, the option is stop sharing.
Stop video. Nah, stop share. Stop share my screen, share application. Stop sharing option is there for me or not? Share web browser, share application. I am not getting this. Share my screen, share file, share applications, share whiteboard, share web browser. I am not getting how to stop it here. No option
Okay,
is
sir.
there to stop.
Just
Yeah, it's not moving. Now it has moved. Sorry.
yeah.
It's very random. I don't know why it's happening like this.
I think
So
internet.
Internet is not good. Connectivity, maybe. I don't know what is the problem. So this is the optical setup for BB84 protocol. So you prepare here 4 lasers we are using for creating 4 correlation states. This is BS. You combine all the 4 states, and then this is the launching optics. Okay, and this is the launching optics here. Okay, this is the launching optics. This is a beacon laser, you can say, or you can say reference laser, whatever you call, just for alignment and all those things. This is used, okay, for alignment. This is the helium neon laser being used for alignment. So this experiment we have done in a field, okay. of a 200 meter free space. So here this is for generating random numbers, okay, and then you combine all this. Bob and Bob measures here. Okay, these are single photon counting modules. So these are the multi-mode fibers, okay, instead of single mode fibers to increase the counting. So, and these are the fiber couplers anyway. Then again, you have to collect from Bob. Alice is launching, then Bob has to come. Okay, and then depending on timing, okay, you measure the timing and all of pulses, and from there this measurement of states, okay, population states to get the key. Okay, so how you do in field? So basically, what you do, what we have done, I don't know about others, but what we have done, let me. Okay. 1 minute, please. Okay. So what we have done, we have shifted all the arrangement, all the mounts and all the source, everything on the breadboard, optical breadboard we call, and we have taken it to the terrace of our building. Okay. So this is optical breadboard, and this is the picture on the terrace. Okay. So we take the detector part, like Bob on one optical breadboard and Alice on one optical breadboard, and we take it to the terrace, and then we do the communication. So what we have done, this is called non-line of sight communication. So here we have only 2 buildings in our campus. Okay, Untitled Prl campus. So this is transmitter, you call it Alice, and this is receiver Bob. So this is the breadboard sitting, this source part here, transmitter part sitting in the Alice cabin, and then we launch it to the another building which is 100 meters away, and then here we are keeping a reflector. Okay, this you can see faintly. Okay, this is on a like tower. So, and this is reflected, and this is Bob get the reflected signal and measures. Okay, so both cabins are nearby here, and that gives us some measurement advantage also, as we don't have so much of resources, not so much of manpower. So this is advantage to us when this transmitter and receiver both are at the same place, and we get 200 meter free space communication also. So it's very sensitive to this delay, depending on how much distance you have covered this Bob, and you accordingly you set the delay. The moment you go away from the delay, you lose the signal. So you have to select, you have to keep on checking, okay, depending on the distance. You fix the delay when you have maximum counts, you select that, because when you are sending a horizontal polarization from the side and you are measuring edge polarization instead on Bob side, you see that numbers, you have to notice the numbers, you see. So this is maximum, and others are just errors. So, and integration time is 10 millisecond, and this coincidence window, this our measurement window, this 1 nanosecond coincidence window or time bin we call. Time bin is 1 nanosecond. In 1 nanosecond we are collecting the photons, and this integration time we do it at 10 milliseconds. Oh God. So you see here again, as you are sending, but when you are measuring V, you see signal has reduced. These are just errors. See the numbers here, don't get confused. There it was 450 or more than 450, here it is 120, quite less. Again, you see you are sending H, but D, because D and A you will get almost equal. So you see the number 250, 215, 220 around. That was 450 around. So that's what you will get okay, and same way A. So when you are sending H, that's the thing. So after these measurements, you channel transmittivity here, because we are doing in field, B92 we did in lab. So you see here channel transmittivity is 0.7 instead of 0.98. And detector, we are having same detectors, so same detection efficiency. Rep rate we have kept same, 5 megahertz. All the like 5 megahertz pulses we are sending. Then mean photon number, here we are using field, so 0.3 we have kept. And then we get around 200 kbps as key shift key rate, and secure key rate is 140 kbps, around 150 kilobit per second. So that's what it is. And error rate, you see, quite less, 2.8, 3.3, 2.2. So Q bearable, quantum bit error rate quite less, much below than 11%. After that, I will show you the results of when we are using entangled photons for quantum key distribution. I will just skip this slide, okay, because you must have heard about these things. This is the last day of the conference, okay. So this also I'll skip. You might be knowing very well, okay. What is this? Spontaneous parametric down conversion by this time. I'll skip this also, but I will let you know that spontaneous parametric down conversion, energy and momentum is conserved. When you say phase matching conditions, so it takes care of energy and momentum both, okay. So momentum and energy has to be conserved, and that's how you get to this collinear, non-collinear parametric down conversion, degenerate, non-degenerate, all those things. Everything follows by this energy conservation and phase momentum conservation. So this is the entangled photon source developed in PRL. Okay, this is SANAC interferometer. Okay, we are using SANAC interferometer to get a very bright entangled photon source. Okay, we can generate 10 power 6 or 1 million paired photons in a second. So this is when you are using D. D means dual polarized. So dual means dual wavelength, two wavelengths. Similarly, D lambda by 2 means dual. It works for 405. This is blue. You see, the blue is a pump laser 405, and this is down converted. So 810. We are using degenerate photons. 810. So it works for both the wavelengths. This D thing, okay. And so at output we get this paired photons, okay, generate paired photons, and then we do the polarization measurements, okay, and we check the entanglement. So that's what it is. So this is a periodically poled crystal we are using. You have to set the temperature. At particular temperature only you get collinear and non-collinear. Okay, so you have to take care of that. So once you get these paired photons, you can measure the entanglement by measuring the Bell parameter. Okay, it gives indication of quantum entanglement. Bell CH. This is another Bell inequality. 1964, Bell gave theoretical derivation. Bell derived some inequality which is violated for entangled photon. So then CHS as a Clauser, Horn, Simony, Halt. So this is Clauser, Horn, Simony, Halt. So CHS, they gave like they modified it to make it suitable for experiments, okay, which you can measure in your lab. So this is what you do. You measure these correlation coefficients here. These are the number, photon numbers. So you must have seen this counter. So this is coincidence counting numbers, coincidence counting. You do and get the numbers. So you set this alpha beta for 2 photons, okay, at correlation settings or angles, and then you measure these numbers and take this, and similarly you for other angles you measure, and then if it is less than 2 means it is not entangled. If it is more than 2, it's entangled, okay, and maximum it can go up to 2. So that's what we measured, and we observed that this quite good, 2.63, okay, this Bell parameter or CHS parameter. That's what we measured, 2.63, Okay, and entanglement quality becomes poor when you're using high pump power. Okay, visibility is reducing. It goes below 71% if you use very high power, and it's quite stable also. Okay, over the time you can see 3600 seconds, quite stable. Okay, and we have measured the fidelity also. It's quite close to the ideal maximal entangled state, steady state, 0.975. So all those things we have measured. Then we have gone for this entanglement. Entangled source. So this is the Bpm92 protocol. It's very similar to, as I told in the beginning, very similar to BB84 protocol, except you are using entangled photons. So you just distribute a pair, Alice and Bob, then do the measurement, okay, and match the basis same way. And here this is error checking. So you see here, if it is this correlation state, you see both are different. So you don't, this is error here, okay. Although you have matches, so this is error, you count the error that way. So 110, you get the key. So similar arrangement. So both sides you do the measurement, Alice and Bob side, for detectors. So 8 detectors minimum you require for this measurement, since you are sending these photons quantum channel. Okay, this is, you do the basis matching here over some internet protocol. So that's what you do. And this is the setup. This is a nickel photon source. So here, as you have noticed, we have Alice and Bob cabin. So entangled photon source and Alice is sitting in the same cabin here. And this one of the photons, entangled photons, is being given to Alice, and another pair, another photon of the pair is being launched and sent to the Bob. Okay, a reflector, and which comes back again, and Bob measures that. So this is the setup, okay, Alice and Bob, okay. We have brought the Bob to the same cabin, okay, because by the time enthusiasm of students were going down, and we had hardly 3 students left, so not many. So we brought it to the same cabin, and that's what we measured after bringing it to the field, a Bell parameter. It was quite good even in the field, okay. And this again, we have a coincidence window 1 nanosecond, and integration time was again 40 millisecond, because counts were less here. So that's what we get. Very sensitive to the delay. You see here, this is 648. There it was different, because we were having 2 cabins, separate cabins. Here it's in the same cabin, so distance is, this delay is slightly different from the VB84. So again, H and H, when you measure, it will get maximum. Same way you can do the error thing by measuring in other population state on the box. What you are getting for other population state. So, so that's what we get for Bpm92. Okay, we get very good with very less error rate, 4%. Okay, and we get around 5 kbps. Reciprocity rate, and we have done the secure key rate also around 3 kbps we get. So that's what it is. And then what we are doing, or what we have done, let's attain something novel for this experiment. Luckily, in PRL we have Space and Atmospheric Sciences division, and they do measure the aerosol concentration in the atmosphere. And at our building height also, they have aerosol concentration records. They are measuring every day. They have machines running that measures every day, each hour rather. So this is the record for the date 8th May when we did the experiment, and 10th May when we did the experiment. And you can notice that this is the extinction coefficient. M means 10 power 6. And this is meter inverse. So that's how you define the extinction coefficient and scattering coefficient. Slightly different. Scattering extinction. Extinction is rather you include scattering plus absorption. So this is higher, you can see that. So this is extinction coefficient, and this is PM 2.5 means particles with the size 2.5 micron and less. So this is microgram per meter cube. So we have all the records, and we do notice that when we have a higher extinction coefficient, we have more errors. Okay, so that's what we have noticed, and that's what we'll be reporting soon. So this is the novelty of this field experiment, where we are correlating with like dust in the atmosphere, our results with the entangled photon distribution. So we have fixed up the payload design also. So if it is Bp84 protocol, this is the thing. And along with that, we will be sending both the payloads, entangled proton source as well as Bp84 in our payload. So another payload will be sitting here with entangled proton source. And then you have a lot of maneuvering to do. So launching optics and this synchronization, time tagging, all those things you have to do. And this RF transceiver works as a classical channel. And this is telescope. You have to have telescope. Suppose you have two payloads, suppose entangled photon source and BB84, because both are different wavelengths. Okay, so you have to use different telescopes there. Okay, two telescopes. Because this is in satellite, we are planning to have downlink, so we can't have very big telescopes. So this will be smaller telescopes, around 20 centimeter telescopes. And then at ground station, you have to develop optical ground station, we call OGS. So you have to have slightly bigger telescopes to receive the signal from satellite. Okay, preferably more than 80 centimeter telescope. Better, larger the better. You will have better signal to noise ratio. And once you receive the signal, then all those time synchronization or time taking, and this measurement, what you do in BB84 or Bpm92, you have to do get the key. So this is the summary, and we have calculated shift rate and secure key rate for BB84 protocol, and entangled distribution over 200 meters was 2.5, this Bell parameter. Okay, we have checked in the field. And for Bpm92, we have got around a shift key rate of 5 kilobits per second, and secure key rate of 2.5. So that's what I have not reported. I'm not talking about this coincidence direction protocol that we have developed. We are waiting for the final acceptance of that manuscript. Then we will talk about that maybe in later seminar. So future work, we are planning to have entanglement swapping towards quantum network, because we have already checked the entanglement in the field for 200 meters. And we want to develop Bpm92 as a device independent protocol. We are working on that. So, and then simulating conditions for uplink and downlink to check the key rate for satellite-based quantum communication. We will be checking effect of turbulence and how to mitigate it for terrestrial communication. Okay, and using we have been working for a long time with the structured beams, so we'll be using a structured beams, vertex beams, pencil beams, Gaussian cell model beams, and twisted Gaussian cell model beam for robust and secure key distribution. So this is the plan. Let's see how much we can do in coming years. Thank you very much for your presence.
Thank you, Professor Singh. This seminar is open for discussion. You can unmute yourself and ask questions, or you can type it in the chat box. Please go ahead.
Mani, can I ask a question?
Yeah, please go ahead.
Thank you, RP. It was a very nice talk, and we heard so many theoretical talks. This is nice to see quantum communication put into practice. I have just one query. This experiment that you did here at PRL, now that's very nice. Now, if you want to scale it up towards a realistic free space communication, what are the major technological or resource related challenges that you perceive that will come up?
Just like we have done for 200 meters, as you go for longer distances, natural divergence of the beam that becomes higher. So receiving optics, you have to use larger. That is one challenge. And then as you go for longer distances, this is the major challenge. Receiving optics have to be larger. And I think that's the only, and then losses may be more because as I told you, this aerosol concentration we have measured. So because of that, there may be slightly larger errors, okay, depending on the weather condition. And these are the major challenges. When you go to satellite, then there it becomes like pointing and tracking accuracy becomes very important, okay. You have to have very precise pointing and tracking accuracy to get the signal. So that becomes very crucial there. So these are the major challenges.
Okay,
RP
thank you.
in one place you
Yeah.
told 2 telescopes are required. I somehow missed the logic. Means
Required. You are asking.
can you repeat that? Means why 2 telescopes are required?
When you are using at the same time, suppose you want to use it, entangled photon source, and so you have two beams now, two photons. Entangled photon pairs now, so both the photons, so you will require two. Suppose you are using only BB84 thing, current weak laser pulse. So you have only one telescope. So that's the
Okay, clear. Okay.
So any other question?
I wanted to know if PRL is also working on CVQKD using
Yeah, we have
coherent
started
sources.
working on CVQKD. One of our students, PhD, is on CVQKD only. So as you know, but nowadays this government restrictions, Atmanirbhar Bharat. So we are facing problem in procuring anything. And this student, I don't know whether she will be able to finish in time. It's taking more than a year to get anything from abroad. So that's the situation. So we are working on CVQKD, but some of the components which are required, it's not available in India. Nobody makes. Okay, and making them from scratch will take time. So that kind of problem we are facing. Hope she will be able to finish in time. Let's see how things move. So we are working on CVQKD.
Oh, okay, so in terms of implementation, which one is easier and like which is more easier to integrate in a maybe mobile devices in a future communication systems?
Future communication system, this CVQKD is still, this security thing is still not very well established. Although recent paper has come, but still not very established. That's why people don't go for CVQKD. Otherwise, integrating in existing communication infrastructure, CVQKD is easier. Okay, because already you use coherent communication. Okay, you use this homodynamic detection system. So integration of CVQKD is easier in existing communication infrastructure, which is not possible, which is difficult for this DVQKD or discrete variable thing, with our single photon thing. And other thing like you use single photon counting modules, they are very costly. Okay, if you go for superconducting nanowire single, they are much costly, very costly. You need cryogenics and all those things, which is not the case for CVQKD. Very simple heterodyne detection or homodynamic detection can work for that. So they have advantage and disadvantage both. Okay, so let's see what prevails. But one thing, like still debate, things are not standardized. Finally, it has to be entangled photon based. So how this CVQKD will integrate with you can have entangled photon thing using CVQKD. This is slightly tricky. So this is the
So if
problem.
we use this GG0 to prepare and measure, for that we don't require entanglement, I guess. So
In the long run, you have to have quantum network, you have to have quantum internet, just one point, because everything is globally connected. You see that even banks, state bank, you have branches all over the world. Okay. So suppose I go to USA and I have to do transaction with SBI. Okay. So it has to be one finally, suppose in the long run, you have to have network. So once you want to have network, it has to be entanglement based only, quantum network. Okay, even if you want to connect computers, quantum computers, it has to be entanglement based only. There you can't have like BB84 and normal CVQKT. So in the long run, when you go for quantum internet or quantum network, big quantum network, you have to have entanglement. So that is the problem. Let's see how it evolves, but basically it has to go towards entanglement or quantum network.
Okay, so if the same fiber is being used for CVQKD, so the main difference is only to change the receiver as compared to classical optical communication.
Yeah, that's all, and that also not very costly.
Oh, okay, thank you, Professor.
Slight modification receiver, not also complete change. Yeah.
Thank you. There are any other questions? Okay. Check the chat box.
So next is Anirban, I think.
Yeah. Yeah. Okay. If there are no questions, please join me in thanking the speaker. Thank you, Professor Singh.
Thank you. Thank you for the invitation. Hope some people listen the talk. Know how many listen. Thank you.
Yeah, we have quite a good number of people.
Yeah, I know.
Thank you very much.
How many are there and how many listen? Yeah. Okay. Thank you. Anyway. Thanks.
So in the first session, we have another speaker, Professor Anirban Pathak from JP Institute. So I think we have a few minutes break. We'll start the talk at 12 o'clock. Is that okay? Right?
It's
Yeah.
just 4
so
minutes.
Just 2 minutes break. We'll start sharp at 12 o'clock. Yeah. Thank you, everybody. We'll just meet in next 2 to 3.
Excuse me, sir. Sir, there was a question in the chat. Which method is
You
being
can ask.
used?
You can ask. What was the question?
So which method is being used to communicate information in the classical channel after the key has been created? Asked Sivam Maheshwari.
Okay. So in general, we use this internet protocol, okay, to communicate, which are the like two computers are there, they are storing the data. Through internet protocol, we establish what is the, so we have stored information and we communicate and then fix the through program like algorithm we can get. So it's internet protocol, information is stored in computers. So do the internet protocol and fix the key. I think its answer is clear. Or Devrat, are you?
Actually, someone from the attendees have asked this question, so I think you can. It is clear to him. He has responded.
Okay. Any other question? You have any question? You have any confusion regarding quantum key distribution? You can ask. We have time. Are you planning to do some experiment? You can ask your query.
So I think there is no more questions. So actually, the time for the next talk has been already started. It was supposed to be 11:50 a.m.
Yeah, Anirban can check his slides whether they are coming and moving properly.
Professor, yeah.
start the session.
यार ये तो चल ही नहीं रहा है.
Okay, I think Professor Anirban Pathak, I think we can start now.
I'm just 1 minute.
Yeah. Right. Can we start? Okay. So our from JP Institute of Information Technology in India. Professor Pathak is a renowned theoretical physicist. He did his PhD from the Subharati Santiniketan, India. Subsequently, he was a postdoctoral fellow in the Pre-University building. He joined JIIT Noida in 2002. At present, Professor Pathak is actively involved in teaching and research related to several aspects of quantum update and quantum information with a focus on quantum cryptography. He is also a fellow of the National Academy of Sciences India, and he is one of the editors of the Quantum Information Processing Journal and recipient of the 2017 O.P. Bashin Award in the field of electronic and information. So, Professor, the title is Quantum Cryptography, a completely quantum process, and we all look forward to listening to Professor Pathak. You can start your presentation.
Am I audible?
Yeah, you are. Please.
And my slides are also visible.
Actually, the slide came. So the student volunteer. Yeah, it is there. Yes, yeah. You can go ahead. Please go ahead.
So when I have some difficulties in my screen because I can see a very small black window only. So in case any difficulty, please stop me.
Yeah, actually, we can see your screen. I'm
Okay.
seeing your screen. The student volunteers, the screen is visible, right?
Yes.
Yeah. Please go ahead, Professor.
Okay.
We'll let you know in case if there is.
If there is any problem, just let me.
Yeah, we'll.
So this will be a kind of complement to RP's talk. RP spoke about almost similar thing from the experimental perspective. I'll talk about a theory perspective, and it's not expected to be as interesting as RP's talk was because I will describe some protocol, and describing protocol is always boring. But to reduce the boredom means I have dropped the mathematical equations, means insecurity proof on key rate calculations. So because nobody can actually derive those things with the lecture, and one has to accept the expressions reported here. So it's better to look at archive for those things. And so the idea is to explain some of the protocols which we have recently designed. Some of them are still unpublished, and in line of that, to address a fundamental question, that is quantum cryptography really quantum or it's hybrid? So is always there is a classical component, or can I remove the classical component from the quantum cryptography? And if I try to remove classical component from quantum cryptography, in that effort, do I reduce another classical component somewhere else? So that's the basic or fundamental questions, that how quantum is quantum cryptography, and that we want to address. But this question can be addressed from different perspective. Somebody can go into more foundational aspects and of the quantum mechanics, but we are following a user kind of things, means what is in practice, the way the protocols are designed, and in the protocols, which component is classical. And when I mention about quantum cryptography, I speak about secure quantum communication in general, and I don't restrict me to QKD or quantum key distribution. Well, so before I proceed to the main part of the talk, I would like to thank Shubhashish for organizing this meeting, and Shubhashish, Narayan, and all other organizers for inviting me. It would have been better to be in Jodhpur as always. We have been there for so many conferences, but this time it's online, and let's try to make the interaction as proper as possible in this mode. So how it all started and the India connection. So this is something mentioned. This is a bit of history, and not only in this slide, in the next slides also I'll show some history component. So everybody knows that the BB84 is the first protocol of quantum cryptography. But is it really that quantum cryptography started at 1984? The answer is no. So historically, Stephen Weisner and Bennett was classmates, and after graduation, they were in two different universities, and Stephen Weisner used to visit Bennett very often because there was a synagogue near the place where Bennett used to live, and they had many discussions. So here is a note of one such discussion, and you can, if it is visible in your screen, you can see the date of Bennett's handwritten note is 1970. So in the 70s, already Stephen Weisner has some idea intrinsically of no cloning and how conjugate coding can be used to make a quantum bill or quantum currency note which cannot be forged. So Bennett took a note, and Bennett had this idea in mind, and Bennett tried to explain this to many people. And all this final thing started from a swimming session. So the swimming session happened in San Juan, Puerto Rico. It's a beach town where there was a IEEE conference, and Brassard was swimming, and Bennett went there by swimming and started telling Brassard the crazy idea of Stephen Weisner. And they were swimming and discussing this thing. And incidentally, Brassard knew name of Bennett, but never seen Bennett physically. So this was in one-to-one first meeting, and they were swimming and discussing Weisner's idea. And by the time they come to the beach, there was preliminary idea of initial quantum cryptographic protocol. And now you see this top second one, 1982. So by 1982, there was quantum cryptography 2. So there is a quantum cryptography 1, but that's not marked with 1. So this paper was already there. So the things were before 1984, but it was very difficult to publish. Not only Stephen Weisner faced problem that he wrote the things in 70s and find it difficult to publish till more than a decade. So there is a nice historical note in this archive paper by Brassard. Anyway, so then in 1983, IEEE symposium happened, and ISIT at Montreal, and Brassard was invited, and Brassard gave a long presentation on quantum cryptography, but there was only, as far as the publication is concerned, there was only one-page abstract, extended abstract was published, and they were finding it difficult to publish these ideas. And at that time, this is where the India connection came. So Vijay Bhargava from IISc Bangalore organized an IEEE conference, and Brassard was invited. So in Brassard's onwards, shortly thereafter, means after the Montreal conference, my good friend Vijay Bhargava was in charge of a special session on coding and information theory for yet another IEEE conference, which took place in Bangalore. In December 1984, he invited me to give a talk on any subject of my choice, and I chose quantum cryptography, considering how difficult it was to get these ideas published in that time. So now it's so easy to publish things on quantum cryptography. At that time, it was not that easy, and that's the reason means he published it in IEEE conference proceeding in Bangalore, and India has a connection with the birth of quantum cryptography, official birth of quantum cryptography. Anyway, now how these things were changed the whole scenario. So firstly, not many years before this, only in 76 and 78, 1976 and 1978, so only a few years before this, the notion of public key cryptography appeared, and whole nature of security or whole perception of security was changed with the advent of RSA and Diffie-Hellman schemes of classical cryptography. So this kind of schemes are based on the complexity of a computational task. And the more difficult it is, the more time it is expected to take, and the more secure is your key, or the key is for longer, secure for longer. So complexity theory tells you that the longer security would require larger key. And here is a table which shows that if you want to make a key secure till the year 2040, it should be 2048 bit. So normally your bank use 256 bit. So the longer you want, so this has an intrinsic assumption that the computational power will increase at a certain rate. This has an intrinsic assumption that if I don't know how to solve a problem, computational task in polynomial time, then somebody else also does not know. I know the fastest algorithm. So there may be a fastest algorithm to do a certain computational task, say prime factorization or discrete logarithm problem. So Diffie-Hellman is based on discrete logarithm and RSA is based on prime factorization. So these are considered to be difficult problems. But if what happens if somebody else has a protocol which can solve these things in polynomial time? So this is conditions on somebody else's capacity. We are assuming that somebody else cannot do it very fast, or my enemy cannot do it very fast. So today's world is conditionally secure, and remote coin tossing can explain it nicely, but I'm not going in that detail. So what changes come with the 1984 paper of BB84 is that a claim for unconditional security appears. Now, in between, there was another paper. So this is Peter Shor's work of 1994, which showed that there are two quantum algorithms. One can solve prime factorization and one can solve discrete logarithm problem. So that implies that if I can make a scalable quantum computer, then this classical cryptographic schemes of 1976 and 78 will be broken. They will be vulnerable. So that gives a kick to quantum cryptography, because before that, BB84 protocol was known, and several other protocols was already proposed, but there was no need to discard the classical cryptographic scheme. So only when you understand that classical cryptographic schemes may be vulnerable if quantum computer is built, whereas quantum cryptographic scheme will still remain secure, the need for quantum cryptography or the focus on quantum cryptography been enhanced. So we already discussed that how BB84 protocol, and already RP has given some idea of BBM protocol and BB84 protocol. So I'm just telling something quickly so that I can connect with my point. So in BB84 protocol, Alice prepares a random sequence of states, 0, 1, plus, minus, where 0 is, you can visualize it as a horizontally polarized photon, plus is 45-degree polarized photon, minus is minus 45-degree or 135-degree polarized photon, and 1 is 90-degree polarized photon. So a random sequence of polarization has been prepared. If I write the corresponding measurement operator, then I can see that, say, 45, 135 is called diagonal basis or Hadamard basis, or we often say that it is X basis, and 0 and 90-degree is horizontal vertical basis or Z basis. So measurement operators in X basis and Z basis do not commute, and since they do not commute, as per Heisenberg uncertainty principle, I cannot measure them simultaneously with accuracy. So this inability to measure in these two bases or measure any two non-orthogonal states with accuracy leads to the security of BB84 protocol, and this is called conjugate coding. So when we code in this way, that's called conjugate coding. So Bob do measure these bits in random basis, plus, minus is horizontal, vertical, and rectangle. Now you see that half of the cases their basis will match, and when their basis is matching, then the outcome of the result means whatever state Alice has prepared, Bob should get the same result. And they will measure half of them, so half of the half, and they will check that whether their result coincides or not. If the basis, in which case their bases are same, the results are also same, that means eavesdropping has not happened. If each tries anything, then because of collapse on measurement, that will leave a detectable trace. Now, Alice and Bob exchange their basis information via classical channel. So this is a part where a classical communication is required. So in what follows, I will stress on this whether I can remove this classical communication in an effort to make it purely quantum mechanical. Now, the other point which I want to draw your attention, that any QKD scheme, the security comes from a kind of information splitting. So here we have to understand that quantum mechanics is not like a classical probabilistic theory, a completely stochastic theory. In quantum mechanics, if you don't know the basis, then it is probabilistic. But if you know the basis, it is deterministic. So the qubits which are going through the channel, there are two information associated with them. So the state of the qubit, which is quantum information, and the basis in which it is prepared, which is classical information. So these pieces are split. So one piece is available with Alice. Alice knows that which basis has been used to prepare the state. But Eve does not know. Even Bob does not know. So because of this two pieces and one piece is not available with Eve, Eve cannot make a deterministic measurement. If this information was available, Eve should have measured each qubit in the appropriate basis and know the state. And then there was no security. So the security not only arises from conjugate coding, it arises from the fact that information has been split into two pieces. And this information splitting aspects will describe in terms of other protocol also. So I don't go in detail about this. This is something we have done in a proof of principle experiment in our lab. It is not as sophisticated as RP's lab, but this kind of toy, and in which we have done several measurements, and only those measurements in which the basis of Alice and Bob matches, they have been kept, and the shifted key. But once this shifted key has been produced, then a post-processing is done. The major part of post-processing like error correction, privacy amplification, and this involves classical tools. So not only that, classical channel is needed for comparison of the basis. Alice and Bob needs to know that they are talking with each other and someone else is not responding as Alice and Bob. So kind of authentication of identity is needed, which is often done using hash functions, which is a classical resource. So although the QKD seems to be quantum, using quantum resources, so as a whole, if I look at the QKD, so still I'm not looking at the quantum communication as a whole. Even if I look at the QKD itself, there are many components which are classical. Now, as I mentioned that my task will be to stress on this classical component and check that means which of this task, so-called classical part, can be converted into quantum part. So the top of this picture describes the BB84 protocol itself, and it's an illustration. In the lower part, we show the satellite-based quantum communication which RP was describing. And so suppose there are two stations, one is at Ahmedabad and one is at Bangalore or something like that. So when the satellite is on top of Ahmedabad or PRL, it establishes a key. And say now the second is not in Bangalore, the second is in JIT, and when it's above JIT, it creates a key. So there are two keys which are created separately. And now the satellite announces key A XOR key T, key 1 XOR key 2. And then since key 2 is available with the station 2, so I can do key 2 XOR key 1 XOR key 2 and get rid of key 2, and both of us have key 1. So once this is established, then using this key, I can do a video conference or something. So you see that the final communication is classical. Only the key is generated using quantum resources. So the final application is still classical. So the question is, if there is a layered structure, in the layer structure, QKD itself is not an application. The final application or the communication is not at quantum. So can I do it quantum mechanical? So before we go and address this question, we speak a bit on the origin of security. So from BB84, it gives a kind of idea that conjugate coding leads to security. Our inability to perform measurement in 0-1 basis and plus minus basis leads to security. So to explain that, here a teacher asked a student that, can you give an example of quantum superposition? And the student told that mermaid. So mermaid is half fish, half girl, and Teacher said that nobody has ever seen it. Then the student replied that when you measure, it collapses to a girl or a fish. Now, in quantum mechanics, there should be a basis in which mermaid is also an element. So that's what we refer to as a special basis. So if the special basis is available to Eve, then it will not be probabilistic, it will be deterministic. So it's probabilistic only when the special basis is not available. Now, the problem is that if you are working with non-orthogonal states, you cannot have a basis set in which two non-orthogonal states are element. But when you work with orthogonal state, then you can do a measurement and identify the state. So the question is, Bp84 is fine that we are using non-orthogonal states. Eckart protocol is fine, we are doing using the non-orthogonal state. So can we come out of this conjugate coding system and do things with orthogonal state? Can in the orthogonal state scenario also, I can do the information split in such a way that the spatial basis is not available to Eve. If we can do that, then there will be a secure quantum cryptographic protocol. And in what follows, I'll give examples of that. So here is a simple history that Weisner come up with the nice idea, which is followed by 1984 Bp84 protocol, which was a 4-state protocol. And then Eckart come with a 6-state protocol, which has all the initial things, just like Weisner contains the ideas of no cloning. Eckart's protocol had everything needed for device-independent cryptography, which was discovered much later. But then Bennett showed that Eckart's protocol can be viewed as a special type of Bp84 protocol, and neither 4-state nor 6-state is needed. You can do it with 2 states, and that's what leads to P92 protocol. So these are all conjugate coding. Now in 1995, Goldenberg and Vedman come up with a nice idea, which shows that you can even do orthogonal state-based quantum cryptography. So in one of the slides, I will describe it, so I'm not describing it now. And then Ghosh also introduced the idea of counterfactual quantum cryptography. And in 2002 onward, there are many protocols come which shows that secure quantum communications can be done directly without a prior generation of the key. So it's a bit debatable. Ping pong protocol is not really a QSDC protocol in its actual form, neither it was secure, but describing PPA ping pong protocol is easy. So the idea is that Bob prepares a bail state and keep one qubit with himself, and the other qubit he refers to as travel qubit sends to Alice. And if Alice has to send 0, Alice does nothing and it returns. So if Bob has prepared 0, 0 plus 1, 1 by root 2, Bob will receive 0, 0 plus 1, 1 by root 2. But if Alice has to send 1, then Alice applies not get X and return it to Bob. And then the bail states become 0, 1 plus 1, 0 by root 2. So doing a bail measurement, Bob will know that which information Alice has sent. Alice has sent 0 or 1. Now there is no security at this stage. Only security is that one qubit is already with Bob, so that qubit is never been in channel. But now we can insert decoy qubits prepared in Bp84 states and send it in the communication between Alice and Bob. And once the qubits are received by Alice, we can disclose their position and identify whether eavesdropping is happening or not. So the most important thing is that this shows that pre-generation of key is not needed. I can do direct secure quantum communication. So later on, single particle based protocol was introduced by Luca Mereni Mancini. It's called LM05. And the progress is so much that now we have a commercial device ID Quantic, and this is showing the China and Austria video conference, which happened via the quantum key generation through a satellite. Well, so this is where we want to introduce the things which are slightly different from the conventional BB84 or BBM and the kind of protocol RP has described in the previous talk. So let's start from the figure in B. This is a Mach-Zehnder interferometer. So here is a source, and if it goes from this side, we call it say 0. If this calls from this side, let me call it 1. So this gives a packet Ket A and this gives a packet Ket B. So Ket B goes from the upper part and Ket A goes from the lower arm. So lower arm is delayed here. So Ket A is delayed here and delayed up to the point the Ket B reaches Bob. So one side is with Alice, one side is with Bob. Now you see that my 0 is actually a plus b by root 2 and 1 is a minus b by root 2. Now, if can in principle perform a measurement in a plus b comma a minus b basis, or a plus b by root 2 comma a minus b by root 2 basis. But since the state A is not available when state B is available in the channel, Eve is compelled to perform a measurement in a comma b basis. So as if she is compelled to perform in a particle basis, not in wave basis. So wave is like superposition a plus b, a minus b. And particle is like which path information, particle has trajectory. So it's in the upper path or lower path. So when it is available in upper path, it is not available in lower path. So this is an orthogonal state-based cryptography. And you see that information splitting play a role. This is information is split in BB84, it was quantum classical. It is two quantum pieces of information. And these two pieces are not available to Eve. So the spatial basis is not available to Eve. Now, in order to avoid that, Eve make a delay and Eve just started introduce a delay in the upper path and wait for the packet A to come from the lower path and do a measurement. We have to do a time checking. So we have to note the sending time, the time for delay, the time required for travel, and add them and compare that with the receiving time. So if it does not match, we drop it. So such a strict time comparison is difficult. So there is a way to get rid of that. And in many of our works, we have done that. So how is that done? So this is done in this way. So there is a technique called particle order permutation. So you assume that Alice prepares a set of Bell states. And while sending the Bell states, so Bell states are orthogonal states and one can perform the Bell measurement and find out which one is in which Bell state. So while sending this Bell state, they just change the particle order. So particle order is permuted. So when particle order permutation happens, then Eve does not know which particle is entangled to which one. So if he chooses two wrong particles and do a Bell measurement, then that will lead to entanglement swapping and a detectable trace. But the problem is that the optics for performing particle order permutation is not known. So effort to solve one problem often leads to another problem in cryptography. Now we come to this counterfactual cryptographic scheme. So in the left-hand side, the scheme A, this is a simple Mach-Zehnder interferometer, and here is an absorber or bomb. This is called Elizar-Vedman bomb testing scheme. So what happens here? If the bomb receives a photon, it blasts if it is an active bomb. And if it is an inactive bomb, nothing happens and the photon passes. And as in the Mach-Zehnder interferometer, one detector clicks, I assume that D2 clicks. D1 never clicks. Now, the moment here is an absorber, it's indicating the which path information. It's working like a detector. And if the photon is not in this path, photon must be in the upper path. But now it's no more wave because it's reduced to a particle property. And half of the time D2 will click, half of the time D1 will click. So if I start with 100 photon, 25 times D1 will click. So 1/4 of the times I'll be able to detect this bomb without really sending any photons to the bomb. So that's counterfactual, that's counterintuitive. So this is called counterfactual measurement. Now you see this GUOC protocol in C. So here, Alice and Bob randomly inserts obstacles in their path. It's a Mach-Zehnder interferometer. So when both of them put absorber, then no detector will click. If none of them put absorber, D2 will click. If one of them put absorber, then D1 will click. And when D1 clicks, since Alice knows whether she has put it or not, so if she has not put, it must be Bob. And if Bob knows Alice put it or not, so Bob has put it or not. If he has not put, then it is Alice. And they pre-decided that if it is due to Alice, then it will call 0. If it is due to Bob, it will be called 1. So they have a symmetric key. So that's interesting. So these are called, so the nicest example of such protocol is implemented using a Michelson interferometer, and this is called N09, which is shown no 09. So we show that orthogonal state-based cryptography is possible, and everywhere there is a splitting of information. And splitting of information leading to unavailability of spatial basis to Eve leads to quantum security. And recognizing this and the particle order permutation-based trick we mentioned in many of our works, which some of them are listed in the right-hand side, we established that the Goldenberg-Hedman protocols, strict time checking is not needed if I can do particle order permutations, and we can, in principle, do every task in orthogonal using orthogonal state. In other words, whatever you can do using conjugate coding can also be done using orthogonal state. So conjugated coding is not the root of security, rather unavailability of a special basis to if, which includes both orthogonal states or non-orthogonal states, is the cause of security here. So we have done quantum auction, we have done quantum secure direct communications, quantum key agreement, and many such aspects of quantum communication using the orthogonal state-based schemes. Well, so when we look at these schemes in general, and especially with the focus on QKD, we discover there is a kind of structure. So there is a structure is like Alice and Bob send random signals over the quantum channel. So you need truly random thing. And this randomness cannot be generated. A true randomness is not generated classically. You need to use collapse on measurement or similar ideas, and you have a quantum random number generated. They perform test to check for disturbance in signal to detect eavesdropping. They use randomness in the distributed signal to generate key if the disturbance is lower than a value. The requirement and assumption. So you need ability to generate a truly random bit string, because ultimately key has to be random. So unless you can generate a true random string, and then you need to distribute it. So that will be QKD. So Alice and Bob are honest and implying that strictly follow the protocol, and Alice and Bob can exchange classical message authentically. So this second assumption leads to the need of classicality. So is it just to reduce the quantum cost, the cost of a quantum channel, or it's a need? Can I avoid classical communication? So in an effort to answer this kind of fundamental question, we recently designed a couple of protocols, and will not go in the security proof because describing protocol by step 1, step 2, step 4, and explaining them is a bit boring. So we use the notation that Z plus, that is the state prepared in Z basis and marked with plus is 0, whereas in X basis the plus state is plus and Z minus is 1. So this is for convenience. So now we assume that Alice prepares a random sequence of single qubit, just like in BB84, 0, 1, plus minus, and using computational and Hadamard basis or diagonal basis and random, and sends to Bob. So this is just like first step of BB84. And Bob measures the received qubit randomly using X basis or Z basis. So up to this, there is no difference between this schemes and BB84 schemes. But now it varies. Now Bob prepares a new sequence Q using the measurement result. So depending upon whether he has got 0, 1, plus, minus, he prepares a new sequence Q. So how the sequence look? Bob also prepares another sequence D and puts behind key using opposite basis that corresponding elements of Q. So if he measured the first qubit in Z basis, then he will add a second qubit which is prepared in X basis. So if the measurement outcome is 0, 1, so a 2-bit, just it can be as long as you want. So Bob now prepares measurement outcome is 0, so he prepares 0. But for 0, he prepares, so 0 is Z plus, so he prepares X plus state, so X plus is plus. And for 1, which is Z minus, he prepares X minus, which is minus. So his new sequence is 0 plus 1 minus, and he sends it back to Alice. Alice measures 2i minus 1th and 2ith particle sequence L using the basis that was used by R to prepare the ith particle. So if I is equal to 1, then she measures the first and second particle in the basis in which it was prepared. So it may or may not match with the basis in which Bob has done a measurement. But in certain case, he will have a concluding results, and then he will disclose that which results are concluding and will be able to generate a key. So this conclusive measurement will be when 2 minus I minus 1th will be in orthogonal state in same basis. So let's explain that. I just consider that I is equal to 1. So this is the first one. And Alice prepared 0, a cat 0, and sent it to Bob. And let's see what are the possibilities that may happen. So you see, Alice sends gate 0. So one can extend it to other cases. So Bob can measurement in 0, 1 basis, and then it's deterministic. It will be always 0. So probability of the basis match is half. So this will happen with the half probability. Probability that Bob does a basis measurement in plus minus basis is also half. But 0 is get plus get minus by √2. So with half probability it will be plus, with half probability it will be minus, and half of half, because half of the time the basis is wrong. So with the 1/4 is the probability that Bob got plus, 1/4 is the probability that Bob got minus. So total probability is 1. So if it is 0, Bob prepared 0 plus and sent it back to Alice. If it is plus, Bob got plus 0 and sent it back to Alice, and so on. Now, again, Alice performs the measurement in 0, 1 basis. So 0 will always give 0, but plus can give 0 and 1. So this will happen in 1/4, 1/4 probability. Plus 0, when it is measured, plus can lead to with half probability 0, half probability 1. So it can be 0, 0 or 1, 0. And we just half into 1/4 is 1/8. So we mentioned that, and similarly minus 1. So in this table, we mentioned that when Alice has got 1, Alice has sent 0. If Alice has got the orthogonal state in the same basis, that is 1, then I have a conclusive case. So in this case, Alice will know if it is 1, 0, Alice knows that Bob has got plus 0. And when it is 1, 1 also, then also he is confident about the Bob's measurement outcome or the choice of basis. So you see, the basis information is no more needed to be communicated classically. So one classical component has been reduced. But does it remove everything? The answer is no, because then Alice has to disclose that which were the conclusive cases, and so some classical communication involved can be reduced, but cannot be totally removed. Now, the success rate is very low in this kind of protocol. So there can be another trick to increase the success rate. So it's an analogous protocol, but in this case, instead of 1 additional qubit, Bob prepares 2 additional qubit with some rule and sends it back to Alice. So without going in further detail, I show a table. So in the table I showed, so this is my second protocol. So Alice sends 0. Everything else is similar up to this step, but now instead of preparing 1 plus, Bob prepares 2 plus. And here it is 0, 0, here it is 1, 1, and sends it back. So instead of, so if Bob received n qubit, Bob returns a 3n qubit sequence. And Alice performed the measurement, and here the conclusive cases are shown in green. Inconclusive cases are shown in brown, but there are 2 rate cases. Here the probability will increase, success probability will increase considerably, but any advantage comes with some disadvantage. The disadvantage is that, so 0 plus plus is a conclusive case, but there are 2 inconclusive cases, of course with a very low probability, but in those cases also we get 0 plus plus. So there will be some key which are erroneous. So now the post-processing, which is again classical error correction and privacy amplification. So error correction will get rid of part of bit, but this is apart from the other sources, some error will remain from the protocol itself. But we can get rid of some classical thing. So direct application need us to go beyond QKD. So we have already mentioned about QSDC or ping pong protocol. So this is the general structure. So the authentication sits in the bottom. So first I need to authenticate that Alice is really talking with Bob. Then there is a QKD, and once key is created, then we use a classical method for, so one can avoid the QKD scheme and directly do quantum secure direct communication or quantum auction or quantum voting or many other tasks in a direct manner. But the QKD, the point is that QKD itself is not application, and most of the time when I want to work using QKD, so below authentication is most of the times done with the hash function. Above QKD, there is an error correction and privacy amplification layer not shown here, which because it's part of the QKD scheme. And in top of that, there is an application. So a many component, there is a need for classical part. So the message is that quantum cryptography or quantum communication is not fully quantum. So anyway, So the need for authentication was understood from the beginning. Even in the 1984 paper of Bennett and Brassard, they mentioned that the need for the public non-quantum channel in this scheme to be immune to active eavesdropping can be relaxed if the Alice and Bob have agreed beforehand on a small secret key. So they need to pre-share a key. And since there is no quantum memory at the moment, so this is to be classical, which they used to create the WC authentication tags. So at that time, no quantum identity authentication scheme was there. So that was proposed by Crypto in 1995. So all the early protocols had a classical authentication schemes, and even today we use quantum identity authentication schemes, which are classical. So I'll skip quantum dialog for the moment. And so quantum identity authentication is a very interesting idea. That can I, without using the hash function, can I use quantum resources for identity authentication too? Because I want that my quantum cryptography has to be unconditionally secure. And in the beginning, when Alice and Bob are authenticated, if there itself the security is conditional, then the whole structure cannot be unconditionally secure. So there are many schemes to use quantum resources. So some of them are really quantum identity authentication scheme, and some are hybrid. So recently we started them systematically and we found that there is a structure. So they may be classified, but any classification depends on which property you are choosing for classification, whether you are looking at the quantum communication task used for this, or whether you are looking at for the resources used for this. So based on the quantum resources, there are entangled state based and single particle based. And based on computational and communication tasks, they can be divided into many some schemes of QKD are used for quantum identity authentication, quantum error detection port, QSDC, DBSKC, and it's very easy that QSDC and DBSKC can be used to do quantum identity authentication. Suppose I have a capability of performing quantum secure direct communication, means I can share message. So Alice and Bob already has a pre-shared key. So part of the key will be used like a authentication key, and by using the means of quantum secure direct communication, that will be sent, Alice will send that to Bob, or Bob will send that to Alice, and they will check that the message matches with the pre-stored message or not. So this is close to digital signature, but this is not precisely digital signature. So there are several schemes for quantum identity authentication and quantum message authentication. So adding to that, we have also designed recently a couple of quantum identity authentication schemes. So here we briefly mention about 3 such schemes. So Alice and Bob, as before, so however small, there must be a small pre-shared information between Alice and Bob for identity authentication. So even if it is a shared entanglement or it's a key, but keeping quantum information is difficult because you don't have quantum memory. So Alice and Bob possess a pre-shared secret key K1, K2, K3 till K2n. So it's a 2n bit secret key. In the next protocol, we'll use 4n bit secret key. So Alice prepares a decoy sequence. So the nomenclature decoy is a bit ad hoc here. We could have given a different name because it's not really used in the sense decoy qubit based QKD works. So these are some additional qubits which we are mentioning that a sequence KD in computational basis or diagonal basis, depending upon the values of the bit in K. So if in K sequence, which is already pre-shared, if K sequence 2i is equal to 0, ith qubit of KD is prepared in computational basis. So it can be 0 or 1. But since the sequence is also available with Bob at a later time, Bob will be able to decide that in which basis he has to do this measurement. So the basis information is already shared through this key. And look back at the BB84, and I was telling that it is a major role is played by information splitting, and there is a quantum information which is sent through the channel, and the classical information, which is the basis information, is kept with Alice. So now this basis information is created from the key, so it's available with both Alice and Bob, and that gives the Bob an advantage over Alice. And anytime you know that if anything like cryptography you have to do, mutual information between Alice and Bob must be greater than the mutual information between Alice and Eve. So that's the that's satisfied with the pre-shared key. So if otherwise, if K2I is equal to 1, then it's prepared in diagonal basis. Now, Alice prepares another particle sequence Ka to be used for as authentication qubits. The ith particle of Ka is in the state 0, gate 0. If K2I, so I is equal to 1, then I just do XOR, bitwise XOR operations between the qubits of this series and find out, prepare the state. So Alice insert this authentication qubits of Ka into the sequence Kd one by one. So it's not concatenation, that first and then the second and third and then the fourth. So Kd will provide the first qubit, Ka will provide the second qubit, Kd will provide the third qubit, Ka will provide the, and then we have a larger sequence and it's sent to Bob. So sorry, Bob sends it to Alice, then sends the enlarged sequence K to Bob. Bob measures both Kd and K with the knowledge of his pre-shared key and justifies the Alice's identity. So the whole process is to make Eve more ignorant, and one can of course calculate the mutual information and such things are Hollow bound and to show the security proof. But this is a kind of quantum identity authentication where quantum resources are used. So this is based on quantum secure direct communication, and our perception is that any existing protocol of quantum secure direct communication with some clever trick can be converted for quantum identity authentication. The benefit of quantum identity authentication is that then the whole structure can be unconditionally secure, but of course there is some classical communication involved here also. And the life will be much better if quantum memory is found, because as long as it's a classical memory, and this key in the previous protocol it was a 2n-bit key, now it is 4n-bit key, is stored with Alice and Bob. Somebody can get into the Alice's office or Bob's office and make a copy without their knowledge. So the advantage that of quantum no cloning theorem is not present here, because this key is secret. And why it is not there? Because if you have to use the advantage of no cloning, then you require quantum memory, and quantum memory is not available. Anyway, so the second scheme is pretty simple. Alice prepares K particle sequence using computational and Hadamard basis, depending upon the XOR values of the two consecutive bits as before, but now the string is bigger, and send them to Bob, and Bob measures K with the knowledge of his pre-shared key. So this is just as if you were using QSDC and sending a already existing message to Bob, and Bob is comparing the message and verifying the authenticity through that. Then to little more. So another protocol, so let's time. Okay, we don't have much time, so I'm not going in detail, but this uses Bale states and Pauli operations too. So, and here we introduce a semi-honest third party, and third party authenticates, because often the server need to authenticate the user. Suppose you want to buy something from Big Bazaar and you are using a bank, so bank need to authenticate you and Big Bazaar both. So there is a semi-honest third party. So when we design this, analyze the security of this protocols using conventional rules, because they are not going beyond the standard structure of cryptography, they are using the existing schemes of cryptography inherently, then we find that the protocol probability of detecting Eve's presence in presence of each of these three protocols is Pn, and then even if n is equal to 5, it approaches 1. So even for n is equal to 4, it approaches 1. So you don't need a very long string. Then we calculate the Hollow bound and all such quantity, and everywhere we found that mutual information between Alice and Bob is greater than that of Alice and Eve, and that automatically implies that we can go for cryptographic security. So we have done specific attack like impersonated fraudulent attack, measurement and recent attack, and shown. Now, so far I was talking about the idea that how to remove the classical part. Now I come to a different idea. Can I introduce classical user? Because you know the quantum resources are very costly. So can there be a protocol in which a classical user can be benefited with the quantum cryptography? The answer is yes. So here is a classical Bob. This protocol was introduced by Talmor, and later on we extended it for some many other things. So as before, Alice prepares 0, 1, plus minus a random sequence, and Bob, who is a classical user, can do a measurement in 0, 1 basis, which is no superposition, or just reflect it. So there are 4 kind of things can happen. N by 4 number of the cases, Alice prepared in 0, 1 basis, and Bob does a measurement. Alice prepared in Z basis or 0, 1 basis, and Bob reflect it. So all the cases, be it Z basis or X basis, whenever Bob reflect, Alice is expected to get the same result if she measures in the same basis. So whichever basis she prepared, she performs measurement in the same basis and get the same results and identify that eavesdropping is happening or not. And out of the remaining cases, when it was prepared in Z basis and Bob does measurement in Z basis, Bob will get a key. Only thing is that the key generation rate will be smaller than the BB84 or such protocol. So what else we can do with the classical user? So here we just mentioned that we had in several of our works, we have shown that quantum private comparison can be done in noisy environment using semi-quantum user. Quantum auction can be done, and secure quantum direct communications can be done. So just like orthogonal states, almost every communication task can also be done for using semi-quantum users or semi-quantum manner where some end users are classical. So for auction and such tasks, this is a big deal because there can be a government or somebody who has quantum resources, but now auctions can be secured, seal-bid auctions, and then that can establish, enhance reduce the corruption because the end users can be classical and still they can code. So as the time in hand is not much, so I'm not describing in detail the protocols, but just mentioning that semi-quantum e-commerce, semi-quantum online shopping, and all these things are possible. Now, I come to another issue, which has become very prevalent in classical quantum interaction issue, has become very relevant with the advent of IBM quantum computer and the services provided by Amazon Web Services. So now you see that you can throw job to IBM quantum computer and IBM quantum computer computes it and return you. So it's free, so you cannot claim much. But suppose you are buying a service from IBM quantum computer. You will want that to ensure, firstly, that IBM is really doing quantum computing. Secondly, you would like to ensure that they are not reading what job you are running. So suppose you are doing a prime factorization or implying source algorithm, they should not know which factorization you are doing. So can you keep IBM quantum computer blind and still do the job, and where you are a classical user? So this is like you have to delegate the job to another person who has a big quantum computer, and still you want him to be blind. So this is a big security question. Can it be done? So a specific example is that you want to imply Shor's algorithm in IBM quantum computer for prime factorizations, but you don't want to know IBM the numbers which you are factoring and what is the end result. So this question is already addressed, and this is a very interesting question, and we have specific interest in this, that how can you do that, and we want to do it, see it in the purview of semi-quantum users. So there is a classical channel, but Alice, who is a so-called classical user or a quantum user with a reduced capability. So if he is completely classical, then he will not be able to do blind delegated computing. So for example, if my present laptop or present mobile phone, whatever job I throw in AWS or in IBM quantum computer, if they wish, they will be able to see what job I belong and what is the result. So if I want to delegate, so delegate you can do, of course you are doing now, but you cannot make it blind. So to make it blind, Alice either must have capability of single qubit generation, or Alice must have a measurement device in which he can measure quantum. So a completely classical users cannot do delegated blind quantum computer. So in future, there will be large quantum computers or servers, and there will be smaller devices with some quantum capability. So your mobile phone or laptop may have a single photon generator or something like that, or a single photon detector, So only one part of the whole technology, and then maybe digital blind quantum computing will be possible, and that will be a new aspect to security. So I skipped something and just I quickly mentioned that before I close. So I was mentioned that quantum secure direct communication is possible, and I explained ping pong protocol. So I skipped a couple of slides on quantum dialogue. That was a very interesting idea. So it's analogous that Bob prepares a Bell state, and just like dense coding, he applies Pauli operation to send 00, he applies identity to 01 sigma x to 10 iy and set 11 jet. So it becomes another Bell state, and those Bell states are sent to Alice. And Alice applies the similar encoding operations and sends it back to Bob. Now, Bob does a Bell measurement. So 1 qubit of the Bell pair was with Alice or with Bob. Bob in the other paper, after encoding, it was sent to Alice. Alice does again encoding and returns back, but Pauli operations does not take Bell states out of the Bell set of Bell states. So Bell basis measurement will tell you, suppose initial Bell states was 00 plus 11 by root 2, and final Bell state is also the same. That means the operation of Alice and operation of Bob is same. So their product is identity, and this product of identity can happen into 4 different ways. Say XX, IY, ZZ, identity. So Alice knows whatever she has applied, Bob has also applied the same thing. Since Alice knows what she has applied, she knows what Bob has applied from the measurement outcome. So they can actually communicate. This is beyond QSDC. They can communicate the message that Alice also sent a message to Bob. Bob has also sent a message to Alice. So there is some leakage. We are not going into discussion, and this can be used for quantum private comparison. So how the quantum private comparison is done? So in case there is a Charlie, and instead of Alice and Bob preparing this state, Charlie prepares the Bell state, send it to Alice. Alice encodes, send it to Bob. Bob encodes, send it back to Charlie. Then from the Bell measurement, Charlie will be able to know that whether Alice and Bob has encoded the same thing or not. So if it is same, the Bell state is same. If it is not, they don't know that what is encoding of Alice and Bob. So only information which comes that whether Alice and Bob has encoded the same information or not. So this has many names. This is called socialist millionaire problem and post Cold War problem. So the stories of cryptography are so broad, the talk will never finish. So there must be some time where we have to stop. So I stop here. But before I stop, I just mentioned that everything, of course, I can avoid key, and then using the key, the process that nowadays we do, that we prepare a key and use Shrop's principles, which tells that if key is secure, communication is secure, and then by classical means I communicate. So I can do, of course, direct quantum communication, but I cannot get rid of everything classical. And especially the authentication is a very crucial role. And if authentication is hash function based, then the whole structure cannot be considered to be unconditionally secure. But at the moment, the confidence on hash function is very high. And even if I have to implement something, and I may go for hash function, but the fundamental issues need to be known and discussed. And this is the intrinsic interest to look at the identity authentication schemes, privacy amplification schemes, and cryptography as a whole, not restricted only to QKD. So with this, I'll stop. So any question?
Question in the chat box.
Anirban,
Sure.
you didn't talk anything about noise in this. What do you think would be the impact of that on this? Would it be on a technological level, or can it have impact on a foundational level also on these questions?
So in all this analysis, especially in the security analysis, we consider that, everything that has happened due to noise, we consider them as part of if. So one way to security analysis is that I consider that if has replaced my noisy quantum channel by a perfect channel, and all the everything, every error which I see in my comparison page is because of the if, not because of the noise. So with you, we have done several works on the effect of noise, but when I do security analysis, then I consider that the channel is not noisy, rather any effect which is coming because of the noise is also due to Eve. Means Eve has done a kind of attack where he replaced my fiber with a perfect fiber and trying to hide behind the noise.
Yeah, but I have one query because see, sometimes it becomes important to see whether this noise is coming from some other source or it is from Eve. Means there comes thing how to distinguish between the two. How does
Yes,
then
means,
one go about that
no, that
basically?
of course, the channel characterization is very important, and that's what led to the idea of decoy qubit. I mean, decoy means initial this classic papers are classic because they address fundamental issues like ping pong protocol address the fundamental issue that direct communication is possible. B92 protocol tells that only two state is sufficient. So similarly, the decoy qubit paper, the first address this question that how to address the difference, how to differentiate between the channel noise and the eavesdropping noise. So when I intentionally introduce those decoy qubits, so looking at the loss pattern, I can identify that what is coming from the noise. And so there are fundamental tricks for that also. And this is of course a foundational problem, but and in many places means we have decoy qubit based implementations beyond BB84 protocol. But as far as security analysis is concerned, it's better to consider that any error which is coming. So if you pose more to Eve, there is nothing to lose that than to reduce the efficiency of Eve, means considering that it's not because of Eve and it is because of the channel and something is leaked. So it's better to consider that everything is because of Eve. So that's a strategy in security analysis. But in general, of course, the channel characterization is very important.
Okay, thank you.
Subhashis, any other questions?
Yeah. Hi, Anirbandha, Himadri here.
Yes, please.
Hello. Yeah, so I had two questions, but yeah, the first one is like it's a bit silly. So I just wanted to know, is there any physical motivation as to why you want to get rid of the classical part of QC, like a BB84 or something?
This is a fundamental question, means which is addressed for many years. That means which part I can do purely quantum mechanically. But as far as the identity authentication is concerned, that has a strong motivation, because if the identity authentication itself remain conditionally secure, then the whole protocol will remain conditionally secure. But getting rid of the BB84 classical channel is not of that fundamental motivation. That's just a theoretical question that whether I can get rid of it, and if I can get rid, how much we can get rid. And the other question that whether I always need to generate a key and then use classical tricks that I have a message and I have a key and then I do bitwise XOR and send it. So that will always be secure because Karsav's principle tells you that the key is secure. Then the protocol is secure. But then the fundamental idea that whether I can do without this pre-generation of key, a direct communication, lead to many other ideas, which has more implications in the society. If auction can be done in a sealed bid auction, then corruption will be reduced. If voting can be done, then democracy can be strengthened. So there are the applications went beyond QKD with the advent of this kind of ideas.
And the second question I had is like you also have this a lot of post-quantum cryptography.
Yes.
Which is somewhere in between classical and quantum cryptography. But do you think like in terms of implementation, we would be easier just doing quantum cryptography rather than post-quantum?
Post-quantum is definitely easier, but post-quantum is still classical and still conditional. It's neither unconditional nor quantum. There is nothing to do with quantum. So the idea is that, so in the classical theory of complexity, there are many things which are in computer science, which are belief. There is no proof. So at the moment, we know of only a few quantum algorithms. So we have a handful of quantum compute algorithm, and Peter Shor has a nice article that why they are so few. So one thing is that we don't have a quantum computer to play with. We live in classical world. So whatever be the reason, there are few quantum algorithms, and all those works in the BQP complexity class. So corresponding complexity class in classical world is BPP, and it is believed now that BQP is a subset of NP. So if PQP is a subset of NP, then there may be some problems which are NP, but which is not in PQP. So if I believe this, but this is a belief, this is no proof. And then I assume that quantum computer can only provide efficient algorithm for problems of BQP complexity class. Then there will be problems in BPP complexity class, which is outside, NP complexity class, which is outside BQP, which will not be solved by quantum computer in efficient manner. So in that case, even after the discovery of a scalable quantum computer, those problems will not be solved in polynomial time, and they will lead to classical cryptographic schemes, which will be secure in the post-quantum world. Post-quantum in the sense that when scalable quantum computer is available. But here are the assumptions that you cannot design. So firstly, nobody knows whether P is equal to NP or not. So here is the assumption that NP has some problems outside BQP. Here is the assumption that quantum computers cannot do problems outside BQP. So these are subject to proof, and there is no proof. So this is a belief or condition on your assumptions. So this is still condition and classical.
Yes. So lattice cryptography would be like NP hard, which is assumed to be not PQP.
No, at the moment it is believed that it is a belief that quantum computer will not be able to solve it in polynomial time, because quantum computer solve all the problems so far is in BQP. So it will not be able to do outside BQP. But even whether P is equal to NP or not, that is not known. So nobody even knows that. Even you cannot prove that in classically also tomorrow you will not have a problem. You will not have a protocol which will be able to solve this kind of codes, lattice code. So that's very difficult to prove. So it's based on a lot of assumptions, and this is the assumption at the moment, that quantum computer will solve only problems in BQP, and there are problems in NP which is outside BQP.
Okay.
So Anirbandha, on the same lines, can we say that in post-quantum cryptography era, I mean, is it like kind of an assumption as of now that quantum computers would not have any role to play?
No, quantum computers will always have a role to play. So even if you see these protocols, I mean, so-called post-quantum cryptography protocols, then it will depend on the known algorithms. Means, like, for example, to get rid of an attack by Grover's algorithm. So it's not a serious attack, but you have to kind of enhance the key size for the same, to remain secure for the same time. Grover has a quadratic saving, but Grover can be used to attack. So there will be more algorithm and more attackments. So even if we cannot have a really a quantum algorithm for breaking this code, but that's a very strong assumption. Means still we don't know that what quantum computer will be able to do.
Okay.
Any other?
What do you think is the future of QKD? Because this European Union and even NEST is suggesting to go for this quantum safe cryptography, there is no need of this QKD as such to make it safe against quantum computer. So what do you feel that? What do you think that is future?
No, I believe that means hybrid technologies will rule for many years, and then before. So there will be a parallel market. Means quantum cryptography will definitely have a market, but hybrid technology will be more popular, and it will
when
depend on the
quantum
business model.
cryptography, it is QKD or quantum safe cryptography? When you say quantum cryptography, both
are. I don't say quantum safe cryptography. So I'm telling that means the hybrid technologies will work better. Means to begin with, the hybrid technologies will rule. Means where part of the network will be quantum secure and the part of the network will be classical. So the whole thing means is not going to, or the semi-quantum kind of things which
then integrating won't be very difficult. Integrating like
this
nowadays everything is internet.
Like
unless until it's the internet, it's not going to work.
There are business houses. Means many things will depend on how it is sold. So for example, when Samsung introduced a nano washing machine, so the paint was nano. So Samsung already has a phone which claims that they are doing something, providing the security in quantum world. So there will be some small tricks and tricky telephones, tricky tricky laptop and which will implement semi-quantum kind of thing. And hybrid thing will work, means the part of the network will be, and then up to a trusted node, it will be quantum secure, and after the trusted node, it will be at a region, means it will be classically secure. Means those things will come. But if the market has to be large, it has to be hybrid.
Very much unclear how things will move here, really.
Means certain things will not be governed by actually by us. Means certain things will be governed by advertisement agency and how
Market, yeah, basically. Yeah.
So market is also means the rule by how it is presented by big houses.
Let's see how it goes. Thank you, Anirban.
Any other queries? And thank you for your contribution.
Okay. Thank you. Hello. Sir, you are not audible. Hello. I think some network issues there. So, I think thank you so much, Professor Pranjati, for chairing this session of the conference. And I thank all the speakers.
Can you hear me now?
No, sir, you are not audible. The voice is breaking so much.
Yeah. I am
Hello.
just saying I'm closing the session. Please close this session.
Yeah. Okay. So thank you so much, Professor Pranjati, for chairing the session of the conference. And I thank all the speakers who delivered really interesting talks in this session. And now we will take a break for the lunch, and we will resume again at 1400 hours Indian Standard Time for the next session of the talks. So I thank all of you for joining. So,
Thank you. Thank you very much.
Hi everyone, I welcome you again for the second session of the day. We will start with the talk of Professor C.M. Chandrasekhar from MSc Chennai and Professor Usha Devi will be chairing this session. I therefore kindly invite Usha ma'am to please take over from here.
Thank you. So, am I audible? Hello?
Yes, ma'am.
Okay.
Yeah.
So, good afternoon, everybody. We have, in this session, we have 3 talks. First talk is by Dr. C.M. Chandrasekhar. He is a faculty member at the Institute of Mathematical Sciences, Chennai, and also an affiliate member at the Institute of Quantum Computing, University of Waterloo, Canada. He completed his BSc from National College, Bangalore. In 2002, he moved to University of Oxford, UK on Rhodes Fellowship. I had met him as a student when he came to Bangalore University when he was studying in National College or a little later. So that's how I got to know about Chandru earlier. So then I recognized that he's now working on this field, etc. So at Oxford, he had worked on experimental Bose-Einstein condensates, but gradually he developed his interests in theoretical aspects of quantum information theory, which led him to Waterloo, Canada, and where he worked under the supervision of Professor Laplan. He finished his PhD in the year 2009. He is interested in quantum algorithms and quantum simulations on near-term quantum hardware. He works on quantum walks, quantum cellular automata, and open quantum systems. So I request Dr. Chandrasekhar to present his work in this session. Hello? Hello?
Okay, so am I audible now?
Yes, yes.
Okay, thank you very much for the introduction, and yeah, it's a pleasure to talk in the conference, which is organized by our colleagues, and in this time, this is the only way we can get in touch with each other. And very unfortunately, giving lectures by sitting itself makes it a bit, very. Yeah, just give me a second. I'm just sorting out. So is my presentation full screen now?
Yes, yes, yes.
Okay.
It is full screen.
So thank you. So I will try to give a slightly bigger picture of kind of work we do towards quantum simulations, and particularly how we want to make it operational such that they can be physically implemented on an experimental setups which are available. Keeping in interest of some students, I know I've been at least a couple of sessions, a few sessions attended. I saw there were many students. So first few minutes I will try to dedicate to give a very general introduction, and I apologize for all the experts because it will be very basic and okay. So what are quantum simulations? In fact, it's one of the first motivation to think in the direction of developing quantum computers. We might have all read about Feynman's, questions asking like, if you really want to simulate a quantum system, you really need, or like if you really want to mimic one quantum system, you need another quantum system. So that is the basic idea, and that was the first motivation to look towards developing quantum computers, and then there were computational applications and various other advantages which was foreseen, and the areas evolved to a very big field of research interest now. So the basic principles of quantum simulations is used to principles of quantum physics to develop tools for solving challenging problems. It need not be just focused to physics, chemistry, biology, or whatever it is. For example, if you see here, there are various, at least last century, we know that the nature is largely defined by quantum mechanical systems, at least at a microscopic scale, which means there are some states which evolve with some set of operators. It can be unitary or noisy evolutions or whatever it is. So if there are some real systems which evolves with time with some set of operators, we want to look at some kind of an artificial or an engineered system which is very closely related to what the initial state of the natural system you want to consider, and try to look at a good approximation of operators which mimics the dynamics and see the final state and make a measurement. So this is just a schematic view of what quantum simulation should be. So the main objective is to harness a controllable quantum evolution so that you can actually access inaccessible complex systems. It can be something, for example, in LHCs, people are doing experiments where quantum physics plays a predominant role in deciding like what should be the way you have to engineer the collisions or all those things. But these are like very high energy setups and needs a lot of financial investment also. If we have a good quantum computers or quantum simulators developed, so one can actually optimize what real experiment had to be done, and that reduces, a complexity of doing some trial and errors and working around it. It's also true with looking at biological systems or drug designings or wherever quantum physics dominates, which it also reduces the exponential resources needed. For example, if I have a quantum systems to simulate another quantum system, then we don't need an exponential resource, which we will see in next few slides what I mean by exponential resource when we talk about simulating quantum systems using a classical system. So this is what it looks like. For example, if I have a quantum system, it can be an atom, 1, 2, 3, 4 atoms, or whatever it is. And if they can be in superpositions and there can be some interactions, then we can always write them in a computational basis. If I'm taking an electron and if I'm taking spin up and spin down, I can choose two computational bases, and I can say a single quantum system, another quantum system with two computational bases equivalent can mimic one electron. And similarly, a classical system, you need two bits, like two classical systems to mimic state 0 and state 1. It might be spin up and spin down. So if the number of quantum systems increases, for example, even having in 4 quantum systems, if you consider the possible superposition states or possible eigenstates, it can be, or vectors it can be. So you will need about 16 classical bits. So, but if I have another quantum system to mimic, then just 4 is enough. So if you go up to 50 quantum system of 50 particles or 50 energy levels, whatever we want to simulate, the number of classical resource needed is to the order of 10 to the power of 16. So which is 15 to 16, which is really stretching the limit of the current super computers available. In fact, if you have seen news for last couple of years, when people talk about quantum supremacy, or there are some devices which are looking at, their targets are around 50, 60 between 50 to 60 qubits. And this is the reason why they'll say, if you have even a good, reasonable quantum simulation or a computational system developed for 50 qubits, then you have achieved to some extent a regime beyond what any best classical computers are available. So it gives an idea of the scalability or the resources which quantum simulators can give to simulate some quantum systems, which are inaccessible quantum systems, I can say. Even a simple examples, which probably would have seen these things very predominantly in various set of lectures. Even a simple hydrogen molecule, which has some chemical complex of this form, H2O, you need 10 to the power of 4 classical bits to exactly simulate the whole dynamics which is happening in hydrogen molecules. Or if I have a quantum systems, then we only need 14 qubits. In similar way, even some things which we daily use like sucrose or caffeine, you see that you need 160 or 270 quantum bits needed to simulate them, and the classical resources are already far beyond an exact approach. So how do people do now? For example, there are a lot of quantum chemists who are a drug industry where people are doing certain simulations and working out some configurations of chemical complexes. They do use a lot of approximation approaches and some parallel breaking processes, which means that you are losing some details of quantum dynamics in such kind of approximations, and probably that's one of the reasons why we might not have we are not in a position to have an exact drug design or understand whole dynamics which are happening in most of the systems. We have a good approximations of them, just because the current classical computers do a lot of approximations to simulate some of these systems. In fact, people don't even have a model for many of those exact dynamical models for many of these chemical dynamics. So one of the other prominent examples which do occur quite often in quantum chemistry is the nitrogenesis processes, which is largely used in fertilization industries, or to develop fertilizers to have good agriculture yield. So this is nitrogenous enzyme. There's a whole complex of this form. You have F, which is sulfide cluster, iron sulfide clusters, P clusters. And we can forget about whole of chemical details in this structure. But what is known till today is currently the whole complex or nitrogenous enzyme has a huge complex of this form, but there is very small sections of them which current best classical computers can simulate. The rest of them all are with approximations, and there's no proper way of simulating all of them explicitly. So it means there's a long way to go in the field of simulating some of these dynamics exactly as possible, because we are still at this small scale of looking at some. So another interesting thing, which has been for last 3-4 decades, even before era of quantum information came in, understanding photosynthesis has been a very interesting topic. I mean, if you really understand them well, you can actually develop devices which can mimic them with good efficiency. Current laboratory solar cells are very low efficient, and we probably need a lot more efficiency. And we are not at the stage of improving those efficiency because we still have some gaps in our understanding. This is one example of FMO complex where it's which is named after the three scientists who worked on it, or broke down the structure. If there is an energy which falls on it, and there are some 7 site centers and 1 reaction, total 8 centers, where energy transports from sun into it to a reaction center where it converts into its survival. So here, one of the most interesting thing which has been known here is that these FMO complexes are in certain algae which are in sea 5 kilometer depth, or deep inside the sea. And even if 1 photon enters into it, they efficiently convert into an energy for their survival. So they just get 1 photon 1 in 2 to 3 days. So with such low photon entering them, they efficiently convert them into energy and survive. So understanding the model was, how is this process happening, was something which was explored for many years. And over the last few years, quantum coherence and its role in modeling these dynamics was very prominent. And this is not a settled debate. Even after establishing various good experimental papers were there, and then theoretical models were developed. So even a few months back again, there has been some challenges in, posed against the quantum models of it. But which also means that these are all evolving areas where we are only improvising our understanding of how the dynamics are happening and how much is quantum. So once we understand and model them, one can probably look in towards simulating the dynamics which is happening in these kinds of systems. So they have probably a long-term applications once we do that. So currently available systems for quantum simulations, we could say, we have superconducting systems, we have ion trap systems, ultra cold atoms where atoms in optical lattice can be controlled. So NMR systems were something which played a very important role in early days of the field. So they could simulate various things to show that these are practically possible. So current developments, significant progress is happening in the area of photonic systems, where photons have been extensively used to simulate some of the dynamics. These are all at early stage, but these are all the candidates where one can have a controllable quantum systems to simulate one or the other system. So giving this as a bigger picture, in fact, I have tried to go towards the problems we look at. So our interest is to have a theoretical framework or operational approaches to simulate some of them in any of these systems, right? So you want to, as I mentioned, it might be a FMA complex, or it can be some dynamics in chemical systems. So there are some known ways those dynamics are defined. We want to convert them into an algorithmic formalism, or give an operational approach such that we can convert them into gates and implement in one of those systems. So that's the direction we try to look at. So in simulations itself, people have these systems. When we talk about these systems, there are two standard ways of looking at quantum simulations. One is a digital simulation approach, and the other is an analog simulation approach, right? So in digital simulation approach, which means we try to take, like I was mentioning about the chemical complexes, or like any dynamics in them. So people do study them in form of Hamiltonians. They're complicated, complex Hamiltonians. So now, taking those Hamiltonians of those complex systems, so it's trying to find some approximate ways of breaking them into small implementable parts, so that we can make them as stepwise unitary operators with minimal errors. So once we break them down into some set of unitary operators, then those Hamiltonians would be very good. Those Hamiltonians can be converted into a unitary operators, which can be converted into gates. And once we have it in gates forms, then they can be implemented, or can be executed on one of those gate-based quantum computers. So one has to take a very good precaution to look at making those approximations minimal, so that you have a good match of these unitary evolutions into what the real dynamics happens. So there are various ways of doing these kinds of decomposition of Hamiltonians. I'm not going to touch in detail, or even just giving an idea of it. So which means that these digital simulations are not much more universal. So it means once I break them down into a set of unitary operators and gate operations, then it's implementable in any of the gate systems. All that we would need is whether these system can implement such gates. It's like it can be C0, control not, or any poly operators. And analog quantum simulations are a bit more rigid, in the sense you try to look at some Hamiltonian in nature, or some systems which is of your interest, and you try to find some other system in nature which has an Hamiltonian or a dynamics in it bit more closer to it. So it's not that you have a complete universality there, but you do have some kind of closeness. So with that closed Hamiltonian system, or a system which has a Hamiltonian which are closer to it, you take them and try to manipulate them in a very small scale, and try to simulate using that approximation. So it's like in this, you have some rigidity in the way of doing it, but it has been quite successful in, if I want to model some lattice systems, then I can actually take another lattice systems whose Hamiltonians are, have a similar kind of dynamics, and then make it bit rigid. So in that way, it has been quite effective in looking at it. Particularly atom-based lattice systems have played a very important role in simulating some of the condensed matter systems over the last few years. So these are two standard ways of looking at it. And our interest has largely been towards a digital quantum simulation. And so we also try to take slightly modified approach in the way here talk about take an Hamiltonian, decompose it into combinations of stepwise unitary operators. But we do it slightly different way, and I'm going to give a picture of what approach we take. So instead of taking an Hamiltonian and breaking them into unitary operators, we construct and some kind of dynamics which are more universal, and then work at it. So that's probably what you call it as a quantum walk approach. And I'll give a quick introduction to the quantum walk dynamics, and then present how it can be used to model or simulate a simple Dirac equations, digital simulation, and some of our recent approach towards understanding are developing an approach to simulate dynamics in polycyclic aromatic hydrocarbons to understand the stability. And these are again some things which are known already in the literature, and we want to give an algorithmic approach and to match such that these simulation protocols would mimic what is happening in the dynamics. Once at elementary level these are satisfied, then probably we can scale it up to more complicated systems into consideration. If time permits, probably we will also give some idea of how we approach open systems and with what approximations are taken so that you don't lose out the generality in picture, but you do capture the most salient features of the dynamics and probably the circuit form of the Sefima complex also. Okay, so the simple way, in fact, why quantum walk is a big motivation for us to look at it, and it's not something which out of blue. It's just that last 50, 60 or 100 years, classical random walk has played very important role in simulating classical dynamics in a whole lot of systems, from biological systems to astronomical systems. Wherever people are looking at dynamics, they do efficiently use classical random walk as a model in various colors, forms, dynamical structures. And that is still a strong motivation for us to believe quantum walk has a very important role to play in simulating various quantum dynamics into the picture. The differences, there's few fundamental difference where in classical random walk, like you see here, you toss a coin, you go to the left or right. It's always one of the paths you choose and then you move on. So at the end, the probability of getting or reaching a destination will be very low. But in a quantum picture, you try to evolve them in superposition. When the measurements are not made during the process, you would end up having a superposition of the walker at various places, and there will always be some finite probability of finding a walker at the place where one hits. So this is the fundamental difference between the classical random walk and quantum walk. There's no randomness in the evolution process. Only when you make a measurement, there is randomness in the dynamics. So mathematically, it means that we take two Hilbert space. I'll first give a description of a discrete version. The coin and the position space, which can be spin up and spin down, or you can use any computational basis to represent them. Or it can be polarization, horizontal, vertical polarization, if I'm talking in terms of photonic language, and the position space. So quantum systems or quantum mechanics allows us to have a superposition. So it can be in any superposition form. Initial state can be in any superposition form. And then you have an evolution. Coin operation is just like coin toss in classical version. You toss, you get head or tail, but these are in the vector space. So instead of having head and tail, you can have a superposition. So which means that this matrix, even if I'm beginning with only spin up or spin down, this coin operation can bring them into a superposition. So there's a conditional shift operator, which means that if it's spin up, I move to left. If it is spin down, I move to right. But quantum superposition is there. So which means that it's both in spin up and down, which means this operator will simultaneously evolve in both left and right position. So it's just like in this, I said it can simultaneously evolve in all possible position space available to it in the next step. So this is just a mathematical construct of that, where we can see that simultaneously. So that it might look like, oh, it is evolving simultaneously. What's the big difference? What happens is that during the evolution, we end up having constructive interference away from the origin in quantum version, and we do have such kind of probability distribution, unlike the classical random walk, which is spread. So which means that if you're looking for some region around here, classical random walk would never be able to reach there, but the quantum walk could reach there with some fine probability at this point. So this was a big motivation for computer scientists to develop quantum algorithms or quantum search algorithm based on quantum walk. So there's been various algorithms which has taken advantage of such kind of quadratic spread or speed in quadratic spread and to look at it. Okay, so this is a quantum version of it. This is just a dynamics which you have a particle, you have a coin operator which can evolve it in, which can bring it in superpositions of its state, and then a shift operator which can spread it in position space. So the basic idea is just this. Each step is composition of coin and a shift operator. So this is a discrete version, which is discrete in time. So there is also a continuous version of it, which would mean that you can have any graph. In that graph, you would have vertices and edge, and that graph you can construct an adjacency matrix. Like it means that if you have an edge connection between I and j, in that adjacency matrix, you give value 1, and if there are no connections, you make them 0. And each vertices in a given graph structure can be represented in a computational basis. So from this adjacency matrix, one can construct an Hamiltonian where D is a diagonal matrix and an adjacency matrix. So from this Hamiltonian, so you can always consider an e to the power of IHT, and then you can evolve a dynamic. So here we don't have a coin operation explicitly, so it doesn't have a spin degree of freedom, spin up or spin down. It evolves only on the position space. So this form of dynamics is also a lot more closer to the Schrodinger evolution, and this also has been extensively used to model some of the dynamics in condensed matter systems over the last few years. So there are these two versions which has been effectively used for model and algorithmic purposes these two forms of quantum walk has been effectively used to model dynamics. So now we want to see, I want to give a quick overview of some simple dynamics, which you call one of the standard textbook dynamics, unlike Schrodinger equation. This is a Dirac equation, right? So this is a standard Dirac equation which we find in any quantum mechanics or relativistic quantum dynamics textbooks, where you have first order time derivative, you have an Hamiltonian, and the Hamiltonian will be in these forms. This alpha beta matrices, which are poly operator combinations of them. Even before the era of quantum information or quantum computation, people working in field theory wanted to use computers to simulate the dynamics of Dirac particles. And at that point itself, there were some way of discretizing them, and they looked at various approaches. I'm not going into the historical aspects of it, but what simply we can see is that such kind of dynamics, such kind of differential equations can be discretized by converting these differential operators, these derivative operators to difference operators and written down in a matrix form. I said there are spin. So these are like 4x4 matrices in general form. You can also have a 2x2 matrix Dirac equations. We take that as for simplistic form here. So spin up would have some moving left component, like going to the left with some alpha probability. And then you would also have a spin down moving to the right component, which will also have the same defined by the matrix alpha. Then you will also have some form of this form. I mean, this is discretized to arrive at this form. So this matrix, you can say the diagonal elements have components moving to the left or moving to the right. Off diagonal element does not have any translational component in that. So this is the form of Dirac equation. So you can take a Dirac equation and just discretize it. You can discretize in various ways. In whatever form you take, you would end up having a unitary operator of this particular form, which means that psi of x going to, and when I say t minus, which means that it is shifting to x minus, t plus shifting to y minus. So this is a form where from that we can actually convert them into momentum basis and write down an Hamiltonian for a Dirac equation. So where beta or alpha terms can be considered as like mass and velocity terms, and mass is there, acceleration is there, and the speed of light component is there. All of these things are encompassed inside this alpha or beta terms explicitly in one or the other form. This has nothing to do with our simulations or information theory protocol as such. This is only giving you some idea of how one can discretize the Dirac equation and have a form. Now, if I want to simulate Dirac equation, I either look at some system which would mimic this dynamics, or I try to engineer the dynamics of some system which would at least implement this form. If I can implement this kind of dynamics or this kind of unitary, which means that effectively I have simulated Dirac equations. So what one could figure out that was the quantum walk I described to you, the discrete version. You do a coin operation and you do a shift operator. There is a coin and shift operator separately. A simple math, if I combine them together, I end up having a matrix of this form. Right now, if I look at the previous slide here, we see here, you have a matrix here, like alpha and beta components are like, there are some scalar terms we can treat for the time being, or like some weights. So you have this diagonal elements which has translation components, off-diagonal element doesn't have. But here in quantum walk, we have translation terms in both diagonal and off-diagonal element. Is there some way? I mean, it means that effectively it is in this form. You have translational element at all the places, the cos theta and theta. If there is some way where I can reduce the component, for example, simplest way would be like I make theta is equal to 0. If I make theta is equal to 0 or like tend it towards 0, then off-diagonal terms will become vanish, which means that you will not have any translational component in it. So only in diagonal terms we will have translational component, which means that effectively we can simulate massless Dirac equation, because we said the mass terms here, which means that beta becomes 0. So which means that a massless Dirac equation can be simulated using quantum walk if I'm making theta is equal to 0. But there should be some way where we should retain theta and still have this translational term vanishing in that dynamics. So if we can devise some operation form, some unitary evolution form, then one can look at it. So there are ways to do that also. Instead of having a quantum walk where I have a unitary operator and simultaneously move to the left and right, one can think of splitting each step of walk into two small steps, where at one time I have a unitary operator, like, I do a coin operator, shift only to the left, which means I only move to the left and I don't move to the right. I know there's some component which stays at the same point and move to the left. So which means that I do a coin operator and shift, one state shift, other states remains there. The next step, I again do a coin operator, now it moves to the left. So which means that at all three positions, I would have a non-zero probability, and each step is broken down into two small split steps. So once I break them into a two small step, we can clearly see that the dynamics or the unitary operator would take this form, which is very much like our Dirac cellular automaton model, where when this Dirac equation was discretized, we were getting the same term. The only difference is my cos and sine thetas here are replicated, or like are mimicking beta and alpha terms, which are seen in Dirac equation. So now this not only gives us that this form of quantum walk not only mimics Dirac equation, it also captures some fine. This is the blue one here. One could simulate. The regular walk would only do this. The red outcome or plots, but these fine oscillations also are something which are known as Zitterbang oscillations in Dirac equation. Even those things are mimicked very nicely using a split step walk. So now theta operator is my coin operator, which means it's an operation I'm doing on a simulated system. It means that I have a simulator, from that I define different theta, which means those theta is mimicking mass and acceleration or velocity term in the system. So which means that I can vary different mass and I can simulate the dynamics. I can say what is the effective outcome of such kind of system. So here we didn't go with the taking Hamiltonian, breaking them. There was that form separately, but here we started from scratch of just taking a qubit, defining an operators on them and modifying a dynamics such that they mimic exactly what a Dirac equation in discrete version mimics. So these approximations, I know people were interested in this problem from quantum gas automaton model, and various work happened over last few years to arrive at some acceptable form of operational approach to that. So once we had this kind of operational form, the next was to see how one can think of converting them into a circuit so that it can be implemented on the existing simulator. So the basic form, whatever might be the operator there, the current existing quantum simulators or computers work on these basic gates. If we can implement these sets of gates, then one can simulate anything on that kind of system, or and that's what the universal computation would say. So we kind of, there are a lot more details into the whole way of converting them, converting the whole unitary operators of quantum walk into circuit form. Here I'm just presenting one simple form of circuits specifically designed for ion trap quantum computers in Maryland, looking at the way they can work. And it was optimized to see that the coherence time is still within the region so that you can see a good experimental output. It's only a few steps, but we could, these are the controlled NOT gate. It means that you take a 5 qubit, it's actually an 8 qubit machine, but effectively it was a 5 qubit machine where one of the qubit was treated as a walker. The rest 4 qubits were used to mimic the position space. So with 4 qubit, we could have gone up to 15, 16 step, but the coherence time did not allow. So we had to look at the 5-step simulations of it. So there's a coin operator here under rotations, and this combinations would give a shift operator to the negative and a positive sign. And effectively, since it was worked out for the specific configurations, so the gates were minimized, and this configuration was implemented last year to demonstrate that a Dirac equation can be effectively simulated using a quantum walk approach. And these are the experimental results, and which matches a numerical output. So now, in fact, though it's not in this presentations, but we also attempted to try to see mimicking curve space, which means Dirac equation. We have looked at operational approach for curve space as well, which means capturing the curvature from operational approaches, which means can my probability output would say what was the curvature in the space in which the particle has propagated. And that one could not take up experimentally because the gates were crossing, even with the few steps, gates were crossing the currently available coherence rate of ion traps. And currently ion traps have the best coherence rate. So which means that if it's not possible in ion trap for the time being, it's not possible in other systems, but might be with time, there will be better coherence rates or improvisations which can happen. Earlier quantum circuits available for quantum walks were not optimized. So even implementing few steps, even 2 steps were not possible with it. So we optimized this using various approaches to be executed. So this is a neat, simple, closed system. It's nothing very dramatic because I can go to classical computers and simulate these small steps. But the demonstration shows that a quantum system is effectively mimicking another quantum system. And the operational approach is working here, an algorithmic approach is working here. So which is a promise to scale up to n higher dimensions. Now, I think I do have still quite a bit of time left. So I'll try to take up another interesting problem here, which is we are all now we have gotten used to searching the space available, like the internet space, what we call the virtual world for us. We go to Google search and we get the data. And Google has certain algorithms in which it ranks. And I'm not going into details of the Google search algorithms, but one can adopt a quantum, one can develop a quantum algorithm to do a similar kind of search. For example, if I'm taking some network like this, a graph structure, which has some 7 nodes, and you can see some of them has a long, more inward paths and less outward paths. And it would mean that some nodes have higher importance than another node, as simple as that. Okay. So using quantum walk, like again, it can be, one can use continuous time quantum walk, or one can design a complicated form of discrete time quantum walk, and you can develop an algorithm. It's just like, to identify which nodes has higher rank, which means that which nodes has higher importance. So comparing with the Google ranking algorithm, that is the blue one, which is here the classical approach, and then the quantum walk approach, we could see a good match of using quantum algorithm itself to rank nodes in such kind of simple. This is purely of, currently it's only a mathematical interest, let's say, an algorithmic interest. So when we test into various other structures, this is another popular GNC network, which has 15 nodes, and you are comparing with the classical and the quantum approach, we could see a similar trend, but there were some fine differences one could notice compared to the classical one, which only says that in quantum dynamics we do have some interference effect, which does not happen in classical dynamics. Which means if there are real systems like this in nature, and if we are using a classical algorithm to look at it, we do miss certain fine behavior like this, which are caused by quantum interference effect. and classical algorithms would not capture them, but quantum algorithms would capture them effectively. And we could see that these kinds of differences, which are an effect of quantum interference in many of these larger networks, which was missing. And in smaller networks, it's very difficult to identify them and pinpoint. But in any larger network, we could pinpoint and identify them effectively. So now this is again just a mathematical formalism. Like I said, quantum walk is only a simple algorithmic approach to begin with, and that is applied to a network to see the ranking. So our interest was to see, is there any system where this can be applicable? A simple example would be, again, these are still a closed system approach. This is to model a dynamics in chemical complexes. Chemical complexes are a huge pool of them. One has to pick something which is simpler to begin with and look at it. So polycyclic aromatic hydrocarbon, which are like, structural combinations of benzene ring, or we call a benzoid polycyclic aromatic hydrocarbons. One example we could pick where we wanted to apply quantum algorithms on them so that you can rank active centers in order of their reactivity. This is known experimentally in some forms, and there's been a good, there's still been a lot of debates how the dynamics happen in such kind of aromatic hydrocarbons. So what makes certain sites more reactive than the other ones, and what causes delocalization of electrons in these rings? So in this ring, it's a benzene, simple benzene ring, and this is a naphthalene, two benzene ring together is a naphthalene, and the three, as it can be in different configurations of them, and this is anthracene, and then the other one is phenanthracene, which is like 3 in this geometry. So now, among these configurations also, there are very few stable configurations which are known, and how this few reaction centers are considered, or like few sites are considered more stable or like more reactive than the other one. So these data are available from an experimental output. So we tried to model delocalization, which is of electrons in these rings. And here is only schematic for only one, which is for naphthalene ring, and we are not presented, which means that you consider the hopping electrons in each nodes, then you implement a continuous time quantum walk on them, and then see whether they replicate what is happening effectively in nature. And for a good set of time, or the way we looked at it, it really could mimic the dynamics of electrons in all the structures we looked at it. And it also helped us effectively. In fact, there is a lot more details when we say how we calculate the nodes, the connectivity. Now you take hydrogen CC conjugate double bonds of them, and then there are already vibrational frequencies of these available from the experimental results. We would take them as a weights in our graph. If you remember the continuous time quantum walk, we said you construct an edge, depending on the connectivity, you write the coefficients of their weights, and then use the similar way, looking at the bondings or the vibrational frequencies which are available in literature, we construct the adjacency matrix for them, and then we looked at delocalization of electrons, which perfectly fitted to what something which is known, or the way it looks like. And this is the ranking of nodes in naphthalene. So naphthalene has 10 sites in them, and if I'm looking at which one are more reactive and which one is less reactive, we could see this exactly matches the rank site 3. It is known in literature that they have the less reactive sites compared to other one, and it perfectly matched from the modeling. So this is for like in a benzene ring, all sites are equally reactive. There is no hierarchy in them. But if I look for naphthalene, there are some hierarchy of sites which are being more reactive and less reactive. And if I'm looking at anthracene, one could rank the nodes accordingly, which one are more reactive and less reactive. All these things are coming from completely a quantum dynamic structure. We use both the combinations of continuous time and discrete time quantum walk model in them. To understand delocalization, it was a continuous time quantum walk model. To understand the way the ranking of nodes are happening, or like which one is more reactive and less reactive, so we kind of used a discrete time model innate, and it's nicely matched with an experimental. It's only a small step to see that how these are fitting in well. So probably a more complicated way of developing quantum walks for more complicated structure can be done to understand and expand them in looking at quantum chemistry itself in a different perspective. So now if we say, all that say up to this point is currently this is an operational form or an algorithmic approach. Now, if we want to go to quantum computers and simulate them, we have operators, quantum walk operators, and now we just want to convert them into circuits form, gate forms, optimize them, and then that would be the feed for quantum computers to simulate them effectively. Of course, currently for the dynamics which we have looked at, the gates, even if you sit and convert them into gates, they are not implementable in any of the current systems. Might be when we have access to just 200 qubits of quantum computers with a reasonable coherence, one can foresee or like envision of implementing them and implementing the dynamics of it. I hope I'm still within time. Okay.
Okay.
Yeah. So I'll quickly. I'll not take get into the whole details of it, but it's the quantum walk. I did give some introduction to FMO complex where the whole dynamics is happening, and this has been one of the very interesting topics for people from physics and chemistry overlap to look at them. I'm going to skip most of them and come to open system approach. I think that some of you did attend some of the open system talks which happened, especially Professor Jakipilio was also mentioning about how one use quantum gems and combinations of modeling unitary and gems together and break them. So one of the approaches we tried to explicitly use quantum walk and also consider open system here, it was to break the whole dynamics which was happening in that FMO complex. It is 7-site reaction center, photon is entering, and it is having a directed transport towards reaction center. So that's all what it is. But the model was you take quantum jumps, which has both noisy and quantum features in it, and a unitary operator. So break them down into an operators which only implement quantum jumps and the unitary operators to that. This is the whole pictorial representation for them and convert the cross operators and all of this. I'll skip all of them and I'll just come to okay. So here I have taken only 2 sites here and we break them down and look at all possible configurations, which means that from site 0 I can give them a computational basis, and site 1 with some probability P, each ops, or it's a reverse with probability P, which goes into them. When we have probability and an open system approach, you try to take these 2 sites and have 2 baths associated with them so that you make collectively as some bigger unitary picture. And then the subject of 2 sites is an open system for you, but when you're collectively having, it will still be a closed dynamics. So it means that I have 2 baths. These are the 2 bars, and one can model the dynamics of them and then write down a cross operators. This is only for 2 sites, and the whole details is there how one can consider a directed transport in such kind of thing. So now you can see that this is the way if there is an photon entering and it can take various paths in 1 or 6, and then there are reaction centers, or like it can go to 7, 4, 3 and enter into the site. So instead of doing what we treat breaking them into a unitary and then jump part for 2 sites, you do that for the whole 7th site. Take all possible configurations. Mathematically, you take them all. It's just a bit meticulous task. But once you write down, you have an Hamiltonian for them, and you can write down the operators, cross operators form with some good approximations. And when we simulate them, taking into account, again, there are experimental data available to give weights of what is the reaction centers. We just have to plug in those experiments to the model. And here one could see that if there is photon entering or energy entering into the site 1, then the probability of it ending at site C is, it's something which decreases, which means that from 1 it is going to site 3. So that's what it means. If there is a transport which is going here, with time, probability of seeing on site C, site 1 decreases significantly, but probability of seeing at site 1 goes up. But there's a small probability of being at other sites. So these two plots are something which takes open system into account, which means that you have noise which are mimicked by baths. If you take them into account, this exactly mimics what the experimental data people have looking at those chemical complexes. If I'm removing noise and purely treating it as a closed unitary system, you end up seeing such kind of oscillations. And it also says that now we can see the role of open system in really mimicking the dynamics that's happening in nature. When it's a purely closed dynamics, we would see these oscillations in site 1 alone and site 2 alone, and we don't see any transport, directed transport, which is happening in such kind of system. And how it varies with temperature, because all these parameters, when you take from experiments, then it's only part of plugging into a quantum walk. And when I'm talking about transport here or dynamic, it is still a quantum walk model. It's just plugging those parameters into them, which means that temperature is under my control. I just have to vary all those parameters, and we can see what is the effect of temperatures for such kind of dynamics, all those things. And when there is higher population certain site and for what temperature is low, all these parameters can be explored and studied in such kind of models. So we could even convert them into a quantum circuits form where these 7 sites can be mimicked by 3-qubit system, and you only pick few sites, and then 2 baths can be introduced, and one can break down the quantum gates to implement few steps of this dynamics. In fact, I will at this point I hope I am still within time to take 1 or 2 questions. So I will thank organizers and the chair, everybody.
Thank you. So your time was up to 2:50, including questions. So we have just 1 minute.
Yeah, it should be okay. I guess probably 1 or 2 questions.
Includes the questions also. Are there any short questions? Any questions, comments? I just have 2 questions.
Yeah.
Yes, please. Please.
Oh, yeah. Hello, Conrad. How are you?
Oh, hello, Chandra. Yes, it's Thomas. Good to see you. Thank you for your talk. Very nice. And I'm very interested in, you talked about, searching the internet and about the ranking of the nodes. And I would like to understand, is there a quantum advantage in doing this, even though it's a classical system? So, I somehow can understand that if you look at a chemical system, which is in some sense quantum, that you can see what the ranking of the reaction centers is, or so which one is more active or reactive. But is it true that we can have an advantage from a quantum?
Okay. So when especially node ranking algorithm, when we try to see how fast it is looking at it, so there are some advantages of ranking the nodes faster than the classical algorithm.
Yeah, and can you explain how this comes about? I mean, why should there be an advantage?
No, it is just because the quantum walk is trying to span the space of the network faster, right? So just that it's as simple as any quantum search algorithm which has been done. So when it is spanning the space faster in the network simultaneously, it is ranking higher. But one of the things I'm not very much interested in the computational part, so we didn't explicitly dig in that directions to give exactly what order improvements and all those things. Our motivation was, as I was showing in the plot, we wanted to see whether some things which classical can't do capture. Like you mentioned that, our interest is to see interference or some really physical systems, not looking at explicit advantage, rather than that mimicking them exactly in that form. In fact, that is still what I'm trying to keep our focus on and not look at the advantage aspect of it. I would like to always evade that question, say that we are not explored in that direction, but as at least when one of my student Pratik was explicitly looking at and is coming out with numbers, how much of iteration it was needed to do the classical and how much was needed to quantum, we can clearly see a faster convergence to the ranks in quantum algorithms. Thank you.
Thank you.
Thanks. So I think any others who have questions, please post it in the chats to Chandru and or email him if there is any. You will find his email ID. So thank you, Chandru, for your very interesting talk. There are a lot of questions, but it is.
No, yeah, we will discuss them. And, hopefully, we'll all get to meet sometime soon and spend time together, learn from each other.
Yes, then it is possible. So through online meetings, we can do at least this much. We can do. That's what is.
No. When we see each other's face, it just our face glows. When we it's just that we don't meet them all, and suddenly when we see them, it's still a good thing to have something going on.
Good thing to have but let us see. Let's hope to have our sessions where we can chat, we can talk over a cup of coffee, etc. Thank you.
Yeah, thank you. Yeah, thank you very much. I'll just try to.
Next speaker is another good friend of mine, Professor Prl Lakshmi Narayan. So I think he is around. You may try to check your slides, share your slides. So let me introduce Professor Prl Lakshmi Narayan. He completed his PhD in theoretical physics at Stony Brook, University of New York in 1993. And then he worked at the Physical Research Laboratory, Ahmedabad, at various capacities, first as a postdoctoral fellow, then a scientist, reader at the Theoretical Physics Division. And he also received the Indian National Science Academy's Young Scientist Award in Theoretical Physics in 1998. And before I met him, I had referred to his lecture notes and presentations on nonlinear dynamics and quantum chaos and other things. So afterwards, I met him in some of the quantum information conferences and workshops. So he has joined IIT Madras as an assistant professor in 2003 and currently a professor in the Department of Physics. So his current research interests are in quantum information, quantum chaos, and complex quantum systems. So it's a pleasure to request you now to look forward to your talk. So you may go ahead.
Thanks. Usha, I'm having some difficulty in sharing.
Any volunteers around? So will you try to help, please?
Because I can see the share button, but it is not really highlighted.
Okay.
I can see it, but it's
yes,
not.
sir. Can you say your problem again once more?
Huh?
Can you tell us what your problem is again?
I can see the share button, but it's not highlighted. So I can't.
Highlight.
Yeah, like what I have. I cannot share screen. So they have to, I think, do it for you.
We will just 1 second. We'll see what you get. Can you try again, sir, just now? Can you try again, sir?
Yeah.
Doctor?
I was able to do it for another meeting, so no, I can still not do that.
Can you try joining us again then? Can you leaving this meeting now and then joining again?
Yeah.
That is like the only other option. Sorry.
Wow, yes, we can see the screen now. Yes. Hello? Hello, Arun?
Hello?
Hello, yes, we can see your screen now. So
Sorry, so I was not this thing at all, is it? I'm sorry, yeah. So I think
it is seen now. So it's
okay.
3 p.m. now. So you have 50 minutes time, including discussions. So you may choose to.
So just give me I think just give me a warning, Usha, if you wouldn't mind, around
Sure.
40 minutes.
10 minutes early?
Yeah, thanks.
Okay, I will do.
Yeah, I'm sorry, I think I started my spiel before I had unmuted. So first of all, thanks, for the generous introduction, Usha. It's a pleasure being here, seeing you and other friends. And thanks especially to Subhashish for putting together a very nice meeting and with a variety of talks. So this work is with my PhD student Suhail and former postdoc who is now faculty at IIT Tirupati. Many of you may know him, Arvinda. And the talk is about putting together unitary operators in a circuit, which is basically a model of quantum computation. But it also serves as a model of many-body systems. And what is interesting is that if these operators are in some sense special, and that's what we would call dual, there are some nice properties of such circuits which make these many-body systems attractive to study. So I wish to talk about that. I apologize to those who may have heard this kind of talk, which I've been talking about in the last few months. So this is based on this archive, which has recently appeared in this publication. So the motivation is the following. I seem to be going on. Okay. The motivation is the following. In a classical systems, classical dynamical systems of classical mechanics, we have a certain hierarchy in terms of classifying randomness of systems, which means actually deterministic randomness. There is no randomness as such. It's only because of the dynamics itself, which is creating apparent randomness. So what is called deterministic chaos. But actually, even before chaos, there are systems which are ergodic in this hierarchy. The lowest are ergodic systems. For example, all 1 degree of freedom Hamiltonian systems are ergodic, especially if their energy is, if it's a bounded system, like a simple harmonic oscillator, 1 degree of freedom. But the word erg, as you know, comes from energy. So we would require that this ergodicity is applying to the energy shell. So two harmonic oscillators, which even though they are coupled, are not ergodic. And as we know, these are forming the basis of statistical mechanics. So Boltzmann assumed ergodicity, to which is, you may say, it's in some sense the microcanonical ensemble. Higher up on this are mixing systems. So by higher up, it means that mixing systems are necessarily ergodic, but ergodic systems are not mixing. So mixing, you should just have in mind dropping putting a drop of ink into water, and then the whole the ink gets mixed in the water. There is no ink that's obviously being created. The volume of ink is the same before and after, but every fraction of the final mixture has that original fraction of ink in it. So this is mixing systems. So this implies quite a strong thing. So, but there are mixing classical dynamical systems. Still higher up are Kolmogorov systems. We can actually think, for the purpose of this talk, that Kolmogorov and mixing are pretty much the same. But to be more precise, Kolmogorov systems have what are called positive Lyapunov exponents. So they are chaotic. So this would imply a measure of chaos. And then still higher up, at the apex of this hierarchy are what's called Bernoulli systems. And Bernoulli systems are, in quite a rigorous sense, as random as a coin toss. So one cannot really distinguish them from a memoryless coin toss, for example. So, but all of them, let me emphasize, are just Hamiltonian dynamical systems. What about quantum mechanics? So in quantum mechanics, such a hierarchy is not really well defined at some level. And but of course there is chaos. There's a lot of work these days on quantum chaos and so on. And putting together many body systems effectively leads to these kind of systems, which in the classical limit leads to these kind of systems. So one would like to understand such an hierarchy in a quantum mechanical sense. So how, mathematically, how would one describe this hierarchy? So one way of doing it, we usually define ergodicity as, mixing is, the phase space average is equal to the time average. But actually, if we talk in terms of correlation functions, one can describe all of these. So let us consider x to be a phase space variable. So x is a phase space variable, and I'm thinking now classical. And you have f and g to be two functions defined on this phase space. Phi t x means that under the Hamiltonian flow, after a time t, x has gone to phi t x. So that is a new phase space point. And this averages over some initial, it is actually over the phase space. So this is a phase space average. So this is a definition of a correlation between two functions f and g. F is evolving with time. G is not evolving with time. So this is telling you how this function f is decorrelating with respect to g. Now you may worry that there is no f of phi t here, but because of this flow is measure preserving in Hamiltonian dynamics, this is same as whether you have phi t there or not. So this is a 2-point correlation function after a time t between these two functions. One is evolving in time. So ergodic systems are those whose average correlation vanishes, average long time average correlation vanishes. That means that these correlations have some, in some sense, they are decreasing, but actually not in a strong sense, only in this average sense in time. So they can go positive and negative and so on, and then average out to zero. So that's an ergodic system. The mixing system, on the other hand, strictly goes to zero. As time goes to infinity, there is no need for time averaging. Kolmogorov systems, as I said, for the purpose of talk, I'm going to club together mixing and Kolmogorov. So we may actually think about Kolmogorov or systems as something where this mixing happens exponentially fast in time. Okay, so not only is it going to zero, it's going to zero exponentially fast in time. And at the apex of the hierarchy, this Bernoulli, this correlation function vanishes instantaneously for every time greater than zero. So this may not happen for every function f and g. I'm not going to go into details of that, but let us say that Bernoulli is characterized by an exponentially fast decorrelation. So that's as random as a coin toss. Okay, there are some very simple models that you can construct, like a baker's map, which is actually how a baker makes cake. Takes this mixing happens between the dough and this thing. So there are these simple mathematical models which have this property of Bernoulli at the classical level. So now what has all this got to do with this conference? So now let's consider these kind of circuits where we are putting together these unitary operators at these sites, so single sites, and then you are coupling them by some 2-qubit gates. So here is, in fact, this I've taken from this Google so-called quantum supremacy experiment. It's a 50-odd qubit circuit, and the problem is to initialize this, and then there are single qubit gates, and then there are random, so to speak, random couplings between these single qubit gates, and this is time on this horizontal axis or the cycle. And after the end of this cycle, a rather complex many particle state is formed, and the idea is to find out what is the statistics of this complex state here. And it is classically a difficult problem because you have to solve a 2 power 53 dimensional problem, as Chandru also was talking about in his last talk. But quantum mechanically, you have this advantage, and you can find out the distribution of the output. So these kind of circuits are actually quite mixing circuits in some sense, and they have been studied as random unitary circuits in the sense of, you can randomly pick 2 qubits and then you can have some interaction between them at each time. So this is a rather low level of interaction, if you wish. You're just selecting 2 qubits and then there is an interaction between them at each time step, like so. And you may apply different unitaries at each of these time steps, 2 qubit unitaries. Now, let us ask, what is the kind of things that we expect? The complexity is coming from this 2 qubit unitaries, clearly. So if these 2 qubit unitaries or these interactions are in some sense weak, then we would not expect a very complex state, whatever complex may mean, at the end of the day. So there is some sense of how much interacting, so to speak, these gates are. So that's one of the points of this talk that I would like to emphasize, that what actually characterizes this feature of the strength of interaction. Is there what is the strength of interaction? And the answer will be quite simple. It will be the entangling power of these gates. So the larger the entangling power is, we find, yeah.
I just want to ask you, are these unitaries same? That is, they are same you everywhere, or are they different at different points?
Here they seem to be also changing. You mean the single qubit unitary?
Yeah. Suppose I write a U single qubit. It is between between 2 leads. I have added a unitary. Let us say, call it U1. Let us say that is like a control knot or something. Are they same in all parts? Is what I
know. So here they're using 4 types of couplers.
Yeah.
These things. So like if you take these 2, they are having this green. So this A is what is acting, and so on. So there are 4 of them which are doing, but they are choosing randomly which 2 that are being acted on in this thing as it's going on. So these are these are actually, you can think of them as models of non-integrable quantum many-body systems, because these are, you can think of each of these qubits as a spin half particle or something like that, and the interaction is there between them. So they are non-integrable. They don't conserve. Mostly, they are not conserving anything, and they lead to typically these kind of mixing kind of systems. Although we have not defined what mixing is. And also they provide unitary K designs. Actually, in the talk of Professor Karol Szyszkowski, he defined T design. So this is precisely the K is used for T here. So how random, how close to being sampling on the Haar measure or uniform measure on the unitaries on this large space of 2 power n, if n is the number of qubits, is this full circuit here. So these provide unitary K design sampling from this. And so what we wish to do is specialize. We're not going to do random unitary circuits. We are going to consider very special kind of interactions. And what is special about it, actually, there's a history to this from at least 2016 that I know of, from these works, Classical Foundations of Many-Particle Quantum Chaos, Particle Time Duality in the Kick-Dicing Spin Chain. So you can see that the motivations actually come from Floquet forced, periodically forced many-body systems such as spin chains. But it was the essential solvability of it, I would say, was realized. What is the essential solvability behind it was realized perhaps in this paper for the first time. Exact correlation functions for dual unitary lattice models in 1+1 dimension. So the key word here is dual unitary, which I will now emphasize. So what is dual unitary? So just to, I'm going to do this in pictures. So just a little bit of background about the pictures themselves. So here is a unitary operator, and I'm going to consider bipartite because remember, like for example, in this circuit, all of these unitaries were bipartite. They are 2 qubit unitaries. Only thing is we don't want to restrict ourselves to qubits for a very good reason. So Q is the local dimension here. And so the dimension of this U is Q squared. So it's a Q squared dimensional matrix. And I keep interchanging things, but here is I alpha. Oh yeah, no, it's fine. So there is J beta you can consider as the leads which are going in. And this is the unitary operator is represented by this. And the output leads are I alpha. Okay, so there's a tensor network kind of representation. Adjoints are represented by this color, the same things. So for example, the identity that U adjoint is identity, that is U is unitary itself, which is represented by this equation here, will be represented by this circuit where we put U adjoint. So you read from bottom to top. Time, if you wish, as you're going from here, so U adjoint first and then U. So time is going like this. So here time is going up. So there is first U adjoint and then there is U. And then this thing is just a contraction. And so this multiplication is contraction of these symbols. And this is the output. And because this is identity, it just disappears. So I is equal to J and alpha equals beta. So this is identity. So this circuit or this picture here is representing the fact that these are unitary operators. Okay, so this is just the other way around. Now, if you have a many particle system, which are, or many qubits or many qubits, which are interacting by these local unitaries, by local, I mean now actually 2 qubit unitaries. So between 1 and 2, we have this. Between 3 and 4, we have maybe the same one, U3, 4, and so on. So we have 8 particles here. And there are these 4 things. So this is how it will be represented. But there is no interaction now between them. So now here is a fully interacting thing where in the next layer, we just layer this. So in the next layer, 2 and 3 are interacting, etc. So now it's a fully interacting system. And that you can consider to be your big unitary operator or Floquet operator. The dynamics is going to be given by the powers of this. So U power T. So let's consider dynamics of 2L particles on this. So it's a Floquet dynamics. It's a unitary operator on this. Or you can consider it as a circuit. It does not matter. But right now in this picture, as I've drawn it, I'm assuming that all the U's are the same. That's why I've written U tensor L. So all these U1, 2, U3, 4, etc. are the same. So now you have a many-body system. You would like to calculate things for it. So one of the main things is a Green's function like this, trace of U power t. And it's a hard task to calculate this. But now you can see now what is this picture? This picture is just telling you that here is U. So this is actually a picture for 3, I guess. So because this is one is U, and there is another U, and there is another U. So there are 3 here, and this will be contracted with this. This will be contracted with this, and then you can calculate the trace. If you apply periodic boundary conditions, you come to this. So you can calculate this diagram, then you would have calculated the Green's function trace U power t. Now let us just turn our sights and say that we are now going to consider this direction as space and this direction is time. So far this is time, this is where the qubits are, and this is time. But now we are going to change our viewpoint and consider this to be space and this to be time, because you see it's very much exactly the same kind of thing. 2 leads are coming in from here, 2 leads are coming in from here, 2 leads going out from here. But now it's a different operator, U tilde, and time and space will be interchanged. So U tilde to the power of L trace of this. So you see, this is now, it's like in quantum, in statistical mechanics, we do a transfer operator kind of thing. So this is somewhat like that. But the observation is that we have 2L particles. We have a propagator on these 2L particles, U. That is, this actually, you should look at this as this big U. And in time t, this is same as 2 t particles. In a propagator U tilde, time is L. So the position and time gets interchanged, and that is the space-time duality in this. When you're looking at this as a space-time, you can apply some kind of space-time duality. But typically this U tilde will be non-unitary. And in fact, there is very interesting non-unitary dynamics in that. But what we want to consider is a case when there is duality, in the sense that actually when you do this, U tilde is also unitary. So this is a case where you would call this dual unitary. So what is required? So let us just look again at this unitary operator written in this tensor form. What we are doing is interchanging the role of space and time. So this horizontal is space, if you wish, J and beta, and this is time here, this index here. So I and alpha are after the time, after one operation of U. So now just consider single two qubit unitary operator. Okay? So now if we interchange the role of space and time, what we are doing is this, what was originally here on the space axis now comes along the time. So there is I and J here, and what was originally on the time axis now is along the horizontal axis, alpha and beta. So in terms of just this matrix U, it's a very simple operation where it's a bipartite system. There are 2 particles now. You're just interchanging the, in this case, yeah, so I have interchanged beta and I. Okay, I have interchanged beta and I, whereas again I have made some kind of this thing. I would have liked to interchange J and alpha, which is what is being done here. Okay, so this is a realignment operation or a reshuffling operation. So it's slightly different from the partial transpose. Partial transpose, you do it on the same subsystem. You interchange I and J or alpha and beta. Here you interchange these 2 things. So that's called a realignment operation. And this realignment has a very easily provable thing that if you take a tensor product of 2 operators and then you realign it, it's simply a rank 1 object of this kind, where this A is this operator which is vectorized. You take this matrix, make it into one big vector by putting all the rows together in one column, and you get this vector A. This is a very useful identity. Now, this is simply the realignment operation. U will be called dual unitary if its realignment U is also unitary. Okay, so that is this identity holds. And in terms of a circuit, you can write it like this. But what does it really mean? It appears that there is a very simple, the motivation from the point of view of circuits was that we can actually calculate these Green's functions. But from the point of view of quantum information theory, the duality condition is has a very basic meaning. Dual unitaries have maximum operator entanglement. They maximize operator entanglement. So you take a unitary operator, you do a Schmidt decomposition of that, so that AI and BI are orthonormal operators, and these are the Schmidt numbers. And there's I'm sorry, again, here I think I'm interchanging Q and N. So N is the same as a local dimension there. And so that's this. So now if you take this realignment operation as I've written it, as I told you, this AI, BI will just become this operation here. I'm sorry, AI, BI, and this will be UR to a joint. So the realignment operation. And you can see that that's the eigenvalues of this combination gives you, in fact, the Schmidt numbers of this unitary operator U. So the entanglement properties of U are determined by the realignment. So that's actually the meaning of the realignment. And it's easy to see then that if the realignment is unitary, then it leads to maximum entanglement, in which case all these lambda i's would be equal. So just as a maximally entangled state. So you can define a linear entropy of this unitary operator's entanglement, capital E of U is an operator entanglement, based on the Schmidt numbers. Okay, so this is now a measure of how entangled this unitary operator U is, and it is maximized if this operator U is the swap operator. So the swap operator is the maximum entangled operator, one of an example of a maximally entangled operator. There are many more, and that's equal to 1 minus 1 by n squared. So that's the maximum allowed. So dual unitary operators, which are useful in a many-body context, have a simple interpretation from a quantum information point of view. They maximize operator entanglement. Now, I want to introduce two other quantities before going on. There is entangling power and gate typicality. So now you should, excuse me, I'm going back to local dimension Q. And this, now consider just a bipartite unitary U here. Entangling power was defined by Zanardi maybe 20 years ago. You take this unitary operator, act it on product states. You get an entangled state. You find out what is a linear entropy of that state. And then you average out this linear entropy or all possible product states. This one defines as an entangling power of this unitary operator. Okay, so it gives you some idea of how entangling this gate is. For example, a swap gate would do nothing. It would just interchange these two, and it still is unentangled, and therefore the entangling power of swap gate is 0. But we know that the operator entanglement is maximum. So this is an interesting thing which is also known for a long time, that the entangling power can be written in terms of the operator entanglements of this unitary operator U and U times swap. So S is a swap operator, U times swap. Okay, so these two quantities will play an important role in our understanding of these circuits, E of U and E of US. So in fact, there is another quantity which is complementary to the entangling power, which we call gate typicality, which, as you can see, is just interchanging the signs of these two terms here. E of U minus E of US plus E of S. The fact that the entangling power of swap is 0, the gate typicality, on the other hand, is maximum for the entangling power, for the swap gate. So these are kind of complementary things. If you wish, you can think that there are two quantities, E of U and E of US, which is characterizing properties of this unitary operator. And these, we are defining two new quantities by just linear combinations, this entangling power and gate typicality. And both of them have a range of 0 to 1 according to our choice of normalizations or factors. Now we can ask, what are those gates U which maximize entangling power? Not just operator entanglement. So they clearly have to maximize both this E of U and they have to maximize this E of US. So this E of U is maximum for dual operators. But what are those operators which also maximize this E of US? Now it's quite simple to see that E of U is related, as I said, to the realignment. E of US is unsurprisingly related to partial transpose of this. So it tells you this is the entanglement in E of U in US. Okay, so this is the operator entanglement of US, and that is given by this, where this partial transpose of the unitary operator plays an important role. And therefore, you maximize entangling power if E of US is equal to E of S, that is the swap, and that's equal to this. So this is true if and only if the unitary operator is such that U partial transpose is also unitary, or US is maximally entangled. So not only should it be a dual unitary, but it should also, in addition to that, be such that U partial transpose is unitary. Okay, so to summarize, this entangling power is 1. That's the maximum possible. If and only if the unitary operator U and its two rearrangements, this realignment and partial transpose, are all unitary. And this is a case where U is also called a perfect tensor. So let me now give you some idea of how these quantities behave for typical gates or unitary operators for, let's say, qubits. Okay. So we take the space of all qubits, all two qubit gates or unitaries, and we calculate their entangling power, place it here, gate typicality, and place it here, and all of them lie in this region, okay, bounded by these two straight lines here, and this vertical line, and this curve, which is a parabola. Okay, so all of them lie in the shaded area. For example, C0 is here, DC0 is here. Local gates or identity will be here. Entangling power is 0. Gate typicality is 0. The swap is here. Entangling power is 0. Gate typicality is maximum possible. Okay. Now, this line here are the dual unitary lines. This is the line where E of U is maximum. Operator entanglement is maximum. This is the gate. This is the line where the partial transpose is unitary. Okay, so that's not got any name. We called it T dual. Okay. Now you see that actually there is no case where this line meets this line. So this unitary, this dual operator cannot be such that its partial transpose is unitary for qubits. So this is a well-known fact that there exists no such operators for qubits. So there are no operators for qubits, two qubit systems, that is, where the unitary U, UR2 and UT2 are all unitary. This is related to the fact that there are no 4 qubits that are absolutely maximally entangled, a fact which is known for now a long time. Now, if we look at qubits, local dimension 3, it's a very different and interesting space which we only partially understand. And you see all these colors, you can ignore it, but it's just it's telling you various types of gates which are there. Again, it's bounded by these two lines and a parabola, but unlike the case of qubits, it's not cut off like this. They actually meet at one point, and this point is where there is a perfect tensor, or there are unitary operators such that both partial transpose and realignment are both unitary, or there are perfect tensors out here. Okay. So this is the case for, we have shown, and well, it was not known whether such is the case for all dimensions except 6. Now we know that for 6 also there exists such a thing. So this is from a paper with Bhargavi, Prabha, and Carol last year, if you want to see details of it. Now I come back to these circuits and ask, what is the use of all of these things on circuits, and what does it imply for these circuits? So we are going to now put these unitary operators, two qubit unitary operators, into these circuits and ask about the correlation functions and how they decay. And what does that have to do with these entangling powers and so on. So that's the idea. So if you stay with me, so we defined a correlation function in the first or second slide, classical correlation function. This is a corresponding quantum one. So there are two local operators, AJX and AIY at position X and Y. And let's evolve one of them with time. Let's say AIY. This one here is evolving with time, and then this is a correlation function. It's overlapped with AJX, this operator here, after a time t. So this is Heisenberg evolution operator, and the trace of that. So this is the equivalent of the correlation function. Okay. And we want to be able to evaluate such correlation functions and ask how they are changing with time, which is a very hard problem for any of these unitary operators U. But there is a great simplification if we assume that these operators are dual unitary operators. That is, they have maximum entangling power. Then there is a great simplification and we can calculate this correlation function. It has been shown in that paper 2019 that all correlation functions vanish except those in a light cone, that is a line which is joining these two operators in the space-time thing. So here is space and that is time. So this is the light cone, and this is the only correlation which is non-vanishing. Everywhere inside it is vanishing. Of course, outside it will vanish. So so between these two local operators, this correlation exists and is given by this diagram. So we just have to evaluate this diagram. And quite interestingly, this diagram, you can see a fractal or a self-similar structure, so that you can write this as a map on a single qubit, this single qubit map with a single qubit, okay, which is taken to the power of time, 2 to the t, multiplied by A alpha. So this can be calculated exactly based on a CPTP map. So this is the map, m plus acting to the power of 2t. This is the local operator A beta, the one which was initially there. And now we take this map n plus to the power of 2t, and then we get some other single qubit operator, and we find the correlation between these two. So now you see it reduces to properties of CPTP maps, and these are not any CPTP maps. They are derived from these unitary operators which are making up these circuits. Exactly how are they related? So this m plus alone, let me concentrate for the lack of time. So this m plus is given by this is given by this expression, or the Liouvillean operator or the super operator corresponding to that is given by this. So this is a CPTP map. So this is a realignment of a positive operator. So what is there inside would be called dynamical matrix, following the works of Sudarshan, Matthews, and Rao. So this is actually just, this positive matrix is a very explicit structure in terms of the partial transpose. Remember that we are assuming that already it is a dual or unitary, which means that U realignment is already unitary. So that doesn't enter the picture. So this map is completely determined by the properties of the partial transpose of the unitary operator. Okay, so this is, so we have to find out the properties of this channel, given that it's maximally entangled, and this is the channel. So this is the problem at the end of it, and this determines the mixing properties of this entire many-body circuit. So the eigenvalues of this map, let's call this lambda j, let's denote this lambda j. This plus minus, you can ignore the plus minus, it's for the other direction. So you can just keep plus inside. And all of them, there are q square minus one of them. I'm sorry, there are q square of them. One of them is trivial. that corresponds to 1. The map is the map is unital, and that just corresponds to the case when A beta is identity. Okay, so so that's a trivial eigenvalue, if you wish, or the and the non-trivial eigenvalues all lie on the circle or inside the circle, unit circle. Okay, so they determine how mixing the circuit is. So what you may think about an open system as relaxation, here we will consider it as mixing rates. That's all. So it's a matter of terminology maybe. And these correlation functions can be explicitly given on the light cone as this expression here. So you can see that it's lambda j plus minus to the power of 2t. And therefore, as long as lambda j is not equal to 1, this is denoting an exponential decay. And therefore, the system will be mixing in that sense of the ergodic hierarchy, which I talked about. So as long as all the non-trivial eigenvalues are less than 1, you would call such a circuit a mixing circuit. So the ergodic classification of such dual unitary circuits are in terms of the eigenvalues of this map. So non-interacting, that is, all of these non-trivial eigenvalues are exactly equal to 1. This is the case when actually, for example, the unitary operator in question is the swap operator. This would be a non-interacting system. The correlations remain constant in all modes and the system is non-interacting. Non-ergodic, interacting but non-integrable, non-trivial eigenvalues are equal to 1. And the correlations in the K mode. So there are some bunch of modes which are whose non-trivial eigenvalues are equal to 1. So ergodic is all the lambda k not equal to 1, but there exists at least one eigenvalue with modulus 1. In that case, you can show that the average is equal to 0. So this would be ergodic, but non-mixing because some eigenvalue is equal to 1. Modulus is equal to 1. So it's not mixing. Ergodic and mixing if all the eigenvalues, non-trivial eigenvalues, are smaller than 1, the correlations decay exponentially. And
10 minutes, Arun.
10 minutes? Yeah.
Yes.
Thanks. So Bernoulli systems are, so this is fine so far, but in fact there are even Bernoulli circuits in this high level of mixing. So for Bernoulli circuits, all the non-trivial eigenvalues are equal to 0. So there's only one trivial eigenvalue and that's equal to 1. Everything else exactly vanishes, in which case the correlations of any space-time separated observables vanish. And the correlations decay instantly. That's why we call this Bernoulli. In this case, these channels are completely depolarizing channels. So what characterizes a Bernoulli circuit? So now you see this map is completely determined by the partial transpose. And therefore, if this partial transpose itself is identity, you partial transpose this one is identity, then this is a completely depolarizing channel. Identity's realignment will give you a maximally entangled state, which determines a completely depolarizing channel. So, so that is in fact this case when the partial transpose is also unitary. So then these kind of contractions happen in these diagrams. It implies that the circuit channels are totally depolarizing, as I said, and the circuit is then a Bernoulli circuit. So there, since we know that there exists no 2-qubit gates which are such that both its partial transpose and realignment are unitary, we cannot have qubit circuits which are Bernoulli, but we can have qubit circuits which are Bernoulli. So it kind of tells us that already qubit or spin half systems are in some sense less ergodic or cannot reach the apex of an ergodic hierarchy that a spin 1 system can. Okay, so we have proved certain things. I just want to mention that these two unitary circuits, actually this two unitary is a terminology introduced by Carroll and co-workers for those unitaries such that both realignment and partial transpose are unitary. And in fact, one can define multi-unitary operators. The two unitary circuits which are constructed out of two unitaries are Bernoulli. And what is interesting is not only do single particle observables based on single sites decorrelate, even two operators whose support is on two sides, they also decorrelate instantly, but not with 3 and above. Okay, so this can be seen, which is not a property of dual operators, for example. But if they are Bernoulli, then two particle observables, which are a much larger class of observables, would also decorrelate. So it tells us that there is a large degree of non-integrability in the system. Okay, so to summarize, there is a kind of rudimentary phase diagram that one may draw. And here the order parameter, or the one with not order parameter, actually control parameter of such a thing is the entangling power of these two qubit operators which are constructing this large circuit. So that is this entangling power. So as a function of entangling power, zero entangling power is a swap, that's non-mixing. For the case of qubits, as we said, this entangling power cannot be maximum, cannot be 1. It can go only up to 2/3, which is for a C0 or a DC0 gate. Actually, for a DC0. C0 is not a dual unitary gate. Now, that is the maximum, and all of these interior ones, they can be mixing in the sense that you can always find local unitary operators on which are having the same unitary, which are having the same entangling power such that it's mixing. So along this, you can have mixing. So actually, dual unitary operators, because they have very large operator entanglement, do have a fair bit of ergodic property. They are mixing. But if you go beyond qubits to qubits, there is more to life. And this entangling power, if it is larger than this EP star, and by the way, this EP star has a very simple expression in terms of local dimension Q, it's there in our paper, then between that and 1, the circuit is guaranteed to be mixing. Always it's mixing. Whatever may be your local fields here, it will always be mixing. So there is, if you wish here, it guarantees mixing. And if EP is equal to 1, it's in fact more strongly Bernoulli. So there is some kind of a quantum ergodic apex or quantum ergodic hierarchy, which is there. Okay, so I've talked about these circuits, dual unitary operators, two unitary operators, etc. But how do you make them? How do you construct them? So there are, in our paper, which became rather long, we have various methods, block diagonal construction, swap combinations based on designs like orthogonal Latin squares, or on maps, cat maps, Fourier transforms, Hadamard maps, and so on. There's also a numerical procedure, an algorithm, which we published here, and which we understand somewhat better now, which allows us to construct actually ensembles of dual unitary operators, as well as maximally entangling, that is, entangling power is equal to 1 unitary operators. And these are based on nonlinear maps on this. But coming back to qubits, there is actually only for the case of qubits, the dual unitary operators are well understood. They are given by the simple characterization of this. So any dual unitary operator will be locally equivalent to this. So you see there's only one parameter J. These things are pi/4s on each of these. And depending on, so if J is equal to pi/4, this is swap, which is also a dual unitary operator. If J is equal to 0, it's a DC0, and this entangling power is given by this. So J equal to 0 gives you the maximum entangling power. J is pi/4, 0. Okay. Then we have shown that any swap multiplied by block diagonal unitaries is also dual unitary, and we can calculate the entangling power of such unitaries depending on the number of blocks. But these are limited. You cannot go till entangling power equal to 1. You can go till entangling power equal to 1 by some other special methods. You can look at operators which are sort of generalizations of Fourier operators. I will not go into details here. This is what we call a cat map, for example, a quantization of a symplectic symplectic operator in 4-dimensional phase space. Okay, so just very, I think I will touch upon some aspects here finally. So what I've talked about is some fixed unitary U, which is constructing the circuit. But what happens if we take this unitary U, which is constructing a circuit, but construct now a new circuit U prime in which there are local unitary operators acting? Okay. Nothing changes with respect to these operator entanglements because they are local or entangling power. Nothing changes. But actually, it does change the circuit properties because this map is not invariant. This CPTP map is not invariant. These eigenvalues are not the same. So the many-body system is different, and that is of course to be expected. You have local fields which are affecting the dynamics of it, and it's interesting to study these CPTP maps and the effect of these local operators on the CPTP maps, especially the largest eigenvalue, which determines the mixing rate, and the smallest. So I don't have time to go into this, but you can look at our papers, and what turns out to be the case is that the unitary operators, the local unitary operators here, if you do an average over them, then one can say a lot about the mixing properties of the circuit. And the mixing property is then determined almost exclusively by this entangling power. Okay, so, but maybe here, let me just try to explain this particular picture because it does show something here. So this is constructed out of dual unitary operators which are diagonal. So that means there's just faces here multiplied by swap. And these faces can be taken as any random face. Okay, so let's take Q equals 3, which means the 9 by 9 matrix. The maximum entangling power allowed is 3 by 4 by this. And you can see here, if we take an operator U, this U here, whose operator entanglement is rather small, 0.098. And we find the largest eigenvalue, lambda 1, which is blue color, smallest eigenvalue, which is red color. And these eigenvalues now are coming from different local unitaries. Okay, so we take the local unitaries over some Haar measure and we do this. And we also plot a circle of radius square root of 1 minus the entangling power of this loop. So you can see that actually the largest eigenvalue, so this lambda 1, is essentially determined by this square root of 1 minus EP of U. And also this largest eigenvalue decreases as this entangling power increases. So this is the largest. You can see it has now come down, which means that the circuit is getting more mixed. I mean, it's mixing more. And a Bernoulli would be such that all the eigenvalues are right at the center. Okay, I think I will stop here because time has run out. But we can do analytical, we can show to a large extent by using random matrix theory that indeed the entangling power of these two local gates determine to a large extent this many-body thing. So this is going back to the very first thing about this Google circuit, where I motivated that, in fact, the entangling power between these things have to play an important role in how this thing is, the mixing properties of that entire circuit. I don't know whether one has looked at those circuits from this point of view, but this certainly indicates that that's the case. For qubits, one can actually solve things analytically fully. For qubits, there are some approximations and so on. So, but let me end this. There are necessary and sufficient conditions, so we show for mixing. But I'll summarize. So what we've done is define Bernoulli circuits, which are constructed from two unitaries as a apex of ergodic quantum hierarchy. The entangling power of two particle building block unitaries constructs the hierarchy. So that's what is interesting about this. And for an entangling power greater than some critical entangling power, the circuit is definitely mixing. That means that there are no locals which will make it non-mixing. And if it is equal to 1, it is Bernoulli, and that is completely independent of locals. So the locals cannot change this character that it's Bernoulli. And the local average spectral gap, average mixing rates are universal functions of this entangling power for Q greater than 2. And this is what we have shown, that the average of the largest eigenvalue of the CPTP map is given by the operator entanglement, by this simple relation. So there has been some recent work, but it's interesting to look at non-dual circuits, finite circuits for time. So basically we are looking at long time behaviors. This is connections with standard quantum chaos measures, also with things like OTOCs, and physical models of Bernoulli circuits. Because for qubits, we know Bernoulli circuits don't exist. So we'll have to look at spin 1. So thank you for your attention. Thank you.
Thanks, Arul. So there is not enough time for questions. Any short comments or questions from the audience? I have a comment. I had come across some duality algorithms in quantum circuits where they take two unitaries again. It amounts to adding the unitaries in the end of the circuit, and people had simulated a PT symmetric system at the end of such duality algorithm. So I think this is very different from what that talks about.
Yeah.
So that is one thing. So there it is something like U1 and U2 are two unitaries where they get an output as U1 and U1 plus U2 acting on the system, which is not non-unitary evolution. In open systems that can be achieved, but this is very different.
This is different, yeah. Although here also the dual can be non-unitary. It's only a special which is not.
Yeah. So thank you once again, Arul. So
thank you.
We will,
Thanks everyone.
So next speaker, the last speaker of this session is another friend, Aditi. So Aditi, you can try sharing your screen now. I will, Aditi?
Yes, I'm here.
Yeah, okay.
Okay,
So
my also screen sharing is not.
Oh.
Get out, get in. That's what I did.
Yes.
And I think they have to enable.
We are now experienced with.
Okay. Now I can share the screen.
Okay, good. So let me just give a brief. Aditi doesn't need any introduction, but I will try to just as a formality. So Aditi is a professor at HRI, and along with Ujjwal Arunpati, she works in the quantum information and computation group. I think this is one of the biggest group with 15 PhD students and 5 postdoctoral fellows. So she had done her doctoral work at University of Dansk, and then she was a postdoctoral fellow and also had a little that is worked as a faculty at Barcelona, I think, before she joined Jawaharlal Nehru University, Delhi, and then she moved to HRI. And Aditi, all of us, many of us know here, she was awarded the Shanti Swarup Bhatnagar Prize for Science and Technology for her contributions to physical sciences in 2018. She is the first woman physicist to be given this honor. I am very happy to introduce her and ask her to take the stage for giving a talk on quantum thermal machines.
Thank you.
Good to see you.
It's nice to see all of you here in this platform, and thank you for nice introduction. It's really a pleasure to talk here, and I thank organizers and Shubhashish for inviting me and give this platform to present some of our recent works on quantum thermal machines. So the work will be based on actually some couple of papers which we have written in last 2 years. And as you can see, and if you are interested, you can also send me an email if you have any queries which you cannot ask during this talk. So these are my collaborators with whom I perform this, the results that I am going to talk. So Srijan Ganesh Tanai are currently PhD student of mine. Pitash was a PhD student and now in Italy doing postdocs. Shiladitya was a postdoc at HRI, now at Taiwan. Amit is a faculty at IIT Palakkad. So this will be more or less the outline of my talk. So the first question probably can come up in our mind that why should we study thermal machines? Because, okay, thermal machines means quantum heat engines, batteries, refrigerator, etc. I will try to show you some motivations, and it actually lead to an interesting subjects or the development of quantum thermodynamics. I will specifically talk about two thermal machines. One is quantum battery, another is quantum refrigerator. So I will tell you what are quantum batteries, and I will show you that they are robust against impurities or against decoherence. I will also show that they can give some dimensional advantage. And finally, also I will talk about very recent work where we are able to design quantum batteries with ultra cold atoms, which can be actually realized in laboratories. If I get time, then I will also talk about a recent work on designing quantum refrigerator, which can also be shown to be robust against disorder. And finally, I summarize. So let's start with the motivation that why we want to build quantum thermal machine. Now, in the subject of thermodynamics, one of the main goals is to study, investigate heat engines and thermodynamic processes. And as we know from around 1824 by Carnot, who and other scientists around this 24 to 40, they found a limit on the efficiency of these machines when the process happens like heat into work. And this is for the ideal machine. And of course, there are modifications were done in a real scenario. So as nicely written in this Mehelar and other collaborators paper, that a classical thermodynamic machine consists of a working medium, which can be gas, typically enclosed in a cylinder with a movable piston. Now, with the miniaturizations of devices, there is an important issue which now comes into the picture, that is formulations of fundamental thermodynamical principles and bound, which will be valid in the microscopic level as well as nanoscale levels. And what it was shown in last few years that it is possible. I mean, it is indeed possible. And so there are several works going on. So they, what we understand from this development is that they may differ from classical ones, but the hope is that they converge in the macroscopic limit, the known thermodynamics, thermodynamical bounds and principles. So the probably one of the oldest work was by in this PRL paper in 1959, and the beautiful book of Mehelar and others. You can look on quantum thermodynamics. So this is one of the first proposal to my knowledge where the 3-level measures are used as heat engines. As nicely written in the introduction, that there is a difference between the heat engines which we prepare by quantum mechanical systems and the normal classical systems. And after this initial work, several models were proposed. Harmonic oscillators are used, spin chains, molecular devices, 3-level systems. all are used to devise heat machines or refrigerator and so on. So, for example, in this work in 2007, again by this Henrik Mehelar and Michel, they actually propose a machine, or they give a design of a machine, which actually initially you have a 3-spin chain where spin 1 and spin 3 are connected respectively to hot and cold bath. And spin 2 is a working gas by deformation of its spectrum. And they show that this machine actually performs Carnot type cycle and is able to work as a heat pump or engine. And this machine depends on the temperature difference of the bath and the energy difference in the spin system. Now, there are a lot of debates that are going on in this respect. First is one of the prominent, or these are probably two prominent ones in my opinion. One is a violation of second law of thermodynamics. Another is whether if we build quantum machines, whether we can get efficiency, which is more than the Carnot's efficiency, that is the ideal classical engine can provide. And more or less both of them were resolved in a sense that there is no violation, so you will not get efficiency more than Carnot efficiency by using Maxwell's demon and etc. So there are, as I said, the work by 59. After that, around 70s and 80s, a lot of work has been done. But in recent last 20 years, a huge amount of works have been done in the development of quantum thermodynamics. And apart from that, developing the principles of thermodynamics in a quantum regime, people also, with the development of quantum technologies, people are trying to build some quantum thermal machines which can be realized in laboratories, for example. So two prominent ones are quantum batteries and quantum refrigerator in last 10 years. So I will talk about these two machineries. So what are quantum batteries? So as we know, in the classical battery that we use in many devices, including when I am talking in a laptop, which also requires battery. So a battery is a device which consisting of one or more electrochemical cells, and we usually charge it via some electrical devices, and it converts chemical energy directly to electrical energy, and energy can be extracted whenever we require. On the other hand, the question that people have asked, if we want to build like other technological, other quantum devices or quantum technologies, can quantum mechanical systems help in storing energy? That means and that energy can be extracted whenever we require, just like a batteries. And it was shown in this beautiful paper by Alichki and Fanes that it is indeed possible. So they took a d-dimensional quantum system with non-degenerate energy levels like this, and this is the Hamiltonian. And they show that work can be reversibly extracted or can be stored via cyclic entangling unitary operator. And this work was defined like that. So this is the Hamiltonian of the unitary evolution, and you have to minimize, and this is also known as ergotropy. So the two prominent designs of quantum batteries, which now are known in this literature. The first design was similar to Alichki. So there are array of two-dimensional system, and then you charge via global unitary operator. So this is the design that was proposed in PRL paper in 2018 by Solid State Systems. And there is a design too, where actually the initial state will be the entangled state, and that will act as a battery, and then one charges the battery by using a local unitary operator. So there are two designs which are known now, and I will mainly concentrate on the second design or the second procedure. So this was actually developed first. There was a proposal by spin chain model of a many-body quantum battery by Kavan Modi Polak in 2018. Their model is a slightly different model than the one we propose in 2020, and this is, as I have said, that we actually, instead of a product state, we start with the entangled state as a initial state of the battery. And so interacting spin-half model can be a potential candidate for building a quantum battery. And that is exactly the proposal in these two papers. So the first, before I give the how we implement quantum battery, so the why we choose spin chain for building quantum battery. So we know that the spin chains typically poses a rich phase diagram, which may help to design some quantum technology that we know from the literature. That so it usually shows quantum phase transitions, rich thermal property, out of equilibrium physics, and so on. We know that, for example, based on a spin model, so using the dynamics of Ising spin chain with a suitable initial state, we can prepare cluster state, and then via single qubit measurements, we can implement universal quantum gates with unit fidelity. And this is the one-way quantum computer or measurement-based quantum computer. And for example, we can show that this measurement-based quantum computer is also robust against disorder. This is our very old work where we show, although the fidelity of the gates reduced. We know that a spin chain can also be used for quantum state transmission. So for example, this is a proposal long back where initially the spin chain can be in its ground state in an external magnetic field, and Alice wants to send some information to Bob, as in the teleportation or the any transmission protocol. Here Alice wants to send some spin to Bob, and so Alice is situated in one end of the chain, Bob is situated another end. Alice places the quantum state that she wants to communicate near to the spin chain, and then it starts evolving, and Bob receives the state with some fidelity on the spin nearest to him. So, and one has to see that how what biggest chain or the length of the chain, and if it is disordered chain and so on. So there are a lot of studies in last 10, 15 years. Moreover, spin chains can be realized in ultra-cold atoms in optical lattices. It can be realized in trapped ions, and these are two nice review articles on trapped ions and polar molecules. So they are also the potential candidates for implementing spin models that I will discuss for building quantum batteries. These are the realizations which are reported. So for example, the photons, by using photons, there was a frustrated Heisenberg spin model, and recent time they have also realized Ising spin chain. As I said, it's quite naturally you can realize spin models in ion traps, and they report creation of a long-lived multipartite entangled states. And as far as I know, the coherence time was 1.1 second, which is one of the probably the highest coherence time in recent time. And also in polar molecules, by which they have shown that they can also create multipartite entangled states, and along with they can create the spin, realize the spin models. So with that motivations in hand, we are tempted to propose spin chain as quantum battery, as I have said. So interacting spin-up model act as a battery, which consists of two parts. One is the magnetic field part. So this is the field part, and this is the interaction part. So here you see this is the XYZ model. And here gamma is an isotropy parameter, J is the coupling strength, and delta is also the coupling strength. And H is the magnetic field strength. Now, suppose a ground state or thermal states thermal state of this Hamiltonian acts as the initial state of a quantum battery, and then we use local magnetic field to charge the battery, as shown in this schematic. So total output, work output of the quantum battery can be defined in this scenario when you have a unitary dynamics, and the average power will be the maximizations over T WT by T. Now, as I said, this initial state will be the ground state or the thermal state of this spin model. And for charging, we actually choose a local magnetic field in the X direction. And with this, we can show that when the interaction is on, then the battery, the power that we can extract or stored in this quantum battery is higher than the model without interaction. And the different lines are for different anisotropy parameter in this XY model. In this plot, delta is put to be 0. So this is just a XY model with a transverse magnetic field. So from this plot, the message that we get is that the XX model turns out to be the best among all the XY model, all the class of XY models. So gamma equal to 0, which is the XX model, can store more energy or more power, can give more power than the other XY model. Even if you turn on delta, we can still show that there will be power will be more compared to the model which has no interaction. So so this is independent whether you have delta or not. Now I will show that in a real experiment, actually, there will be impurities in the model, or there can be a decoherence. And this kind of battery will be robust against both. So, so one of the interaction strengths depends on site. So that is what I mean by disorder. And so you see that now the interaction strength, say JJ, this coupling depends on J. So J is a site index, here also delta J. In our case, we put either the coupling in front of XY Now, of course, when we talk about disorder system, we should also look at this year Nobel Prize, where you know that the Giorgio Parisi got the Nobel Prize because of the discovery of the interplay of disorder and fluctuations in physical systems. So these systems are, apart from the technological impact, these systems are, or they're dealing with the systems or properties of the systems are reached. And so they are interesting on their own. So here, how to compute power in this disordered system. So typically we consider quenched averaging. So quenched averaging is such that you first compute the power of the battery for each realizations of randomly distributed interaction strength. So one of the, say, delta J is random. So delta J will be chosen from the Gaussian distributions with mean, say, delta and standard deviation sigma. And then we have to choose several times. So we have to perform averaging over all such realization. And such method is known as quench averaging. And this was done because here we assume the change of disorder in parameters under study remains almost fixed for certain times, and so are much longer durations than that of the evolution of the system. And so it is like behaves like a glass. So in this scenario, one can show that the average power, which is here, as I said, JJ actually site independent. So they are staying for all the sites. and delta J depend on site even when we do that. And for different sigma value, that is different standard deviation of the random distribution. So sigma delta equal to 0 means this is the ordered case that I have already reported. And different sigma means this is the disorder strength. So when we increase sigma, that is the disorder is increasing in the system. And as you see that once we increase the disorder and we perform quench averaging for certain value of gamma, we actually get more power than that of the ordered system. So typically the people believe that when you put disorder in the system, then the physical property should reduce. But there are counter examples already reported before where the people have shown that the magnetizations, classical correlators, entanglement, they can be enhanced by introducing disorder. These are the disorder enhanced order, it is called. And here we see that even in case of quantum battery, the power can be enhanced by introducing disorder in the system. So now I move to the another scenario where the quantum battery is under decoherence. So this is much more realistic scenario if you want to think about the implementation. So again the battery Hamiltonian is this interacting Hamiltonian. So this is the XY model in a transverse magnetic field. And the charging is done when each of the spin is attached to a local bosonic reservoir, which can act as an absorption channel, and they supply energy to the system. On the other hand, discharging is done. So we first do the charging when the process is, when the state reaches to steady state, we start the discharging process, where again the quantum battery is attached to the local bosonic reservoir. And these reservoirs actually helps to extract energy from the battery. And moreover, each spin of the quantum battery can be exposed to the noise, which are dephasing noise. And here we consider this phase flip and bit flip noise. Again, the noises are locally acting on each of the spins. So for this, actually, instead of unitary dynamics, now we have to do a dynamical evolution of quantum battery via Lindbladian or via master equation. And so suppose I start with a thermal or ground state of the battery, and then I evolve via master equations, where the Lindbladian in the weak coupling limit look like that. And these are the gammas. Now the figure for it will be the ergotropy, because the energy stored and energy extractions can be different, and so this will be the definitions of the performance of the battery. And what we show analytically, that in the transient regime and in case of local phase flip channel, the transverse Ising model based quantum battery gives more power than the battery without influence of noise. And similar results can be obtained for bit flip. And if we compare bit, show analytically that that bit flip noise actually gives more power than the phase flip noise. Now, important to note, both the results you see that this is the charging process, this is the discharging process. The sub-indexes or subscripts of this denote the fact that 0 means there is no noise, 1 means single qubit of the battery is affected by noise, 4 means the 4 qubits of the battery are affected by noise. And in all these scenarios, you see that the transient regime, actually the noise helps to store the power of the battery. So the yellow one, where all the 4 qubits are affected by the battery, by the noise, then we get more power to be stored. And similar situations we get for the discharging. So more noise gives more ergotropy in the transient regime for the Markovian noise. Now we move to the non-Markovian noise. So here now dephasing channel is time dependent, and here we consider a ohmic spectral density, and this is now the dephasing channel, and here varying S we can move from the Markovian noise to non-Markovian one. And we see that in non-Markovian noise, this scenario, where actually the not only in the transient regime, but the entire regime noise helps to store as well as quickly discharge the power. So this is the plot of ergotropy for non-Markovian noise with S value, I think 3. So this is clearly we can see the difference between Markovian and non-Markovian noise, because Markovian noise only the noise help in the transient regime, while in case of non-Markovian noise, it helps in both the regimes, steady state as well as transient regime. Now I move to the dimensional advantage. So up to now, or in most of the studies in the literature, the systems considered are qubits, that means spin half particles. Now, what about spin J? So if we increase the spin quantum number, what will happen? So typically it is believed that with the increase of dimension or with the increase of the quantum number, the quantum nature will be lost. And so we can expect that the storage capacity of the battery can be reduced. However, there are some interesting work long back. For example, in the work in this two very important papers in quantum informations, where people have shown that if Bell inequalities violations doesn't diminish even when the spin becomes arbitrary direct. And interestingly, it was also shown that maximal violations of Bell inequality for arbitrary large spin. So this work, along with these results, where it was shown that the security of quantum key distribution increases with the dimension, or in the quantum communications can give some advantage in high dimensions or in a quantum switch. These all the results actually give us a hope that with the dimension, with the increase of the spin quantum number, the performance of the quantum battery may increase. And this is indeed the case. Because if I now consider a battery of this form, where A's are the spin matrices, so when K is 2, that means when the S is 2 dimension, then it is Pauli spin matrices. And here the charging Hamiltonian is same, but these are the arbitrary spin matrices. And again, the battery is prepared in the ground state of the Hamiltonian. And we can show analytically that if the initial state of the battery is a ground state of spin 1 transverse XX model, then the maximum average power of the battery is higher than that of the XS model with spin half particles. Here there is one thing that this result or the advantage can be obtained for higher spins only when the interaction strength between the sites is big. Now, this is the analytical result for comparing spin 1 and spin half. And then we show that for any other J values, for example, up to J equal to 3, we show clearly that this red line is for spin half and all the other lines for other J value. And as you see that as you increase, so the dotted lines are for the integer spins and the solid lines are for the half integer spins. And you see that the dotted lines are also kind of moving towards left, but giving more power in the initial transient regime. And here we actually plot the Pmax. So we optimize over T. So this is clearly the power increases with the dimension, provided the coupling between the particles are weak. So here I have only presented this for the XY model, but we have shown that this advantage persists for other spin model like bilinear biquadratic model. And interestingly, this spin 1 or higher spin model has a much richer phase diagram like Halden phase, etc. And we show that this the performance of the battery depends on the phase on which you are starting, or you take the initial state of the battery. But this I am not presenting due to the time. Another interesting move can be that up to now, all the models that I have talked about our work and the work previously done by in the which I call the design 1 of the battery, the individual system is fixed at space. So they are distinguishable via the lattice points. Now, suppose I go beyond that. Now I create, or I want to build quantum battery with indistinguishable systems. In particular, we now consider the initial state of the battery is a ground state or thermal state of one-dimensional Hubbard-Hamiltonian. So as you know, this is the Fermi-Hubbard model, and Jij are the tunneling term, and U is the on-site interaction. So this is the lattice sites, and each are occupied by some bosons or fermions. So these are now the initial state will be the ground state or thermal state of the Fermi or Bose-Hubbard model. Now, considering this system has, of course, one advantage is that currently it is possible to realize in the laboratories, in several laboratories around the world. At the same time, this scenario, this picture can help us to somehow see the trade-off relations between the battery made up by bosons and fermions. And this is the charging Hamiltonian. So on-site interactions are used to charge the battery, this battery. And again, we are able to prove analytically that if you have a lattice with two sites occupied by two particles, then this average work output for Bose-Hubbard and Fermi-Hubbard model coincides. You can see clearly that this is the work. And if this UCB, the strength of the on-site interactions and the tunneling terms of fermions and bosons are same, then they give the same work output or the power. Now, if we go beyond two lattice sites, if you have a three lattice sites and filled with three fermions or bosons, then we can show that in the absence of on-site interactions of the battery Hamiltonian, that means that the battery Hamiltonian doesn't have this term, we only have the tunneling term, and we use this on-site interaction to charge the battery, then we can show that the fermionic battery is better than the bosonic one. Because as you see that the difference is a 1 minus a cosine function, and so clearly it is a positive number. Now the question is, this is for 2 and 3 sites, which we can do analytically. Things become much more complicated if we go beyond this. So the next question is, if we increase the lattice sites, what will be the whether fermionic batteries still perform better than the bosonic ones. And this is actually the power of fermions and bosons with different lattice sites. Here, number of sites is equal to number of particles. So for example, if we consider 7 sites, that means it will have 7 particles. Now here we should remember, since it's talking about bosons and fermions, so bosons can sit in one lattice site. I mean, 7 can sit in one lattice site, right? To avoid that, we actually put here the assumptions to draw this figure, that in the Bose-Hubbard model, we consider that at most 2 bosons per sites are allowed. And with that, we got this figure. And then to compare bosons and fermions, we actually find out difference between fermions minus bosons. So this is the difference between power of fermions minus bosons. And we see that this is positive in the entire range of attractive on-site interaction, as well as some parts of the weak, in presence of weak repulsive interactions, fermions are always better. On the other hand, there is a on-site critical value of on-site interaction where above which bosons are better than the fermions. So there is a kind of, it's not ubiquitous. There are other issues which I'm not going to discuss. For example, that temperature of the initial states. As I already mentioned, that how many bosons per sites are allowed, what is the filling factor in case of fermions. These also play a crucial role in this picture, and also the performance of the battery. And in this scenario also we can show that if there is impurities or the interactions, the tunneling or the on-site interactions have some impurities or some randomness, then the battery still remains robust. And here I should mention that the impurities of on-site interactions and tunneling can be realized now in laboratories, and there are papers where the people have realized these impurities in this Bose-Hubbard or Fermi-Hubbard model. Now I come to the last part in a few minutes. This is design of quantum refrigerator. And as we know that in our refrigerator, the main aim is to decrease temperature. The question that was asked, is there a fundamental limit to their size? And does quantum mechanical systems help? And both the answers are affirmative, that was found. So all the works considered before this work in 2010, there are sources, outside sources were allowed to do the external work or to do the heat engine. So the initial work that I have presented, the initial results by Mehelan and others, there is an external source which actually control also the to cool down the engine. Now here in this work, they propose a self-contained refrigerator, and they showed that there will be no sources allowed for external work. And then they asked a question, right, what is the relations between efficiency and dimension? And they propose different models for such refrigerator, the self-contained refrigerator, like a two qubit refrigerator, one Q-treat qubit refrigerator, Q-treat refrigerator, and so on. And they show that they can cool down in dynamics the one of the cold qubit, one of the qubit can be cooled down, or the temperature can be reduced. So we also took this model, but now again we realize this in a spin model. So there is a Hamiltonian which acts as a refrigerator, has a field and interaction term as before. So field is this sigma z, and this is the XY Hamiltonian. And each, so first if you consider a 3-spin refrigerator, then these are the 3 qubits which act as a refrigerator. And in our model, first qubit we want to cool. So this is the one. And each of them is attached to a bath. So each spin is connected with a bath in case of harmonic bath. And this is the spin bath interaction. So initial state we consider when the interaction is turned off. So that means it will be just the eigenstate of the field Hamiltonian. So this is the initial state. Then in the weak coupling limit, you can consider the dynamics of the system. Here I should mention the results that I am presenting here for weak coupling limit, but in our paper we also consider the global Markovian dynamics, so global Lindbladian. And here the performance of the refrigerator is measured by heat current, so which is defined like that. So this is the system Hamiltonian, and this is this dissipative term. If heat current is positive, then in the steady state, then we claim that the qubit is cooled, or the cooling occurs or the refrigeration occurs. Similarly, in this scenario, we can also define local temperature. So initially the temperature, suppose is Ti0. So on the ith qubit, an initial state of the system, since the interaction is turned off, then this is the thermal state of the Hamiltonian. It's a diagonal. Now I start evolving the system, but you can show that in this scenario, the evolved state also will take this form. And so the TIT can be, so the temperature of the ith qubit at time t can be defined in terms of HI and this tau y, so the coefficient. And this is the temperature, and just the simple algebra, it can follow. So the local steady state cooling is achieved when ith qubit of the temperature of the ith qubit at large time. So the temperature at the steady state is strictly less than temperature of the initial state. And as I have said, in our model, this I is 1. So we want that the first qubit of the system and the steady state will be, the temperature of the first qubit will be strictly less than temperature of the initial state. And this is the result. So in case of two-spin refrigerator, we show that heat current of the first spin increases and temperature decreases. So we can show the proper refrigeration. And this is also you can show analytically. Here, just for demonstrations, I choose this figure. And similarly, you can show for the three-spin refrigerator. So clearly, heat current of the first spin increases, and these are for different interaction strength and different models that we have considered. And this is for the temperature. And clearly you see that in steady state temperature, which we have plotted, is, and the x-axis is the interaction strength. So when we increase slowly the interaction strength, actually the refrigeration happens more, again, we find that the quench average heat current or temperature shows a similar trend, as you can see. And this even when there is a disorder in the system. With this, I come to the end of my talk. So to summarize, I have tried to kind of convince you that quantum spin models are important to implement quantum technologies. As I have argued that these models can be realized in physical systems, in laboratories, like via ultra-cold atoms, ion traps, polar molecules, and even NMR and superconducting devices, and so on. I have shown that the battery can be designed efficiently via quantum spin model. They are robust against impurities as well as environmental noise. And we can also get some dimensional advantage if we beyond spin. Ultra-cold atoms, and this is probably more close to the experiment, because these experiments can be done in laboratories. So, and then I also have shown that the quantum refrigerators, the self-contained quantum refrigerator, can also be modeled by using quantum speed models, which are robust against impurities. So this is more or less the current group of mine. So they are my PhD students, and although is a postdoc under DST Project Quest. This is the QIC group, as mentioned by Usha. So this is a bit old picture. Many of them are now faculty or postdoc in different places. Due to COVID, we are not able to take a new picture. And thank you very much for your attention.
Thank you, Aditi, for an interesting talk. Any questions? Questions, comments from the audience? Is there... Yeah. Hello, Thomas.
Hello.
I think. Do you have a question? Do
Yes,
you have a
Usha,
question
may I
to
ask?
Aditi?
Yes, may I ask?
Sure.
Sure.
I'm not sure whether this is a naive
Please
question. So, but let me ask, I mean, I understand with your batteries that you have a magnetic field in X direction and somehow the spins are rotated from the ground state into the excited state or into a higher energetic state, let's put it this way. And now then you said that if you just have XX coupling, just XX coupling and no YY coupling, then you can charge better. And also that this order helps. Can you please tell me why it is better to not have the YY coupling?
But when you have the XX model means not only XX interaction, but also there is a YY interactions if you look. So can I go back maybe? Okay, maybe I make it like that so that I can move faster. So any Hamiltonian I can show you. Sorry. Yeah. So for example, this is the yeah. So when you have a gamma 0, then you have both XX and YY interactions, but in the same, they have the strength is same. Okay. But when you have a gamma non-zero, then you have somehow the disparity between XX interactions and YY interactions. And as you correctly pointed out, that we want to charge the battery in the X directions, right? So the charging of the battery in the X direction. And suppose when your system has a very weak coupling, then actually your magnetic field is dominating, which is in the Z direction. And so it will be hard, or you have to push more energy to get the, to put your spins in the X direction, giving you more power. Okay. Because we want to put it in the X direction. Now, when even you have a same XX and YY interaction, okay, that helps in some sense because, the spins are kind of entangled states, but also has kind of X component. But, in case of, suppose I increase the XX interactions very high, so gamma is very high, okay, that means the XX interaction dominates, right? So in that sense, now my charging magnetic field also in the X direction. So it actually, to make the system out of equilibrium, you don't have to put more energy. Actually, you have to put less energy compared to the scenario when you have a XX YI interaction strength the same. Okay. So in that sense, you get more power because pumping more energy to the system, here unitary dynamics I'm telling. So the pumping more energy to the system to lead to the out of equilibrium, to put the system out of equilibrium, you actually store more energy in case of XX model compared to XY model when you have a biasness towards the XX interaction. Am I clear to your question?
Yes, thank you. I think I understood you. Thank you.
I mean, probably the extreme scenario are much easier to explain when you have a very high, say, gamma, or you have a very low gamma or zero gamma, because, the system will be highly entangled. So the way I am saying is not that way simple because but this will be in a paramagnetic phase because J by H is less than 1, where I am showing this. So probably the argument that I show was correct. Is it satisfiable?
Yes, thank you.
Thank you.
So Aditi, I have a some kind of a question where I want to get it clarified for myself. So you showed a 3-level system also as you went on from a half to 3-level system also. So in the same sense, that is what you explained made clear sense because it gives you higher power and other things. So in the case of, in the earlier paper that you showed, Aliski and 2013 paper, they had taken many of the thermodynamics analysis, quantum thermodynamics cases. You have a single shot and a multiple shot kind of a analysis, where if you have a single shot, what you get, and if you take multiple copies and then subject it to the entangling batteries is what Aliski had shown, that you can extract still more energy, even though you will treat one copy as useless. So in that sense, what I want to know is, I don't know how many spins that you are taking in the chain, but if you had taken 2 copies of them and used the same analysis, would it have been 2 or 3 copies, and would it have given you something sensible in the sense?
Yeah, that's a very, Usha, it's a very interesting question. We haven't checked, but you are absolutely right, because, you know, if I have a spin half particles, okay, suppose I have a chain. Okay, one thing I haven't mentioned, there are calculations that we show is for 4 spins, 6 spins, 8 spins, and so on. And actually, we see that with the number of increase of the spins, the power is not that much of changing. Okay, although each spin dimension matters. Okay, so if you now what you are saying, suppose I have a 2 copy, and then the local magnetic field you have to apply not U1 tensor U2 in the local sense, but the global that entangling. Exactly. And then I mean local entangling in some sense, because one you will be local entangling, and I think it will be helpful because you know that means you are actually acting unitary on the 4-dimensional space instead of 2-dimensional, right? And what we have shown that if you so when you have a spin model with a J, there the battery Hamiltonian, the initial state is in higher dimension. At the same time, the charging field is also higher dimension. What you are saying, that suppose I also prepare the ground state in the tensor product of the, you know, the initial state, but I charge it with a higher dimension, I think it will be middle of what we got and what is what is the Alichki's result in the beginning. But it is a very interesting question. Maybe I will ask, and if I get something, I will tell you.
Thank you.
Because that will be,
because it's very curious in thermodynamics, because we can have a control of a single system and also multiple copies. So that's what is of some
because it will be easier for us to check, because you know all the mechanisms we have, we just have to check. So if I get, I will surely ask, tell you.
Sure. Thank you.
Very nice.
Thank you. So if there are no other comments, let me thank Aditi and for a wonderful lecture, and also all the 3 speakers, friends of mine, Chandru, Arul, and Aditi. It's very nice to listen to this. Thanks for enlightening us in this session. So the next session is after a tea break. So I think it is going to start at 5:20. So see you all. Last session is after break. See you. Bye.
See you.
Thank you so much, ma'am, for chairing this session of the conference, and I thank all the speakers for delivering wonderful talks in the session. We will now take a short tea break, and we will meet again at 17 hours 20 minutes Indian Standard Time for the next session of the conference. Thank you.
Hello, Dr. Agarwal.
Yeah, hello.
Yeah, you can share your screen. You have access right now.
Okay, sure. I will. Thank you. Hello.
Hi, Gopal.
Yeah, hello.
Yeah, can you just try presenting now?
Yeah, so actually to share here, this is open system preferences. So in WebEx, I haven't shared before.
Okay.
So
Okay,
you
so can
just
you do
guide
one
me?
thing, sir? We've had this problem before, so just leave the session now and then join again.
Okay,
That
sure.
usually
Sure. Thank you.
it's not about the thumb. This happens sometimes. Okay, now, sir.
Yeah, hello. So to share, I have to say it says open system preferences. So I have to do that.
Yeah, just follow steps then. Just follow the steps.
Okay. Okay, can you see the slides?
It's clear.
Okay, thank you.
Hello everyone. I welcome you again to the last session of the final day of the conference. In this session, we have three talks by Professor Pankaj Agarwal, Professor Sandeep Goel, and Professor Shivashish Ghosh. The session will be chaired by Professor Alok Khan. I therefore kindly invite Professor Khan to take over from here.
Well, thank you very much. I think we have 2 more minutes left. So should I start after 1 2 minutes?
Yes, sir, you can start in
Yeah.
2 minutes.
Yeah. Pankaj, how are you?
Oh, I am fine. So, how are things over there?
It's okay.
Yeah. Yeah, I mean, there was some common person. I mean, he was telling me about you.
Yeah. He told me. I told him that you tell him that clearly that you had did some work with me, and so
Right.
yeah, proofs. Then it's okay. Otherwise, we can stop it. Then
No.
he told me that you agreed happily, so then you can.
Yeah. I mean, this is science, right?
Yeah. Fine.
One should be able to work with anybody, at any time.
Yes.
Yeah. So
The guy
no,
is good actually.
yeah, he seems to be good.
Yeah.
Yeah, I think he told me you are considering him at NIT. I told him it is good for him.
Let's see what happens.
Yeah.
Any other things are okay? You are in Bhubaneswar still.
Yeah.
Okay.
Right. Yeah, at one point you were planning to come, right? I think
And due to COVID, I had to cancel. And then let's see when I get again that opportunity again. Let's see.
Yeah, this COVID will continue, I think, for another
For another year, I suppose. Yes.
Yeah, no, I think unless there is a third wave.
Yeah,
after a
third
few
wave
months-
seems unlikely in this part of the country. Maybe I don't know. I mean, it has not come yet. So let's see. I mean, after Durga Puja, we'll be able to see that how it goes.
Yeah, exactly. Because people are mingling so much that
Yeah.
we don't know. That we don't know.
Diwali is also here, but Diwali is kind of family festival, so it's not that much. Crowd will be there.
Yeah. I mean, actually, Durga Puja is more of a
Durga Puja more,
public thing. People get together and especially in puja pandals and all that.
In Kolkata, what happened, we have seen. I have not gone there, but in the newspaper and the TV, I've seen that people are mingling a lot.
Oh, yeah. Actually, I'm told one of my friend with his family went to Calcutta. Was telling me it is as if, COVID doesn't exist.
They forgot so quickly that in a few months back, there was no hospital.
Yeah. Actually, we have short memories, right?
Okay, Pankaj, we can start now because it's already 5:20, right?
Sure. Okay, so let me start then. Okay, so
okay, no, let me introduce you first, then we can start.
Okay, just okay, sure.
So formally, good evening to everyone and welcome to the evening session. And sadly, this is also the final session of this conference. And we have 3 excellent speakers in this session. And our first speaker is Professor Pankaj Agarwal, who is currently a professor at Institute of Physics, Bhubaneswar. And he works in the high energy physics and as well as in the quantum information theory. And I would like to add that Professor Agarwal himself arranged 3 huge international summer schools and conferences, and which were immensely successful. And I think those were perhaps one of the best summer schools in India. So we really miss those schools, and I hope when the COVID crisis gets over and he will arrange such schools again. So today he will be talking about the Bell's inequalities and tripartite states. And with this, I invite Professor Agarwal to start his talk. Thank you.
Okay. So, thank you, Alok. Actually, it is good that you remember all those schools. Actually, there were 5 of them and 5
5 of them.
conferences.
Okay. I missed that.
Yeah, but unfortunately, because of various, monetary and logistical issues, we couldn't continue. So, but I think in Calcutta now they are organizing some good schools, right? Okay, so let me start. So actually, the topic which I'm going to speak on is somewhat old. Okay, And actually, a lot of very interesting talks in this conference, they are on the more recent topics, right? And which are actually more interesting in some ways because a lot of them have some practical significance. So, but this particular topic which I'm going to speak on, although it is quite old, but there are still lots of possibilities, because as you know, multipartite states, we don't know, how to characterize their non-locality or their entanglement properties. If we don't know how to do that, then obviously, characterizing their non-locality is also, is still an open question. Although there are thousands of papers, there are thousands of Bell inequalities perhaps in literature, but still I think everything can still be perhaps put together better and perhaps more can be done. Anyway, so let me start. So I think my slides are visible as far as I understand. So let me start with the introduction, which is very trivial type of thing for this audience, but I guess as some formality, I will go through some of the statements which are known to everybody. So as you know, as we all know, that this framework is quantum mechanical framework has been with us now for more than 100 years, right? And it is everywhere, right? We cannot imagine doing science or physics at least, without using quantum mechanics. But actually, we still debate actually what this framework represents. Okay, there are all kind of issues like measurement issue, interpretation issue, wave function collapse issue. Are there any, people are also debating whether, these postulates, where do they come from? Is there some physical motivation, to get those postulates? And one of the features of a quantum mechanical system, especially if it is a composite system, is that it may have a property which we call entanglement. Okay? And this has led to many enduring mysteries, starting, from the very beginning when Einstein even presented this EPR paradox. Okay, so I think more than 75 years. And we still, some people will still say there is still some mystery involved in understanding what this entanglement is. But for us, from practical standpoint, this entanglement actually can act as a resource. So it can allow us to do many things like in so many talks people have discussed, which you cannot do otherwise. Okay, well, so it has a lot of practical implications now, quantum computer, quantum communication, quantum cryptography. Okay, not all of them may involve entanglement, but they do involve some quantum features, right? More generally superposition. So, but from a more theoretical standpoint, one of the implications of this entanglement is, that there is some non-locality in the framework. And whether some people, of course, will say there is no such thing, but I think more generally speaking, perhaps there is a general consensus that quantum mechanics does exhibit non-locality. Okay, so so how do we explore it? So one way has been from the time of Bell that you have certain kind of inequalities which will help you to explore, some of the non-local features of a quantum system. Okay, so we are just interested in these Bell type things. So as you all know that if you have a 2-qubit pure state, non-locality can be explored using Bell type inequalities, especially Bell CHS inequality. There is also relation between the violation and the entanglement. Okay, so if you know, so there is a relation. If you know how much is the violation, then you can also find the entanglement, especially in the pure state. Okay, so it can be used in some sense to measure the entanglement. Of course, once you go beyond 2-qubit pure state, like almost everything is not as well understood. So if you go to even two qubit states, okay, you will find some interesting features. So if you go to 2-qubit pure state, okay, or multi-qubit pure state, or even 2-qubit mixed states, to understanding these states is still, especially there are some of their characteristic and some of their features is still a challenge. But our focus will be just on 3 qubit mostly. Okay, and we will focus on the inequalities that are maximally violated by GSZ state or a W state. Okay, so okay, just a bit of past history. So as we all know that in 1964, Bell obtained an inequality, and he demonstrated the incompatibility between local realism and quantum mechanics. Of course, he was using a singlet state, but then actually took quite a bit of time. But it was, as Jisin was saying, he was surprised to know that no one has shown it explicitly, that any pure entangled state of a bipartite system will violate this CHSH inequality. Okay, so he gave a formal proof, okay, at that time. So this inequality can actually be written in terms of correlations of observables. And we have a Selson bound, which tells us that maximal violation in quantum mechanics is 2√2. Okay, so when I say violation, it means a value, okay, of that particular, collection of those correlations, okay. Okay, so one can establish also relationship between entanglement and non-locality, at least for pure, bipartite states. Okay, as we just discussed, situation about mixed state is not very clear. There are entangled states which do not violate the standard CHS inequality. I mean, as we all know that Werner state is a very prototype example. So although because there are hidden variable models for for a range of parameters for such entangled states, even if not for all entangled state for which we have this hidden non-locality, at least for Werner case we have. Okay, people have not constructed for all kind of mixed state which show this phenomenon of hidden non-locality. Because this phenomena is pretty universal. I mean, it is pretty common. So there exists this phenomena. Okay, as I just said, in literature, people have shown that even if we have this Bell CHS may not be violated, but there is a way to explore the non-locality. So there were these various attempts by Jisin, Buscemi, and Massenes, and they have basically then shown that in some sense all entangled state, even if they are mixed, they show some non-local behavior. Okay, so but as I was just saying, this phenomena is more of a norm, rather than exception. Okay. Okay. Okay, so I mean, there are many ways to characterize non-locality, but I don't wish to get into that. But one thing which I want to just a bit focus on is this phenomena called anomaly of non-locality. I mean, intuitively, you may think, more non-local, quote unquote, a state is, more will be the violation, okay, of some Bell inequality, okay, or Bell type inequality. But this doesn't seems to be the case, okay. So number of people dubbed this phenomena as anomaly of non-locality. Okay, so now it appears to be more of a norm. Okay, so one has to understand it. Okay, why we have this anomaly, because as I will just discuss, this is as common as hidden non-locality. In the case of 2 qubits, this Bell CH is maximally violated by a maximally entangled state, as we all know. So this is what you may call minimal scenario inequality. So what I mean by minimal scenario is that for 2 qubits, if you want to see the violation of some, if you want to come up with the inequality, it has to involve 2 measurements by on each party. So you have 2 qubits or you have 2 qubits, whatever. So you have to make at least 2 measurements each on each system. Okay, you can make more than that also. I mean, more than 2, but the minimal scenario will require that you should make at least 2 measurements each with 2 outcomes each. Okay, and it has been shown that for for such a minimal scenario, actually there is only one non-trivial facet inequality. which happen to be Bell-CHS inequality. Okay. So you have this only one facet facet Bell inequality. When I say facet Bell, it means non-trivial facet inequality that I may refer to sometimes as Bell facet inequality. Okay, so there happens to be just one, and that is Bell-CHS, and that is is in accord with this intuition that more non-locality implies more violation. Okay. So, okay, but situation is different as we go beyond 2-qubit case. So as we all know that even if you just look at a 2-qubit system, there is this famous CGLMP inequality. Even that is maximally violated by a partial entangled state. Okay, and it is true for actually any bipartite qubit system. If you go beyond qubit, the same situation holds. So if you go to multipartite, of course, situation becomes more complex. So if you look at the simplest possible scenario beyond bipartite scenario, that will be tripartite scenario. So in this case, we have this one of the earliest inequality, and which is I think more famous than any other. Although there are maybe literally hundreds of inequalities, but we all know more about this Mermin inequality. So this Mermin inequality is even not violated by all in entangled states. Okay, so and this happens in part because if you look at this particular scenario where you discuss this Mermin inequality, there you have three parties, three qubits. I mean, in the simplest case, it can talk about more than that also. If you have a 3 qubits and you are making 2 measurements each, okay, on each qubit with 2 outcomes. So then actually it has been shown by Silva that there are actually 46 non-trivial facet inequalities. So you don't expect that Mermin will be violated by all entangled state. Only one of those 46 has to be violated. So you see, if you want to detect non-locality using this particular measurement scenario, you have to make a test of at least 46, different inequalities. I mean, violation of them. Because if you use just one and it is not being violated, that does not mean that your state does not have non-locality. Okay, so one may wish to get around this situation by going to, as I was talking, minimal Bell scenario. So if you want to go to more minimal scenario, then it means you have to minimize the number of measurements. Okay, so which will reduce the number of non-trivial facet inequalities. So in the case of 3 qubit, minimal or even n qubits, okay, if you go to some minimal scenario, then actually you will have fewer facet Bell inequalities which have to be violated. And if you do, say, for example, tripartite case, then actually such a minimal scenario will be 2 parties make 2 measurements each, and third party will make only 1 measurement. Okay, so this is a minimal scenario where you will get a Bell inequality which is actually violated by a state which is entangled. Okay. And this can be generalized to multi-party case. Okay, so in multi-party situation, minimal scenario will be that 2 parties makes 2 measurements each, and rest of them make only 1 measurement. Okay, so so actually, as we will see in such a case, you may have actually only one non-trivial facet inequality. So instead of 46, you need to see the violation of only one of them. So, okay, so this is the advantage of considering a minimal scenario. However, as we will see that even when you have a minimal scenario, and even if you have only one non-trivial facet inequality, this also exhibits this anomaly of non-locality. So it is not so. Okay, so in the case of 2 qubits, we had only CHS as a non-trivial, facet inequality for the minimal scenario. Here also for minimal scenario, when you go to 3 qubit, you could have only one non-trivial facet inequality, but here we have this anomaly of non-locality. It means in the case of 3 qubits, okay, when you go to multi-qubit, this is itself is the issue, that which state you will consider to be maximally entangled. Okay, but in the case of 3 qubits, I guess there are many reasons to consider GSZ, okay, state to be maximally entangled. Once you go beyond 3 of qubits, of course, this thing would not hold. Okay, but for 3 qubits, I think perhaps most people will agree to that. Okay. So because of this phenomena of anomaly of non-locality, one may wish to construct Bell inequalities that are maximally violated by a class of states. Okay. So for the 3 qubit case, one classification. So there can be many different ways to classify. Okay. It all depends what you want to do. Right. Because so one way of classify is on the basis of SLOCC, which is the interconvertibility of one state to another. Okay. But you may wish to consider some other way to classify also, like whether you can do teleportation or some other communication task using that class of state. So that will be a different classification, but more standard well-known classification is for 3 qubit pure state is at least this on the basis of this SLOCC. And we know that if you look at only genuinely entangled state, so we have these two classes, GSZ and W. And then as we also know that for GSZ, we have this particular state 0, 0, 0 plus 1, 1, 1. While for W, we have this 1, 0, 0, 0, 1, 0, 1, 0, 0. So what you may wish to construct Bell inequalities, which may be maximally violated by either GSZ state or by say W state. Okay, so in that way, because in that way, we have at least you can detect that by looking at the violation, what state it is. Okay. So this is because as we just discussed that we have this anomaly of non-locality. So if you are given a Bell inequality, so it need not be violated maximally by a particular state. But if you are interested in a particular state, then you may wish to construct an inequality which will be violated maximally by that particular state. And on the basis of SLOCC, interesting thing will be this GSZ and W. So one may wish to find inequality which are maximally violated by either GSZ or W. Okay, so our discussion, as I said, is about tripartite. For the GSZ, we already have this Mermin inequality. Actually, this is maximally violated by GSZ state. But as we all know, it also has a drawback that it is not violated by many generalized GSZ states, like alpha 0, 0 plus beta 1, 1, 1, 1, 1. Okay, so therefore, some values of alpha and beta, Mermin equality is not violated. But of course, there are no many inequalities in literature which have been shown to violate, which are violated by these generalized GSZ state. And actually, it is not surprising, right? Because if you, as I just said, if you look at this Siliva's 46 Bell inequalities, Mermin is just one of them, right? So if Mermin is not violating, then one of those other facet inequalities will be violated. Okay, and it has been, people have not only used those Bell inequalities, but also there was some construction of Bell inequalities by Banker et al. And people have used those inequalities also, and then they've used some new constructed inequalities also. Okay, so what we have, but in most of those cases, scenarios are not what we are calling minimal scenario. Okay, so minimal scenario, as I have already defined. Okay, so what we want to be interested in, minimal scenario Bell inequality, which is maximally violated by GSZ state. Okay, so okay. So I will also mention this, this minimal scenario non-trivial facet inequalities, which have been found actually at some other point in literature, and they are referred to as lifted Bell inequalities. Okay. So, but one can, so one can, so there's some, so one can construct from Bell inequalities, from CHS inequalities, these non-trivial facet inequalities for minimal scenario. Or one can just go and just construct all the facets, and see which are the non-trivial facets. Okay. So advantage, as I said, of minimal scenario is that you don't have to test many inequalities. Okay, so like Sliwa case, I mean, if you have 3 qubits, 2 measurement each with 2 outcomes, you have at least 46 inequalities to test. Okay. So once you want to make one measurement on one of the systems, so then you can have 3 different scenarios where you can be, because if state is not symmetric with respect to permutations, you can make a measurement on any one of those 3 qubits. But each scenario will be different. Okay, and each scenario you will get just one non-trivial facet Bell inequality. But as I was just saying, unfortunately, the minimal scenario for 3 qubit also show the anomaly of non-locality. So one has to understand why that is the case, and which I think is still not well understood. Okay, so we'll also discuss, Bell inequality that is maximally violated by a W state. Okay, but actually that will be only for a specific measurement setting. Okay, so as I should also mention, whatever I will discuss was done with Arpan, Chandan, and Shuryansh. Okay, so in the tripartite case, if I want to have a minimal scenario, right? So one can construct inequalities just just the way one constructs CHSH inequality. Okay, so we know that there is this value state 5+, then we have this GSZ state. And the measurement settings, which will give you the maximal violation for this 5+, will lead to an operator which will be proportional to this sigma x plus sigma z sigma z. Okay, actually we root 2 into this, which will actually lead to the maximal violation. So this particular measurement setting is the best for, measurement setting which will lead to this particular combination of operators to be the most useful. So similarly, one can construct for GSZ. Okay, so you will have just, then you are making one party, you want to just make one measurement, like here by sigma x. Okay, and okay, so there are 2 parties will make 2 measurement each, one third party will make only 1 measurement. So if you do that, then actually one can come up with a bunch of inequalities. Here there are 6 inequalities. Okay, so if you look at it closely, you will see this is like CHSH, B1 C1 plus C2 plus B2 C1 minus C2, except I have this one extra measurement on the third party. So there is A1. Okay, so this is just a slightly modified version of you may say CHSH. Okay. Okay, so since I can make a one measurement on either by Alice, Alice, Bob, and Charlie, either one of them may choose to make only one measurement. Okay, so in that way you will have kind of multiple Bell inequalities. Okay, like for example, if you look at 1, 1st, and 3rd, here Alice is making only one measurement. Okay, but Bob and Charlie are making 2 measurements. But if you look at 2nd, here Bob is making only one measurement, but Alice and Charlie are making 2 measurements each. Okay, so actually, in some sense, there are actually 2 independent Bell inequalities because if Alice makes only one measurement, then 1st and 3rd. Others 6 are there because in other 2, Bob is making one measurement. In the 3rd pair, Charlie is making one measurement. Okay. So as I was just pointing out that they have a similarity with with conventional CHS inequality because their form was motivated in some sense by this CHSH. Okay, and then one can actually generalize these inequalities to arbitrary number of qubits. Okay, so one can look at this quantum bound for this inequality. So one can choose one of them. A thing will work similarly for the other, and the process actually is just same, just like for CHSH. Okay, you just square it, then you use this Schwarz inequality. Okay, and after using that, you will find bound is actually same as the Celsius bound. Okay, so this is a maximal violation you could have. So now just look at this generalized GSZ. Actually, okay, here interesting thing about this inequality is that it can track in some sense entanglement of this generalized GSZ state. Okay, so if you have this parameter alpha and beta, so if you think this some combination of alpha and beta will characterize the entanglement of this state, and then you can have some function in analogy with the concurrence for a 2-qubit state. And then you will see that violation is tracking that entanglement. Okay, so let's see here. So our pure state in generalized GSZ class will violate this inequality that we have, and we will see it below. And this is not surprising because this is designed for GSZ state. Okay. So now let's see, as long as alpha and beta are non-zero, this state will violate one of these inequalities. Okay. So let's take this inequality. Here, as you see, Charlie is making one measurement, but it does not matter. We can take either any of the cases. And if I choose this particular measurement setting, which is also inspired by what you do in the case of Bell CHS, to get maximal violation, right? So there again, so Alice makes like this measurement, sigma z, sigma x. This is a Bob. So Charlie is making just one measurement, as you notice. Okay. So then in the end, you want to calculate this, this expectation value for the generalized GSZ state, use this inequality, and then you immediately see that it is proportional to 2 into 1 plus 4 alpha square beta square, where alpha and beta, they characterize this state. Okay. So if one of them is 0, then state is not entangled, right? As long as both are non-zero, your state is entangled. And that is what you see here. As long as alpha and beta both are non-zero, however small, okay, there is a violation. So all generalized GSZ states will violate. So as I'm saying, there are many other Bell inequalities which people have shown. Okay, they also now violate this generalized GSZ state. Only thing here is this is a kind of minimal scenario. Number one, number two, that your entanglement in some sense, if you say it is being tracked by this alpha beta, just like concurrence, then there is a relationship between the violation and the entanglement of this generalized GSZ state, which is not true in the case of other Bell inequalities which are there in literature. Okay. So as we see, as long as state is entangled, so all generalized GSZ state will violate. And as I was saying, if you think of 2 alpha beta as some kind of, in analogy with 2 qubit, some measure of entanglement, then again, violation is tracking the entanglement. Then one can generalize for n qubit. So okay, so I have just shown here for the case of GSZ. Okay, I'm generalized GSZ, but actually one can see numerically. And that it, because analytically it is not easy to show that if you take any arbitrary 3-qubit pure state, in particular you can take like SN parameterization, okay, and then you try to check numerically whether you randomly choose some states, say few thousand or maybe hundreds of thousand states, and see if one of those inequalities is being violated. Okay, so in this case, so you can take a most general case when all these lambdas and phi are non-zero, or you can have some specific cases when some of these lambdas are zeros. Okay, so what we did actually, we took 25,000 states, okay, where all lambdas were non-zero, and then there are different classes for which you use 5,000 each. So total 70,000 states were used to check if there is a violation for all these. So they were randomly chosen states. So so here x-axis tells you, violation, okay, whether it is more than 2 or not. Okay, so first inequality turns out is not violated by most, okay, except 297 states. Then if you go to second, you are left with even fewer. If you go to third and fourth, you left with fewer. Only 3 states don't violate it. Third, only 2 fourth. If you go to fifth, all of them violate it. Okay. So this was for 25,000, and then similarly we had checked for other other classes, 9 classes where some of the lambdas are 0. So total we took 5 into 9, 45,000. Okay, there again we see the violation. Okay, so these inequalities, which are minimal scenario inequalities, seem to be violating, at least in the pure state case. Okay, in mixed state, obviously, as I was saying, there will be phenomena of this hidden non-locality. In some cases, it will not be. I mean, these inequalities will not be violated. So one can generalize it to n qubit. Okay, so you can distinguish between odd and even case. Okay, for odd number of qubit, one can check that there will be 2n into n minus 1 inequalities. Okay, because you can make one measurement each by either Alice or Bob or Charlie. So in this case, only 2 measurements are being made by only 2 parties. The rest of them are making just one measurement each. Okay. So I mean, so one can check actually. This is a generalization, and it seems to work if you look at generalized n qubit GHZ state, and if you use these inequalities, you will find that there is a violation. For even number is really smaller. Okay. So in the case of general, if you look at n qubit GHZ state, one can show that these inequalities will be violated by this generalized n qubit GHZ state. Okay. So what we have shown is set of minimal scenario inequalities, which seems to be working fine. Okay. So now what about W state? Okay. Now in the case of W state, actually one can construct some Bell inequality. And the one which I have written down here seems a bit complicated, and which actually has been one can come up by looking at what kind of measurements can help you. Okay, so here this inequality is actually of this form. Okay, B1 plus B2 and bracket may A1 1 plus C1 1 plus A2 into C2, and then B1 minus B2 A1 C2 minus 3 A2 C1. This number 3 seems to be critical. If you change it, you will see there is no violation. Okay, plus root 2 A1 C2. Actually, if you want to see the local values, as you will see, you can get 4 into 2 8 there, 4 into 2 8 here. Okay, that's why in the end 3 turns out to be the ideal. If you make 2 or 4, it won't work. So now this state is symmetric, right? This our this W state. If you permute qubits, so you can even permute here these AI, BI, and CI, and all of them will take this value plus minus 1. And then you can check the local value. Is just you can get 4 into 2 8 plus root 2. Okay, I mean that is a maximum local value. Okay. So now, of course, you want to see whether there are measurement settings which will violate it. So in the case of so you want to calculate this expectation value, and actually the form of that inequality was motivated by a particular measurement setting, because they give rise to operators of which W is the eigenstate. Okay. So if you use A1 like this, sigma x, sigma z, when Alice makes 2 measurements, sigma x, sigma z, Bob use these operators, and Charlie uses these operators. So then you look at what this operator looks like, this Bell operator. Okay, and therefore for this BW which I wrote down earlier, this one. Okay, so this form, which looks somewhat intriguing, one can see how it comes if one looks here. Okay, so if you look at this Bell operator, then one can rewrite in terms of oh sorry, this there is a misprint here. Just 1 minute. Yeah, there should not be equal to. Okay, this equal to should not be there. Plus this. Okay, so this equal to is a mistake here. Okay. So actually, it turns out then this thing can be written in terms of two operators, O1 and O2. I mean this BW operator, where O1 is this operator sigma x, I plus sigma z. And I plus sigma z is basically permuted, okay, on all three qubits. And O2 is this. And this W state is actually the eigenstate of both of these operators, 4 and minus. Then if I calculate this expectation value, I will get 7 root 2. I will get 4 from here and 3 from there. If you see here, 4 from here and 3 from here, 7 into root. I will because its eigenvalue is -1. Okay. So I will get just 7 root 2, which is 9.898. And maximal local value was 8 plus root 2, which was 9.414. Okay. So what we see that maximal local value, you can get more than that, okay, for this W state. So W state is violating that particular Bell inequality for this specific measurement settings. Because as we all know, this value of violation, or whether there will be violation at all, depends on the measurement settings. Okay. So in this case, we see there is a violation if you use this particular these particular measurement settings. Okay, and for this particular inequality. Okay. So so in that way, this is good. We have some Bell inequality, but only drawback, as I will show you, is that unfortunately, if you use some other measurement settings, then there are other states which could violate this inequality more. But if I restrict myself to this specific measurement settings, then W state actually violates it most. No other state will give me 9.898. They will all give me values smaller than this. Okay, so what we see that, okay, a specific set of measurement, W state violate this Bell inequality. And as I was just saying, we have checked that for this setting, the maximal violation which we have is 9.898. I mean, this is the maximal value which we are getting for W state. If I use some other measurement setting, then even for W, I will get a smaller value and sometime no violation. Okay. So all other states, if I replace this W state by those states, I will get value which is smaller than 9.898. Okay, so W state is violating it most, but for this specific measurement setting. Okay, so this is what it says. Okay, there are states which may violate more if you use a different measurement settings. Okay, so I mean there is a scope still to find a Bell inequality which is violated most by a W state, and for any arbitrary measurement settings. But in our case, okay, since it works for a specific measurement setting, so you can use it to in some way to identify a W state also, right? Because we know if I use a particular measurement setting, if I am trying to, then if I then measure this particular Bell operator, W state will give me the largest value. Okay. Okay, so this is about W state and GSZ state. Now, as I was telling you, there are also these facet inequalities, and one can get them as a facet inequalities, but also, as I was just telling you, in literature, some people have obtained them through a different procedure called lifting procedure, and they have come up with, they have also found the same inequalities. Okay. So if you then, one can always, use this. There is a method to find facet Bell inequality. If you follow that specific procedure, you can find all facets. and you will find of this local polytope. Okay, so then you have this giant probability distribution which have to satisfy certain conditions. Then you try to find out using those conditions what kind of local polytope facets you can get. And most of them happen to be, just positivity conditions. Only some of them happen to be non-trivial, inequalities. So in this specific scenario, remember we are talking about minimal scenario here, right? So where 2 to 1 measurement with 2 outcomes each. And as I was just telling you, there is actually only one. So actually, by one can show these 4 are, so these 4 are there, but these all 4 are actually equivalent to just 1. So there is actually one, this Bell inequality, which is facet inequality for this minimal scenario. Okay. Okay, so where actually in this case, you think Charlie is making only one measurement. Okay. So point here is that, you don't have to find the violation of those 46. Okay, because if you have entangled state, it may or may not violate one of those 46, most of those 46, facet inequalities which were obtained by Sliver, right? But here you have only one. So this is a big advantage of minimal scenario. Okay, so as I was just telling you, instead of Alice, Bob and Charlie could make one measurement each, but they correspond to different scenarios. Okay. Okay, so here you have these inequalities, then actually from I just want, so one can discuss many things, but I just want to point out things which are related to this anomaly of non-locality, right? Because as we said, CHSH was only facet inequality for 2 qubits, and that was maximally violated by maximally entangled state. But although in this case also I have only one facet inequality, but in this particular minimal scenario, but unfortunately, this is not maximally violated by GHZ state. And as I was saying, if you go beyond 3 qubit, you will not consider GHZ to be maximally entangled. But for 3 qubits, by many different considerations, you can think of this as maximally entangled. But here you see, if I calculate this, then maximal, so I can maximize over all measurement settings, then you will get 2.83, for GSZ, but 3.10 for W. So, so this inequality is violated more by W. Well, but it is not, so is the W is the state which violates it most? It turns out not to be the case. Okay, so because you can find a state in GSZ class. Okay, but before talking about that, one can show that actually all generalized GSZ state actually violate this. Actually, as you will expect, any entangled state, at least if it is a pure entangled state, should be violating it. And one can check easily that for GSZ, just following our earlier procedure. I think I may have shown it, just let me see. Yeah, I have shown it later also, that one can show that, this Bell inequality is violated by all generalized GSZ. But as I was telling you, here you see GSZ 2.83, 3.10, but there is a state belonging to GSZ class. Okay, this state one can check, by calculating, okay, so by calculating this quantity called tau, okay, whether it is GSZ class or W class state. So if you this state GSZ class, but gives you more, okay, then not only GSZ state, but also this this W state. So in some sense, you may think this state is not as entangled, okay, in some vague sense as compared to GSZ state, but only inequality that you have is violated more by this. Similarly, you can see for the W case, you will take another W class and you will see more value, 3.10 for W, but you have a higher value. So there doesn't seem to be any pattern. Okay, all you can say is, okay, if you have a pure entangled 3 qubit state, and then this inequality will be violated. Okay. So actually this, because as long as it is entangled, even if it is biseparable, like this state, this will also violate this, because while you are for finding these facets, so we are the criteria which one uses, for that even this biseparable state should also be violating, as long as there is some violation of locality. Okay, so here actually it is just being shown that, just following the earlier procedure, that this particular facet inequality is violated by all generalized GSZ. Okay. So other thing, I guess quickly, I think time is coming to an end. So I may just want to quickly mention that actually a lot of these facet inequalities as well as this Mermin and Swift-Lichner, they can be used to even measure the entanglement. Because if you use some general measurement setting and you find, this expectation value, it has this type of form, x plus cy. Okay. So, so you can measure, how much, especially, if you think this C does characterize entanglement, if you take that way, then, you can see, you can even measure it. Okay. Same thing is true about this Bell inequality, which we talked a bit earlier. Again, it can track that entanglement for any measure. Thing is for any measurement setting, as long as it is 2 to 1. 2 by LS, 2 by Bob, 1 by Charlie, as long as it is that, for any measurement setting, you can measure this entanglement. The same thing is true, but Mermin is not violated, as you see, C comes here. Okay. So unless C has a large enough value, this GGSZ state will not violate that Mermin. Same thing is true about Swift-Lichner. Okay, so similarly, one can look at mixed state, but as we will see, just there's a phenomenon of hidden non-locality. Okay, so you have all these mixed, you have this GSZ state, which are, in some sense, non-maximally entangled. So using that, you can create this mixed states, and you can find the value of P, for which you start having violation. Okay. And you will find that as long as state has a lot of GSZ, Mermin can detect it more. But if a state has less of that, more of W, then actually his facet was better. Okay, so in conclusion, this CHS inequality for 2-qubit system, is maximally violated by a maximally entangled. For 2-qubit, 2 measurement on OS 2-qubit is a minimal scenario. So for this scenario, there is only one facet inequality, which is CHSH. So there is a direct link between non-locality and violation. But as soon as we go beyond 2-qubit, you have the anomaly of non-locality. In the case of 3-qubit, we considered minimal scenario, and we saw what are the possible Bell inequalities, which are maximally violated by GSZ as well as generalized GSZ. Also, we had an inequality for W state, which is maximally violated, by W state as compared to any other pure state, or any other state, I should say, in general, for a specific measurement setting. But of course, they are not, so you can have only one non-trivial facet Bell inequality, but unfortunately, you still have this anomaly of non-locality. Okay, thank you. This is all I have to say.
Thank you very much for this very interesting and wonderful talk. So we are now open for a couple of quick questions. Is there anyone?
Hello, sir.
Yeah, hello.
Yes, please go ahead.
First of all, thank you so much for this wonderful talk. I'm also working in something like that, for inequalities. I have a question regarding that inequality you discussed for W state. I just want to know what is the violation for that inequality for GSZ case.
Yeah, actually, I don't have number here, but I can find it and tell you. Okay, but we have checked it. Okay, it is violation is more for W case. Okay, in GSZ case, actually somehow I think this, I mean, okay, one of the problem with this inequality is that it is perhaps is not being violated by all entangled states. Okay, and some of the GSZ class states were not actually violating. Okay. Okay, so
Okay, sir, thank you so much.
okay.
I just want to know that that inequality violated by the maximally entangled GSZ state or not?
Yeah, actually, okay. From what I remember, it is not. Okay. Okay,
Okay,
so
sir.
if you look at this GSZ state, okay, so we have these numbers. Okay, I have to, but from what I remember, this GSZ state, even this quote unquote maximally entangled, was not violating this. Okay.
Okay, sir. Thank you so much.
Mhm.
Any comment about mixed states?
Any mixed state is again, the things are in flux, right? For some mixed states, there is a violation. For some, there is not. Now, sometimes you see, thing is, okay, I don't know which particular inequality you are talking about, but in each case, same situation exists, right? And in some cases, from my understanding, will be if I look at this for this facet, it will be violated by as long as the state is entangled and there is no hidden non-locality. But unfortunately, there is hidden, as I was showing you here, right? So if you see here, this facet thing, it starts violation for large enough P. Okay.
Okay.
So because there is hidden, you cannot get away from that. Okay. So it is true. Even Mermin, if you use, it is also, whatever inequality you use, you always once you have a hidden, once you have a mixed states, you will always have this phenomenon. If a state is quote unquote mixed enough, okay, then you will always have this phenomena of hidden non-locality, as you can see here, right?
Yeah.
P has to be large enough.
Any more question? Maybe I have one.
Sir.
Okay, sure. Go ahead.
Okay, so thank you, sir. Sir, actually, I just want to know that if this work is published, can you please share the link for this paper?
Okay. Okay. So if you send me an email, I will share it with you. Okay.
Okay, sir. I will send you a mail. Thank you so much, sir.
Okay, so I have a question.
Sure.
Thought is that how did you find those inequalities? I mean, what's the basic, the background of it?
No, actually, facet one is simple, right? You find the
okay.
facet.
I mean, the
right?
first inequalities you showed for the bound was 2, local bound was 2, and you said they're all GHs to be violated.
Yeah, right. So you see, motivation came from to find basically. Okay, so let me go back.
Yeah.
Just 1 minute.
And it's surprising. I just want to add that for any n number of qubits entangled state, you kind of only for 4 correlations you are considering, and you are getting the violations.
Yeah. Actually, what I'm saying. This is minimal. Actually, somehow in literature, people don't worry about scenarios, right? They don't somehow, making one measurement seems, oh well, why make one measurement? You should make at least 2, right? So people don't think about making less than 2 measurements most of the time. And because of that, you don't get to minimal scenario. Okay, you always, as I was just telling you, Siliva, he has 2, 2, 2. For 3 qubit, you have 46, facet Bell inequalities, right? But as soon as I come to minimal scenario, I have only 1, right? So minimal scenario is somehow not emphasized as much in literature as it could be,
Yeah.
Okay, so
you go back to the first one. Yeah. For example, these 2.
Yeah. I'm going to first one. Yeah. So actually, motivation was coming just from this how it works for Bell. Okay.
Yes, sure. Let that one.
Yeah. So let me just go below. Just 1 minute. There was something somewhere. I had written those operators. Just 1 minute.
Yeah, the sigma x plus sigma x and sigma.
Yeah. So I'm just going there. Let me see where it is. Just 1 minute.
It's down.
Yeah. Motivation, as you see, just from here, right here. Okay. So if you make your, that measurement, like Alice measures a sigma x, sigma z, Bob measures a sigma x plus sigma z by √2 and sigma x minus sigma z √2, right? So with those measurement setting, you will get this operator.
Yeah.
Multiplied by √2.
Yeah.
Okay. And you will see your Bell state like this phi is the eigenstate of both of those operators. So it was just being generalized. Okay.
Okay, that's a good one. Yeah.
So
okay, if we are running out of time a little bit, so Pankaj, thank you very much for this really wonderful talk.
Thank you. So I will stop sharing now. Just 1 minute.
Yeah. Yes.
Stop sharing. Yeah. Thank you.
So our next speaker is Dr. Sandeep Goyal. Sandeep, are you here?
Yes, I'm here.
Okay. So could you please share your screen?
Yes.
I mean,
share screen. Yes, I'm just new with the WebEx, so I'm just.
Yeah, me too. Yeah. It took time.
So can you see my screen?
I see screen, but nothing. Yeah, your
The
presentation
talk is not there. Now can you see the talk?
Yeah. Okay. It's coming. Perfect. Yes. So our next speaker is Dr. Sandeep Goyal, and he is currently an assistant professor at IISER Mohali. And he did his PhD at Institute of Mathematical Science, Chennai, and popularly known as IMSC. In fact, he did his PhD with Professor Sivasis Ghosh, and he will be the next speaker. And Sandeep did, after PhD, Sandeep did a couple of postdocs at University of KwaZulu-Natal, South Africa, and University of Calgary, in Canada. And his primary interests are in classical and quantum optics, in particular on light matter interactions, quantum memory, classical simulations of quantum algorithms, and a few more. So today he will be talking about this a linear optical scheme to implement arbitrary discrete POVMs, and it seems it's a very interesting topic. So I invite Sandeep to present his talk. Thank you.
Thank you, Alok, for this introduction and giving me the stage. For a moment, the introduction sounded very familiar. Then I realized I was the one who wrote this introduction. We all had to write one. So I would like to start the talk with thanking the organizers of QFA. It's a wonderful conference. Unfortunately, I could not attend much of it because of some personal issues. But today I'm here for most of the time. Today I was here. So now let me start without wasting any more time. Let me start with the talk. In this is our recent work, and it's still making rounds with the referees because apparently APS is not finding enough referees nowadays. So the title of the work is Linear Optical Scheme to Implement Arbitrary Discrete POVM. So as the title suggests, in this work, we show how you can implement any arbitrary POVM on linear optical setup. Whenever we have optical setups, it's generally difficult to imagine non-local operation or non-unitary operations and all those kind of things. So here in this work, we show how you just give me any arbitrary POVM and I'll tell you how you can implement it on an optical system, right? So with this, let us start as usual with the introduction of the basic concepts. So first thing in this is POVM. The most general measurement in quantum theories are represented by POVM. So there is nothing which you can call measurement and does not fall in POVM category. Although there are many ways of explaining or introducing POVMs. For example, you can introduce POVM as a set of operators, M, set of operators, and where operators are E0, E1 up to En. So it's N outcome POVM. Okay, POVM stands for positive operator valued measurements. Sorry, I did not mention it anywhere. So POVMs, so they are like generalized measurements. We can just think of it like this. So one formal way of introducing it is by a set of operators. Okay, and these operators have certain properties. Namely, all of them should be positive in the sense that they should be Hermitian and they should have a positive semi-definite spectrum. So eigenvalues are allowed to be either zeros or positive numbers. On top of that, they should add to 1. So it means none of the eigenvalues can be more than 1. And when you add not the eigenvalues but the operators, then it becomes identity operator. Okay, so this is a formal way. So I want to perform a POVM. I want to study a POVM. So I have a set of operators which satisfy these properties. And when we perform measurement on this hypothetical setup, we get one of these outcomes 0, 1, 2, or n minus 1. The ith outcome, let us say I can be 0 to n minus 1, will occur with probability pi, which can be given by the expectation value of the operator ei. I did not write it here, but EIs are called effects. Okay, so this is POVM, these are effects. This is one way of introducing POVM. So you have a set of positive operators, they add up to identity, and the outcome, ith outcome gives you some state. We are not worried about the state, but the probability of that is pi, which is the expectation value of ei. There is another way, there's a little bit more detailed way of introducing POVM. Since EIs are positive operators, we can always write them as ki dagger ki. So instead of having EI, let us say we have ki. I'm giving you ki. And they are called measurement operators when you're talking about measurement. When you're talking about open system dynamics, then they are called Krauss operators. Okay, but here we'll stick with measurement operators. So KIs are called measurement operators. EI is effect, KI is measurement operator, and there's a relation between EI and KIs in this way. Now, till now we knew if you perform a POVM, the probability of getting ith outcome is pi. Now we know what is the state of the system after the measurement. After the measurement and you get ith outcome, this happens with probability pi, and the state collapses to rho I equals ki rho ki dagger upon pi. This is just normalization here. Okay, everything else is same. So this is more generalized way of introducing POVM. So now you can see that if POVM describe all the measurements, then projective measurements are also can also be explained with POVM. Projective measurements are special cases of POVM where EIs are nothing but just one-dimensional projectors with an additional constraint that they're orthonormal. Okay, if you choose that, then your POVMs, this POVM or this POVM, everything will become just projective measurement. The one we know from quantum mechanics, the von Neumann measurement. Okay, so now there's another more detailed way of explaining. Till now, we do not know what are the measurement operators, KI. They are just given some operators. Now we can go even further. How can we actually understand POVM in a more real or physical scenario? Okay, so a POVM can be realized by a joint unitary evolution of a quantum system, which we are interested in, and an ancilla, an assistant system, we can say. Okay, and followed by a measurement on the ancilla. So what we do is we have a state of the system. We have a system in some state rho s. We attach an ancilla in some initial state psi. We should know what is psi. We don't need to know what is rho s. Okay, now we make them interact and let them evolve. So U is a joint unitary on the ancilla and the system. Okay, so after some time, after some interaction, the state is this. Now we perform measurement only on the ancilla and nothing on the system. Okay, when we perform projective measurement on the ancilla, this thing will give us the ith outcome. And this whole thing can be shown to be equivalent to what we had earlier, that rho s goes to ki, rho s ki dagger without normalization, of course. And ki we can calculate from here will be I u psi. But u is acting on system and ancilla. I and psi are only acting on ancilla. So this becomes an operator. It means we have identity on the system. In that way, now you see everything was physical here. Ancilla was physical, interaction was physical, measurement was physical on the ancilla. And from there, we could find the measurement operator. From measurement operator, we can find the effects and we can perform the whole POVM. Okay, so in that way, a POVM can be related to unitary evolution and projective measurements. So it seems like projective measurements were special cases of POVMs, and POVMs are special cases of projective measurements. Somewhere we have to perform projective measurement, just that we are not performing this measurement on the system directly, but we are doing it on the assistant system or ancilla. Okay, so now you see we have unitary and we can get the cross measurement operators. Can we do the reverse? If I need for certain protocol, if I already have KIs, can we generate U from there? The answer is yes for that. Let us say we have a set of measurement operators KI, and the ancilla state is psi. Then let us assume for simplicity psi is 0. It does not. We can very easily change it to any state. Then the unitary matrix U will be of this form, where KIs, they are matrices, so operators, they will be on the first few columns of this matrix U. And what are AIs? They are irrelevant. As long as U is unitary, it does not matter what we choose for this. In that way, the choice of U for a given set of KIs is not unique, because AIs are matrices which are arbitrary matrices. As long as U is unitary, we will get the same dynamics of the system. Okay. So now our aim here, like in the paper, is in this talk, is to implement the POVMs on the optical systems. And we see that POVMs can be implemented if we can implement this kind of unitary on optical system, where optical system we mean by that is system and ancilla. So both of them should be there in the optical system and ancilla. If we can perform this unitary on system and ancilla in optical systems, then we can perform any POVM. Before going to that, let us see a small mathematical result, or like it's more physical than mathematical, but still in the beginning it looks like mathematical result. If you give me any unitary matrix, okay, I'm just saying special unitary, so determinant is 1, and let us say dimension of that is m plus n. Okay, I'm assuming m is smaller than n, but doesn't matter really. Then we can decompose this unitary matrix W in this form, where you have m by m unitaries, n by n unitaries, similarly here m by m unitary and n by n unitary, and a matrix in the middle which has a very special form. Here S to m is 2m dimensional, it's not m plus n dimensional, it's 2m dimensional matrix of consists of 4 matrices. Okay, where these 4 matrices are diagonal, cos and sine matrices. Because of this cos and sine, this decomposition is called CS decomposition, which stands for cosine sine decomposition. And this decomposition makes it possible to perform POVMs on optical systems. This is just identity. So only out of n dimension in this lower subspace, out of n, only m dimension has S, and rest n minus m has identity. Okay. So this decomposition we will use, CS decomposition, along with the relation between the measurement operators and the unitary, to implement POVMs using the POVMs on the optical systems. Okay. Here, one thing to notice is, or let me say, like this looks like one type of matrix, and this looks like other type of matrices. Okay. So in our optical implementation, it will turn out that if we will implement this POVMs on optical systems by assuming 1 degree of freedom of the optical system as system and other degree of freedom as ancilla. Okay, so typically we will, have I written it in the, yeah. So typically what we will do is we will have internal modes of light, such as polarization, orbital angular momentum, time bins, frequency bins, anything we can work with as the system, and we will use the path degree of freedom as ancilla. Okay, so in that way, these matrices LMs and LNRs, they will act on the internal degree of freedom, whatever internal degree of freedom we choose. Let us say polarization, so they will act only on polarization. This will act on polarization as well as on the path degree of freedom. Although these matrices are acting only on polarization, it's still not local operations. Okay, these are more like controlled operations. So in one path it is acting this operation is acting, in other path this operation is acting. That is like a control operation. So now we need to know how to implement this CS matrix and L and R matrices in our degree of freedom of interest. So in the path degree of freedom, balanced beam splitters and phase plates are enough to implement any arbitrary SU2 operation, and then we can generalize it to any SUN operation. Okay, so beam splitter matrix can be taken like this. It's a balanced beam splitter, and the phase plate will introduce a phase in one path and nothing in the other. So it can be written like this. And any arbitrary SU2 matrix W can be written as one phase plate, one beam splitter, other phase plate, other beam splitter, and phase plate. This is actually the Mach-Zehnder interferometer. So using Mach-Zehnder interferometer and three phase plates, we can realize an arbitrary SU2. And then Zeilinger in 1994, they have generalized this result to SUN, where you can implement any n-dimensional discrete unitary matrix. That is one problem solved. The second is how to implement the unitary operations on the internal modes. So if we consider polarization, then half-wave plates and quarter-wave plates are used to perform unitary operations on any state of polarization. In fact, so half-wave plate and quarter-wave plate, their matrices, if we rotate half-wave plate and quarter-wave plate with respect to the fast axis and by angle theta, then these are the complicated form of them. But more important is any SU2 operation can be realized by just using just one half-wave plate and two quarter-wave plates, and that's all. You just have to have different rotations of these, and you can realize any arbitrary SU2 operation on polarization using just these three plates. Okay, so this is more important. The technicalities are different, and this result was given by Professor Simon in 1989, if I'm not wrong. This is one degree of freedom. Other degree of freedom is like orbital angular momentum. We were saying no one knows really how to implement an arbitrary SUN transformation on it, but on certain restricted subspaces, you can implement certain unitary operations using something called Q plates, special light modulators, Dove prisms, polarization sensitive Dove prisms, and there are some more gadgets like J plates and all. So things can be worked out if we have a specific unitary matrix to implement on orbital angular momentum of light. Similarly, there are schemes to implement arbitrary SUN operations on the time winds of light, and I don't know if there is anything on frequency, but so this is how you can implement the unitary operations on the internal modes of light. Okay. Now, can we implement an operation on two different degrees of freedom simultaneously? Okay, so let us say I am given a four-dimensional unitary matrix W, where two dimensions are coming from two paths of the beam and two polarizations. So it's basically two qubit system. So if we have a four-dimensional unitary, we can use the CS decomposition. It will look like L matrices, R matrices, and an S matrix. Okay, and you can see these are L and R are 2 by 2 matrices, and S4 can be realized with balanced beam splitter and wave plates, not phase plates, but some special kind of wave plates. Okay, and the S4 is like again like diagonal T2, which is a diagonal cos theta 1 cos theta 2, S2, which is diagonal sin theta 1 sin theta 2, and so on. Okay, so with this we can realize the four-dimensional unitary on spatial and polarization modes. So if you want to see what gadgets we will need, so this L2 prime, R2 prime, R2, they are acting on specific paths only on polarization, so they can be realized with one half-wave plate and two quarter-wave plates. And this whole box here gives you the S4, where we are using two balanced beam splitters and two phase plates or wave plates, which will introduce theta 1 and theta 2 angle, the phase for different polarization. Okay, So these waveplates can be, the action of them is represented by d theta. It is C2 plus IS2. Then you can see this becomes exponential of I theta 1, exponential of I theta 2. So this one, sorry, this one is d theta and this is d theta dagger. We have to have opposite phases. So in this simple, with this simple setup, we can have we can implement SU4 transformation on 2 spatial modes and 2 polarization modes. Okay. We can generalize this thing. So if we have like NP number of internal modes and NS number of spatial modes, then what we can do is we take the first path and all the rest of the paths. We use the CS decomposition. It will look like L, L prime, R, R prime, and S. And you remember S had the matrix elements only for 2m dimensions. So it's 2np dimension here, and rest is identity. So nothing on the other spatial modes. Now you can see L is also a unitary. We can further decompose it using CS decomposition, and so on and so forth. We can keep on decomposing it. And eventually on both sides, when we do, we can always decompose it in this form, where the green boxes are the matrices acting on internal states or internal degree of freedom in each of the path. Okay, these lines are paths. And these orange boxes, they are the beam splitter setups I just showed you in this one. So of course, the values of thetas will depend on the matrix W, but for each of them can have different thetas, of course, but they will act only on 2 paths. So you will need only 2 balanced beam splitters and 2 waveplates. In this way, you can implement any arbitrary discrete unitary on internal and spatial degree of freedom. Okay. Now you'll see we have now a way to implement an arbitrary unitary, joint unitary between 2 different degrees of freedom. Now the thing is obvious how we can implement POVM. Okay. So how do we do that? Let us take a simple case of 2 outcome POVM on optical system. So let us say our system is polarization. I'm saying m dimension, but let us make it even simpler. Let us say our system is polarization, and we want to perform a POVM such that it is given by the measurement operator K0 and K1. So first step will be I will generate a unitary U, where first 2 columns are given by elements of K0 and K1, and other 2 are just arbitrary matrices A and B. Okay, let us not worry about them at the moment, what they are. Now we have an alternate way of writing W, that is in the CS decomposition. So we get L, M, L, L prime, R, R prime, and CS matrices. Okay. Now if we compare these two, this U and this U, if we compare, then you will see that K0 becomes L, C, R dagger, and K1 becomes L prime, S, R dagger. So from K0 and K1, these are the only quantities of interest, only operator of interest. And these can be described in terms of L, L prime, C, S, and R. R prime has no role to play. So we can choose R prime to be identity because we want to make the setup as simple as possible. Okay. So once we make R prime identity, then A and B choices are gone. Now we have like everything fixed. And our setup will look like this, where in the middle, we have the CS matrix, okay, the cosine sine matrix. So we have balanced beam splitter, we have wave plates, which will give us diagonal phases for the polarization. We have R prime is identity, so nothing here, L and L prime. So for given K0 and K1, we can find L prime because these are the singular value decomposition of K0 and K1, because L, R are the unitary matrices, C and S are positive matrices. We can always make them positive. So this becomes the singular value decomposition. So by finding the singular value decomposition of K0 and K1, we have L, L prime, R, and C and S, everything. So this becomes here, this becomes the unitary, the minimal unitary, let us call it, which is sufficient to get you the cross operators K0 and K1, right? So this will implement the unit tree. This is the initial state of the ancilla. And in this, the photon or light has some polarization state. That is the state of the system. Now, what we do, we have done only the unit tree. Now we have to perform the measurement. Measurement is just the intensity measurement in the two outcomes. Here, it will come with probability P0, and here it will be with P1. Okay. Once the state is here, the state here will be K0 rho K0 dagger. And state here will be K1 rho K1 dagger with without normalization. So we normalize it with the probability. In this way, with this simple setup, we can implement two outcome POVMs on optical system on polarization. Of course, polarization has no specific role to play. We can have any degree of freedom of m dimension, and this scheme will work as long as we know how to perform these operations on that degree of freedom. If we choose OAM, and if we know how to perform these unitary operators, we are okay. If we choose time bins, if we know how to implement these, we are okay. So this scheme is general in that sense. It does not depend on the dimension of the system. Okay. The extending it to n outcome POVM is straightforward again. So in n outcome POVM, you are given n measurement operators. You implement you make a unitary of this form where AIs are arbitrary. We again do not worry about that. And we, by using the CS decomposition, we can always write it like this. We can always represent it like this, and we can show that this part is it does not play any role in defining K0's Ks. So we can always take it identity. When we do that, then our Ks can be written in terms of L, R, Cs, and all those things. So we have R1, R2, R3, L1, L2, L3, L4, C, S, all those matrices. And by repeatedly solving, finding the singular value decomposition for Ks, it's not just singular value decomposition, it's slightly more complicated than that. But by doing that, we can calculate the L's and R's and C's, and we can design this setup, and we can perform the unitary U, which will give us the projector, the measurement operators Ki, and then we can just perform measurement at the end here, and we find that the probabilities. This is how we can perform the POVMs and outcome POVM on optical systems. Okay. So now, what are the applications of it? Like, why? Like, it looks like we are not really implementing POVM because we are using the internal degrees of freedom and two different degrees of freedom of the same system. So how can we work with it, or what are the applications? So we found a couple of applications of this way of performing POVM. One is local filtering. Local filtering is a special two outcome POVM. I'm just reading from the slides here. Local filtering is just a special two outcome POVM which can transform stochastically, of course, which can transform a state rho to a rho prime such that rho prime has a higher concentration of entanglement and well non-local correlations. Okay, so let us say we have this local filtering operation. So we have two qubit system. On the first qubit, let us say the Gauss operators we have, or measurement operators we have, are M1 and M2. And for simplicity, we can take M2 to be square root of 1 minus M1 dagger M1. Okay, then it will satisfy all those conditions, whatever we asked. On second qubit, we have N1 and N2. Okay, and let us say upon measurement, we got M1 click and N1 click. So the state rho prime can be written like this: M1 on the first qubit, N1 on the second, M1 on the first, N1 on the second, and divide by the probability of success. Interestingly, the concurrence of these two states, rho and rho prime, are related by this. C rho is the concurrence of rho, C rho prime is the concurrence of rho prime. It comes with a factor like this, which depends on the the determinant of the measurement operators and the probability of success. If somehow you can make this factor more than 1, then you can have entanglement in rho prime. You see, rho prime is not a general state. It is the state only in this outcome. Then if we can make this vector more than 1, then the entanglement in rho prime can be more than, or will be more than rho. Okay, and there is a way to find that particular POVM for which will give you, if possible, a state rho prime such that the entanglement is more than rho. Of course, so of course that cannot always happen. There are a class of states in which this improvement is not possible, but there are class of states for which this improvement is possible, and it's not very difficult to find. In fact, you need to find the measurement operators M1, M2, N1, N2 such that M1 and N1 takes your rho to a Bell diagonal state. If you can find such M1, N1 such that you go from rho to a Bell diagonal state, that is your optimum filtering. Okay, so there's a reference here. You can read about this interesting piece of work. It's not our work, it's a really old piece of work. How can we use this local filtering? So sometime, like when we are doing QKD, we have a system, we have a source which is producing an entangled pair of particles. We are sending them through the noisy channel, and by the time they reach Alice and Bob, they lose entanglement. Okay, so they are useless for QKD. Maybe once in a while we can put a filter in between this local filtering, and we can increase the entanglement such that the entanglement can become more than. So one thing here, one thing I should mention: if the entanglement in rho is 0, then entanglement in rho prime will always be 0. You cannot make from 0 to non-zero. You cannot go, right? So what happens sometime when we are sending it through noisy channel, that the entanglement stays, but the Bell violation is no more there. So it's not Bell non-local. So it is useless for QKD, because for QKD entanglement, Bell violation is more important than the entanglement. So once in a while, for certain scenarios, we can have filters specifically designed for this setup, which will give you with certain success probability a state which has more entanglement and hence or may violate the Bell inequality, and then those states will be usable for QKD purpose. So what we do is we take our setup for 2 outcome POVM. We design this filter such that it implements M1 and M2 measurement operator, N1 and N2 on the other side. If M1 clicks, we just let it pass, and then Alice and Bo perform measurement. If M1 and N1 clicks, if any other combination clicks, then we don't let it, we will just discard it. Okay, so in that way, we have shown in our paper that you can actually, in certain cases, increase the key rate and make some useless states useful. Okay, so in this way, our optical scheme can be important, because this we are sending single photons. Let us say they are entangled in the polarization degree of freedom, and then using our setup, you can actually perform POVM using their internal degree of freedom. Okay, like path degree of freedom or OM degree of freedom. You can implement these POVMs, and you are good to go, and you can improve the key rate here. Another application is coherent feedback control. I do not want to say much here because yesterday Professor Thomas Conrad gave an entire talk on this topic. So coherent feedback control is a protocol in which you take a system and you perform weak measurement on it and bring it to a target state with fidelity 1. Okay, and how it works is the mathematics is very interesting here. Let us say we have a quantum channel. I'm representing it with dollar, and the Krauss operators or measurement operators for this are ki. Okay, such that dollar acting on rho is given by this sum over I ki rho ki dagger. Okay, so if ki's are such that for some state t, ki acting on t is proportional to t, means t, or this state t, is an eigenstate, is somehow an eigenstate of ki, all the ki's, and ki dagger acting on t spans the Hilbert space. Okay, Then if you apply the same channel multiple times on row for sufficiently large number of times, then the state will collapse to the target state. Okay, so now you see we have measurement operators, okay, and we have a system, and we want to implement this on this this POVM kind of thing on our system. So we can use our scheme. So for example, if there are only 2 cross operators, then this 2 outcome POVM scheme is more than sufficient to realize this kind of coherent feedback control protocol. I'm sure this is quite straightforward if you just follow what we have done so far for 2 outcome POVM. The only difficulty comes when we have to repeat the measurement. If you have a ancilla as a separate system, then you can just have more and more number of ancillas, n number of ancillas, make it interact with the system, and then perform measurement on ancilla. But when you have only one ancilla, namely one specific internal degree or external degree of freedom of the photon, okay, and then you want to use it for POVM, then your resources in the experiment start increasing. Yeah, and it started increasing exponentially, the number of beam splitters you will need and other things. So for that, we have in this work we have given some ways of like reducing the resources. So that was that is also quite interesting, but that has already been discussed in Professor Conrad's talk. So I'll just skip all those things. Final application which I found interesting is related to preparing an arbitrary mixed state. For us theoreticians, it does not matter how we get a mixed state. Mixed state is just a density matrix written by a density matrix. But in experiments, it can be difficult to prepare a mixed state, a specific mixed state. Maybe you have like maximally, you have pure states which are easy to prepare, and maybe you have the maximally mixed state. Somehow you make your system entangle with something else, and you get a maximally mixed state. But if I ask you to give me an arbitrary mixed state, then what people do generally is they find some kind of decomposition, like spectral decomposition for the mixed state, and the spectral decomposition have the eigenstates with certain probabilities. So they prepare the system in those eigenstates, and then they take a mixture, not in the experiment in the lab, but on the paper they take the mixture, and then they find the result from there. So in the lab they generally work with pure states. Okay, maybe I'm wrong because I'm not an experimentalist, but this was my understanding whenever I saw how people prepare mixed states. So if you can prepare, if you can perform an arbitrary POVM, then you can prepare an arbitrary mixed state. For how does that work? For this, we will need 2 outcome POVM, okay, and the initial state as a maximally mixed state. So here also we will need mixed state, but here we need only one type of mixed state, that is maximally mixed state. And the Krauss operators for the measurement, we will choose K0 and K1. K0 is given by root of rho over lambda 0. Rho is the state we want to prepare, the mixed state we want to prepare, and lambda 0 is the largest eigenvalue of rho. Okay, so K1 automatically becomes 1 minus rho 0 over lambda 0. And now you see when we perform measurement, if the 0th outcome comes, it will be K0 rho r K0 dagger, and rho r is just identity, so it becomes rho. Okay, rho over m lambda naught. So this happens with probability 1 over m lambda naught, and the other one is just paste. So with a certain probability p0, we can prepare an arbitrary mixed state, whatever we desire. Okay, so in that way we can actually use this scheme quite elegantly and for many useful applications. I'm sure some of you will come up with more interesting applications of these optical POVMs. And with this, I will. There's something else also. No. With this, I will finish my talk. And these are the references on which the talk was based. And thank you.
Sandeep, for this wonderful talk. And we are now open for discussion and questions, comments. Yeah, yeah, please go ahead, Thomas. Oh, Thomas. I think you are muted.
Yes, I am. Thank you very much. Hi again. So I just wanted to mention this paper by Reck and others. So did you know that it's a different decomposition of unitary matrices, but the net result is that this POVMs is like unitary on system and then Scylla, so perhaps it's also somehow relevant.
Sorry, I could not understand the question. I think the audio
Oh,
quality
it's
is
not a
slightly.
question. Sorry, it's just something that came to my mind when I was listening to your talk. That there is this paper by Reck and others from in the 90s, I think 96 or 7, where they show how to decompose arbitrary unitary in a sequence by a particular sequence of beam splitters and phase shifters.
Yes, that is by Zeilinger and Reck and Zeilinger.
Yeah,
and
exactly. Yes.
Exactly,
That one.
1994. Yes.
Yes. So I just wanted to mention that because maybe.
So I also mentioned that, but I did not write that.
From time to time.
Yeah, I did not write that reference, but I mentioned that when I was discussing the beam splitter. I mentioned that this SU2 result was generalized to SUN.
Oh, okay. So sorry, I missed that one. Okay. No, it's okay. No, thanks.
Yeah, thanks for the comment.
Thanks.
Yes, here I mentioned that this is for only SU2, but this has been extended to SUN by Zeilinger in 1994.
What question? Yeah. Please go ahead.
Yeah. Hello, Sandeep. Yeah.
Hi, Thomas.
I wanted to ask the CS decomposition. Where does that come from? Did that also come from the Zeilinger paper or from somewhere else?
No, so we thought we developed it independently in 2015, but then we found some mathematical papers where they had already given it. I'm not sure people have used it for any practical application earlier, but it is like we have given reference in 2015 paper. I can send you the reference also. So people have done it in some maths work.
Okay. Can I ask you a question concerning your application to QKD?
Yes, please.
Yes. So, I mean, you mentioned that if you filter, you somehow can, provided that it works, that something comes through, that the photons come through, you can increase the entanglement, right?
Bell violation, more like.
Yes, but doesn't that mean entanglement between the two parties?
So it may not be the case. So we actually, in this work, when we did this local filtering work, we found a class of states, and like we can show that very easily, that they will have a non-zero entanglement, but no Bell violation. And there are some states which have less entanglement, but more violation than some other states. So it is possible that you go from the state which has non-zero entanglement but zero Bell violation to a state which has slightly less entanglement or same amount of entanglement but more Bell violation.
I see. And does that in total increase the average number of let's say bits that you can transport?
So for
from the QKD, you get some bits, you get some bit string. I understand.
Yes.
And the number of bits per photon that you kind of produce, is that increased, or because it only happens sometimes, or don't you
so
anything?
Let us take a case for which there was zero Bell violation in the beginning without filtering, and after filtering you have non-zero amount of Bell violation. In that case, surely we will have more key rate.
Okay, thanks.
Right. So we have produced those examples. So I'll send you the reference of this paper where you can see the references. You can see those states for which you see a clear improvement in the key rate.
Okay, thank you.
Thank you.
Any more question? Sudeep, I have a question.
Yes, Alok.
Yeah, Sudeep, you said that it's a two outcome POVMs you are considering, many outcome POVM you are considering. These are the one parameter family POVM or two parameter family?
So I could not hear your because of my
for
audio.
example, in a spin POVM, you have two kind of. For example, one is a biased POVM, another is an unbiased POVM. So, as you said that your things are completely from the. I mean, it seems that it is from the measurement because you are considering the ancillas, and then you are considering the ancillas and the projective measurements. Then you are getting the Krauss operators and the measures. Sorry, the effects. It's okay. So the thing is that in that case, you are getting the unbiased POVM. If you take a biased POVM, for example, there is two parameter family POVM. That may not be the, I'm not sure, that may not be the origin is not from the measurement, it's origin from the preparation. So in
Its origin from where?
Preparation, state preparation.
Okay.
So, I mean, whether you are considering this, I mean, it is for the general for any kind of POVM, for example, let's say one parameter family POVM and two parameter POVMs.
This is an interesting point. I never knew that there are such POVMs. I thought all the POVMs can be this normal dilation theorem it captures all the POVMs. I thought.
But from the because I have not understood the whole talk, definitely I'm not that much.
So but my
initially what you said, there that you are taking the simple trick, and then of course you are implementing the unitaries, and from the Krauss operator you can get back to the kind of unitaries, and you can get the you can implement it.
Right.
The question is here your E0 and E1 everything. It seems that it's a one parameter family POVM. It's not two parameters because kind of spin POVM to consider only the two qubit example. So
are you talking about the argument of this type, like Kij rho, Kij dagger, sum over j, sum over I, some such thing you are saying? So what we are like right now, for simplicity, I'm just showing those measurement operators which are purity preserving. Let us say.
Yes, but the way you implemented, you prepared your POVM. I mean, that's POVM you described. That compares you are defining the from going back to you are getting the unitaries, and then you can implement the unitaries from the setup.
Yes. No, but the thing is, if you take those unitaries which are those Krauss measurement operators which are not purity preserving, they also can be implemented with this setup. But we have to increase the number of path degree of freedom.
Okay. Okay. Maybe we can discuss later on.
Yeah. Sure.
Sure. Thank you. So is there any more questions? If not, so let's thank Sandeep once again for this wonderful talk.
Thanks, Alok and the organizers.
Yeah. So next speaker is Professor Sivasis Ghosh. Sivasida, are you here? Not yet. I think the time 7:05. It's already time. Sivasida, are you there? Anyone from the organizer?
I think he's not there yet. Okay.
Maybe I can give him a call.
Hello?
Hello?
Yeah, he will be joining in shortly.
Oh, you called?
Yes, sir. I called.
Okay.
No, no, ঠিক আছে.
Yeah, Sirajida, you joined, right?
Yes, I joined. Yeah. So
please share your screen.
Yeah, I'll just share
your
this.
PPT.
Yeah, see, this is Windows system, so I don't know whether it will work.
And so WebEx is new to us, I think.
Yeah. Yeah, the problem is it is just a minute, eh?
Yes, sure.
What do I show? I like to share Windows, right?
Although the PPT, just go to the start video. Maybe someone from the organizer can help. Yeah, it's coming.
Has it come?
You shared your whole computer, so whole screen. So,
oh, I see.
Yeah. Show us your PowerPoint.
It's not. So can you see this?
Yeah,
screen?
it's coming. Yes, coming. It will make it big, say full screen.
Yeah, that's what I'm
You
trying.
open it from the browser.
Open it from the browser. Is it now?
Save it. Could you please save it?
I have saved it, but it is
Yeah,
not.
but open it from the Adobe. I mean, it's possible.
No, this I am new to Windows. See, this is not working in Linux.
Okay.
But can you see this thing?
Yeah, I can see it, but it's a half of the screen, ma'am, I think. Right? Go down to the next slide. Let's see. Yeah, we are seeing the half of the. Yeah.
Is it okay?
Okay, I think.
Okay.
So.
Yeah, you can start. Sorry for the delay.
Yeah, no problem. Let me introduce you first. So, Professor Sivasis Ghosh is our next speaker, who is a professor at Institute of Mathematical Science, Chennai. And Professor Ghosh did his PhD on quantum foundations from ISI Kolkata. And his primary research areas includes the quantum foundations, quantum information theory, open quantum system, quantum thermodynamics, and a bit of quantum optics. And I recently had an opportunity to work, I should say that I had recently had an opportunity to work with him, and it's a real pleasure to discuss with him. I must also mention that he is an excellent teacher. Today, he will be talking about the information leak and incompatibility of physical context and improved approach. So I invite Professor Ghosh to start his lecture.
Thank you, Alok. And I would like to thank the organizers, Subhashish and Narayanan and all others, for giving me this opportunity to talk about this work, which is a work which I have done in collaboration with one of my PhD student, Arindam Mitra. By the way, can you see my cursor? Hello?
Yes, Subhashish, we can see. Go ahead. Yeah.
Okay. So my PhD student Arindam Mitra, a postdoc in our group, Gautam Sharma, and myself. So so this is basically it is an improvement of an earlier approach on information leak and incompatibility of physical context. So where we have made the improvement using most general kind of measurements, namely POVM, and also an useful measure of classical information content of a given quantum ensemble, namely Hollyhough bound. Okay, so this is what we have done. So let me try to motivate you. Basically the existence of incompatible measurements, like measurements which are not compatible. That means you cannot design an instrument by which you can measure these observables simultaneously, like position and momentum, or say sigma x, sigma y, like that. So this is a hallmark of quantum theory. I mean, you don't get to see in classical theory, but it is also known that two observables which are incompatible in quantum theory will remain incompatible in any non-signaling theory, which might be a generalization of quantum theory. So that is why, you know, this incompatibility of measurements is quite important, and you know, this has several applications like non-locality. When you get to see, we need to perform incompatible measurements. Steerability has direct connection with incompatibility of observables. And then quantum key distribution protocols, we know when we have the prepare and measure key distribution, then Alice performs kind of you know, preparation, and then Bob performs also measurement, but these are in some incompatible basis, incompatible observables. So mathematically, you know, there are several ways of quantifying this notion of incompatibility. Like what one can do if I have two observables A and B, even if they are POVMs, generalized measurements, what you can do, you can go to their Neumark extensions where they will become projection valued measurement and see whether they are compatible or not, because for projection valued measurements, compatibility testing is just to check the commutativity of the observables. But operationally or physically, it is not so easy to quantify this notion of incompatibility of observables. What one can do is to look at, let's say, the amount of deviation from repeatability, because if two observables are commuting, then measurement of one observable will give rise to an ensemble on which if I do the other measurement of other observable, the system will not change, the ensemble will not change. So what we can figure out is to quantify the amount of deviation from repeatability of measurement, to quantify this you know, the amount of incompatibility of observables. So that is one way of doing that. Okay. As I said, these measurements which are projective measurements on a state, they may provide basically non-trivial measurement statistics, provided this the state to begin with is not a maximally mixed state. Okay. So maximally mixed state is basically, you know, uniformity of these measurement statistics. When you perform measurement of any you know, any projective measurement, the statistics that you will get, by the way, if you take this to be rank 1 projective measurement, so the statistics you will get on a measurement of a projective measurement, rank 1 projective measurement on a maximally mixed state, it will be uniform distribution. So basically what one should look at is how much your measurement statistics will deviate from this uniform distribution. So thus this I of rho, you can think of it as a measure of information content of a state rho due to measurement, which is of course projective measurement of all possible observable A, B, C, etc. on the state, one after another, of course. And then thereby you can consider this measure log of D, where D is the dimension of the Hilbert space, minus you take the measurement statistics. That means AI is the ith projector, rank 1 projector, corresponding to the observable A, and you take the corresponding probability trace of IA rho, and then you calculate the Shannon entropy of that probability distribution. And if you take minimization of that Shannon entropy over all possible choice of observables, it will give you basically log of D minus the Farnham entropy of rho. So this is basically this log D minus S of rho is a measure of non-uniformity, you can think of. So non-selective measurement, that means if I don't look at the particular measurement outcome, then this will give rise to basically a channel action NA of rho. Okay, so NA of rho will be, in this particular case of projective measurement, it will be basically sum over I, AI rho AI. So NA of rho is that. And this will give rise to this I of NA of rho, this information content. And yeah, so that is what you will get. Okay. So when I perform two measurements, A and B, one after another, then the difference in the measurement content is, so first one is I of NA rho, minus second one is you apply NB, the corresponding channel for the measurement B on NA of rho. So this will give you basically difference in the information content. Okay. So for compatible observables, that means when A and B, they basically, whether if they are projective measurement, they will commute. Even if they are POVM, they will not commute, but they can be measured together. So for compatible observables, one can show that this I of NA of rho minus I of NB of NA of rho, this is which I call is I of rho comma A comma B, which must vanish. So think of A and B to be projective measurements. Measurement of A will give rise to an ensemble which will not change under the measurement of B, and therefore this difference in information content should vanish. So you may think of the QKD scenario where Alice performs, Alice prepares her qubit in the Z basis or X basis, and then sends the qubit to Bob, where Bob will perform measurement at random of sigma Z and sigma X, Z basis and X basis. And basically what they do is they will then announce the preparation basis and measurement basis, Alice and Bob, and from which they will select those runs where there is a matching between the preparation basis and measurement basis. And if there is any eavesdropping, that can be detected by looking at only those successful runs. Okay. So, so you see that, so we will come back to this QKD scenario in an example later. So basically the negativity of this information content, that means the difference in information, will tell you that there is some information leakage, okay, by some eavesdropper or in the environment, whatever may be the case. So this quantity will tell you, this I of rho A comma B will provide you the amount of information leakage in this scenario. Okay. So recently, this Martins et al., they introduced this notion of physical context. So the context is basically this tuple, rho is your initial state, from which Alice prepares the state based on the measurement of A, and then this system is sent to Bob. In between, if there is an eavesdropper who can perform measurement of B on that state, and then there will be some leakage of information. So the context means this tuple, and this I of C is this difference that I mentioned in the previous slide, that is called the incompatibility of physical context. So I will come back to that in details. So they considered basically these A and B to be projective measurements, and their information content, as I said, they have used something like a measure of non-uniformity. Okay. So what might happen is that if I general the measurement from projective measurement to POVM, then this measure of information content, this measure of this incompatibility, incompatibility of physical context, what I call as IC, that may become negative. So what does it mean? It means that Alice prepares her ensemble by performing measurement of observable A on rho, and then sends to Bob, and in between there is an eavesdropper who can perform measurement of B on that ensemble, and eavesdropper can get more information than what was actually there in the ensemble which was prepared by Alice, and that is physically impossible. Okay. So so this is why this notion of their measure of incompatibility of physical context is not very useful, in practical context. And so what we will do is we will generalize their notion. So we will take POVMs, and also we will take a more an effective measure of information content. So that is the and that is what we are going to do here. So let me give you the outline. So we'll have to mention some prerequisites briefly in order to describe about this notion of IPC, the general notion basically. And then in details, I'll talk about the limitations of Martin et al.'s work. And then I'll talk about a modified measure according to our approach of information leakage, and and then a modified version of this, basically the physical context, measure IPC, and relation between IPC and its modified version, and I'll show that why our approach is better suitable. And then I'll very briefly talk about the modification of IPC in the presence of memory, namely if there is an entanglement between Alice and another system. And that's it. So that is what I'm going to describe. So so briefly I'll tell you, because all of you know about these observables. So here I will use this A hat as an observable which is generic observable. That means a POVM. So A hat corresponds to collection of positive operators AX with outcome set omega A, and that will give rise to identity. So the set of all observables, I'll call it as this Kali O on the Hilbert. So my system Hilbert space is H. So when these are orthogonal to each other, pair is orthogonal, they are projectors, orthogonal projectors, then this will be basically a projective measurement. Otherwise, it's a POVM. And two observables, A and B, that means two POVMs in general, are compatible if you can find out another observable G on the same Hilbert space such that A of X can be obtained. So G will have this outcome set sigma A cross sigma B. Sigma is the outcome set of A, sigma B is the outcome set of B. Similarly, AX will be of these forms and BY will be of this form. So this is the standard definition of compatibility. And for projective measurement, compatibility means that these projectors AX and BY, they should all commute for X and Y. Okay. So a quantum channel is basically a CPTP map, and I can concatenate the quantum channel one after another. So for two channels, gamma and lambda, I can have such a relation. Gamma is less than or equal to lambda if one can find another channel theta such that you can obtain gamma by concatenation of lambda with theta. Okay, and gamma and lambda are concatenation equivalent if the relation is gamma less than or equal to lambda and lambda less than or equal to gamma, both hold good. And this box of lambda, it denotes the set of all concatenation equivalent channels to lambda. So we will use basically this idea, this concatenation equivalence, later. Now, the spin map, which takes every state. So S of H is the set of density matrices acting on H. So every state to a fixed state is called, so this is a pin map, which is a particular example of a depolarizing channel. Okay, and this is what we are going to use later. So once I have told you about the channel, let us tell you about the standard model of measurement. So basically a model of measurement means of an observable AX, which is in general POVM. What you can think of is a unitary interaction between your system and some ancilla system A, such that this bond rule will be satisfied. So rho times A of X, trace of that should be basically what you do, you perform measurement of an observable on the ancilla space, and that will give rise to the same probability. And this four tuple, ancilla Hilbert space, the fixed state of ancilla, this unitary interaction, and the ancilla observable, this is called a measurement model for measuring the observable A on my system. And post-measurement state, of course, it will depend upon the realization of measurement. It will be of this form, mx row, mx dagger, where mx is basically this, unitary up to, so basically ax to the power half up to some unitary v. So these are all known. And the average post-measurement state will be given by this channel action, lambda, which is basically this action. So you take trace over the ancilla system of unitary action of rho tensor sigma. So this is the measurement part, and then every measurement can be realized by some instrument. One POVM can have different instruments also for realizing it. So a quantum instrument, basically it's a collection of non-trace increasing CP maps phi x, okay, such that the particular outcome Ax of rho, the probability should be trace of phi x acting on rho, and the channel, measurement channel for non-selective measurement will be given by this phi x rho, sum over x will give you lambda of rho. And we call this I as an A compatible instrument. A is the observer. So one can show that if this instrument phi of x is A compatible, then the concatenation theta composition with phi x is also an A compatible instrument. So once you have one instrument, you have several other instruments, and which are A compatible. And I call this J of A as the set of all A compatible instruments. Sorry, I mean, for these mathematical details, but I will need it to some extent. Okay. So given this measurement model, as I said, HA is the ancilla Hilbert space, sigma is the fixed state of ancilla, U is the unitary measurement interaction, and A prime is the observable that you are measuring on the ancilla. So given such a measurement model, one can always associate an instrument which is A compatible, such that this condition holds good, this traceability condition holds good. On the other hand, given an instrument, okay, one can always find out a measurement model such that this traceability condition will be satisfied. So you see that the measurement model and the instrument idea, they are basically equivalent. So you can use any one of them as required. Now the concept of observable and channel compatibility. We have seen that if you perform a measurement, non-selective measurement, it will give rise to a channel. So basically, what we say is that a channel lambda is compatible with an observable A, and this is the notation, lambda and A. I don't know how to read this thing notation, but anyway, if there exists an instrument, basically, so lambda will be compatible with observable A if there exists an instrument I such that this traceability condition is satisfied, and the sum over phi x rho is equal to lambda rho whole. So both these conditions should hold good. And in that case, we call lambda as A compatible channel. If one of these conditions or both of these conditions are not satisfied, then we say that lambda is incompatible with the observable A. You can argue that a completely depolarizing channel, which I mentioned, a pin map, is compatible with any observable. So these are the two sets which we will consider later. So basically, for a given channel lambda, you consider the set of all observables which are compatible with the channel lambda, which I call tau c of lambda. And for given observable A, you consider the set of all channels. So this Q is the set of all channels for the system. So you consider the set of all channels which are compatible with the observable. So this particular set, sigma C of A, we will require later. So here is one theorem which is not our theorem. This is the theorem by Hainosari and Miedra. So basically it tells you that for any observable A with outcome set omega A related to this state space S of H and its Neumark extension. So V is the basically the isometry, K is the outcome, output Hilbert space from H to K, and A is the PVM, projective measurement. So basically it tells you that if you take this observable and then its Neumann extension, then the sigma C of A, the set that I said, which is basically the collection of all channels which are compatible with the observable. So you can show that sigma C of A is this set. So it is the collection of all channels lambda which are basically less than or equal to a particular channel lambda A, where this particular channel is nothing but the action of these projectors, this projective measurement after your isometry acts on this row. Okay? So this lambda A is a particular channel based on your Neumann extension, and this is called parent channel of the sigma CA, and corresponding A compatible instrument is called the parent instrument. As I said that for each channel there will be an instrument and vice versa. So this is the idea of parent channel and parent instrument. So you see that this parent channel, this lambda A, it depends upon the choice of your Neumann extension. As you know that Neumann extension is not unique, and therefore the parent channel will also be not unique. Okay, but of course two such parent channels will be always concatenation equivalent. So it is up to us to choose such a parent channel. Okay, so that was about the channel, and let's this Olivo bound, of course all of you know, this is basically the given an ensemble this px rho x, what is the classical information content that you can extract about this ensemble, that means about this x, and this information content, classical information content, is upper bounded by this Olivo quantity, which is S of rho. Rho is the average density matrix minus average of these entropies, von Neumann entropies, Px of S of rho x, and one knows from this Olivo-Schumacher-Westmoreland theorem that this Olivo bound is achievable asymptotically. And if you take this classical quantum state, basically you take this rho x, which is here, and paired with it some orthogonal states x with probability, same probability px, then this will give you for this state the mutual information, that means the information content that you get about C by performing measurement on Q, and that will turn out to be basically the Olivo bound corresponding to this ensemble. It is also known that under channel action, Olivo bound decreases. So Olivo bound of the original ensemble will be greater than or equal to Olivo bound of the output ensemble after the channel action. So this is what we will use later. Now let us come back to this incompatibility of physical context, which I just told briefly. So this tuple rho x and y, where x and y are projective measurement, basically these are observables. This is called a context, where rho is your system state, and x is basically, it consists of rank 1 projectors xi. Similarly, y consists of rank 1 projector yi, and d is the dimension of the Hilbert space. And this Martins et al., they have taken this non-uniformity measure that I told you earlier also, where d is the dimensions, log d minus s of rho. So one can think of the following game. It's like a QKD-like game. So Alice prepares the system in state rho, and then she performs the projective measurement x. And to transform the state rho into this, so if it is non-selective measurement, into this state sum over I xi rho xi, which is a channel action. And then this state is transmitted physically through some channel to Bob, who then verifies the information content, whether there is some leakage or not. So the transmission channel will be free from information leakage if there is no loss of information. So that is the idea. Okay. So if there is eavesdropping, let's say eavesdropper performs this PVM yi, on this state nx of rho, and this will get transformed into this state yi nx rho yi, and this is the information content as I mentioned earlier, I of nx rho and I of n yx rho. So the information leakage for this context, which I call as IC, is basically it should be I of nx rho minus I of n yx rho. Sorry for this. So this will be the entropy of Von-Neumann entropy of n of yx rho minus S of nx rho. So you see that the information leakage happens only if this IC is positive. Okay. Otherwise, there will be no information leakage. And it is important to note that in this particular case, when x and y are projectors, I mean these are POVMs, projective measurements, x and y, tilde x and tilde y. So you see that this information leakage will be 0 in only 2 cases. When x and y they commute, that means when they are compatible projective measurements, in which case nx of rho is equal to nyx of rho, and when rho is basically maximally mixed. In that case, both these information contents are 0. So only in these 2 cases, basically these information leakage will be 0. Otherwise, it will be positive. Okay. So you see that, well, I can't say positive or negative, but it will be 0 only when these 2 conditions, one of these 2 conditions are satisfied. So you see that IC is not 0. It means that Bob can detect some information leakage in principle. So let us see what will be the, so then the definition of context incompatibility basically is this resource encoded in this context C that allows one to test security of a quantum channel, communication channel, against information, and its amount basically IC is this quantity which I just mentioned earlier. So this was basically the work of this Martins et al. And let us describe about their limitations. What is the limitations? So limitation is, well, I can limit Alice to use projective measurements, but I cannot limit eavesdropper to use only projective measurement, because eavesdropper is not under control of neither Alice nor Bob. Okay, so therefore this is a restricted situation if we consider the measurements to be projective measurements only. Okay, so what we will do, we will change both this x tilde and y tilde as POVs. Okay, another restriction is this thing. So you see that this is something important. So if you take arbitrary instrument, okay, which I call as I prime A, corresponding to the observable A, which is a POVM. So take this arbitrary instrument. This is the collection of non-trace increasing CP maps. Okay, and this lambda prime is the channel. Basically, this is the action. And if chooses a particular instrument, namely this depolarizing map, and we know that for this depolarizing map, you will also have an instrument. Okay, so then you see that for such a situation, if I calculate the information content, it will turn out to be basically minus of S of lambda prime rho, and which is in general non-positive. Okay, so the post-measurement state of Eve has more information than that of Alice. Alice's post-measurement state, due to the measurement of A, has less information than the post-measurement state of Eve, which is an absurdity, as I told you earlier. Okay. So in this situation, you see that if I take POVM in the Martins et al.'s work, they are measured, it will give you absurd result. Okay. So one may think that this measure of non-uniformity that they have defined, log of d minus S of rho, it may not be an appropriate measure. So what I will do, we will replace that by this Olivo bound, which is, as I said, a tight upper bound on the accessible information about an ensemble. Right. So let us discuss about now the modified measure. Alok, how much time I have?
I mean, it's just you have 20 less than 20 minutes.
Less than 20 minutes.
Okay. Around 15 minutes. Yeah.
Around 15 minutes. Okay. 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 Good. So let us modify the game. The game was, Alice chooses a state row and then prepares the ensemble by performing measurement of an observable A, and then sends it to Bob. In between, there will be eavesdropper who can perform measurement of an observable B, and then there might be leakage in information. So let us modify that game. So Alice performs her measurement on the state row with this POVM A, and using an A compatible instrument, because to implement a POVM you need a measuring apparatus, namely an instrument, which I'll call at phi of A comma X, such that it will give rise to a channel. And let's assume for generality that the action of this channel can take your state from row S of H to S of K. It can be in general true. Okay, so this lambda prime A is the channel action corresponding to this instrument. And it will generate this ensemble EX rho X in the state space, and for this average state. Okay, and you see what is the probability of PX? Basically the trace of this instrument action, and the post measurement state is basically this phi of AX rho divided by trace of it. So that is the game. And what is the information content in this ensemble epsilon A or EA, which Alice has prepared by her measurement choice? So this is the Hollywood bound. So chi of rho IA prime is the Von-Neumann entropy of the output state lambda prime rho minus the average Von-Neumann entropy. So this is the information content in the ensemble EA. And similarly, now Alice sends that system to Bob. In between, eavesdropper gets hold of that system and performs measurement on the state lambda prime A, okay, with this POVM B using a B compatible instrument, okay, such that it gives rise to this channel lambda prime B and the corresponding ensemble E of B. So now the information content in E of B will be basically this Hollywood bound. So this is the average state, S of average state minus average of lambda prime of rho X. Okay, so that is what you will get. So the modified information leakage, as you can think of, is just the difference of these Hollywood bounds. So this is the initial Hollywood bound minus this is the final Hollywood bound, and you can argue yourself that this will be the form of the modified information leakage. So the C underscore C corresponds to the context. This H corresponds to Hollywood bound. So basically the information content we are taking is Hollywood bound, and this is rho is your initial state. This is the instrument I prime A, and this is the instrument I prime B, compatible with A and B respectively. And as you know that Hollywood bound does not increase under channel action, therefore, because this ensemble you have obtained EX lambda prime B rho X, you have obtained by action of lambda prime on lambda prime A of rho. So as Hollywood bound does not increase under channel action, therefore this information leakage quantity is always non-negative. So this is our modified information leakage, and this is always non-negative. Okay. So now the question is, how can one minimize this information leakage, this ICH that I mentioned earlier? So there are two ways one can minimize. One is that eavesdropper can choose a measurement which will basically gives rise to minimal change in the information leakage. Basically, it will give rise to minimal information leakage. And secondly, Alice can choose a measurement which will give rise to the maximum Hollywood quantity for hard measurement. So this is basically the two things that one may look at. So let this lambda be the parent channel, as I mentioned earlier, of sigma c of b. So this is the basically collection of all channels which are compatible with the observable b, and sigma be the parent channel. That means it is greater than or equal to all the channels in this set which are compatible with b. And let I be with the corresponding b compatible instrument. That means it can basically give rise to this channel. Then for any other channel, okay, which is parent or not, which I call lambda prime b within this sigma cb, we know that lambda prime b is less than or equal to lambda b. That means you can obtain lambda prime b by concatenation of lambda b with theta. Now, because of this, you know, the Hollywood bound that we have obtained for this, b compatible instrument, I prime a can be anything, I b. So this should be the maximum over all the Hollywood bound that you can obtain for arbitrary instrument I prime b, corresponding to channel lambda prime b in sigma cp, because the Hollywood bound does not increase under channel action. So you see that for any instrument of Alice, let's say I prime a, the minimum leakage in the information due to measurement of Eve of this observable b is basically this quantity. So this is the minimum leakage for any choice of instrument of Alice, but this particular choice of instrument by eavesdropper, which is basically corresponding to the parent channel lambda b. And we call this as IC of rho I prime a IB. Okay. You can also call it as this IC of H corresponding to Hollywood quantity, I prime of A, and B is the observable. Okay. So note that here this B, it depends upon the output space Sk, and it can be corresponding to this channel, and it can be of any dimension. So basically B can be arbitrary. So over all such arbitrary choice of this thing, this Eve's measurement, this is the minimum of the information leakage. Okay. Now let's talk about maximizing the Hollywood quantity by Alice. So Alice's aim, as I said, will be to maximize the accessible information in our post-measurement ensemble, in order that Bob can get maximum amount of it, best amount of this information. Okay. So what Alice will have to do for that is to choose again an A compatible instrument, IA, for which this Hollywood quantity is maximum. Okay. And let's say this gamma A be the parent channel in sigma Ca. As I said, this will use time and again. So this is the set of all channels which are compatible with A, observable A. And you can show by the similar argument that the Hollywood quantity for any other instrument I prime of A, it is less than or equal to Hollywood quantity for the instrument I. So therefore, in this case, the information leakage will be basically this quantity, this IH rho for the observable A and observable. And this is the appropriate amount of information leakage for the parent instrument. So this is what we should concentrate, we should consider as the appropriate measure for information leakage, this quantity. Okay. So let's look at this modified version of the incompatibility measure. So let us take for simplicity that the output Hilbert space for Alice's measurement K, this is equal to the input Hilbert space H. And let's say that this context incompatibility, basically it's a resource in this context C, rho A and B, which allows one to test security of the transmission channel from Alice to Bob against information leakage. And this resource is quantified by this quantity J of C. C is this context, and which is, as I mentioned, is this quantity. And why I have chosen here I of B, see, basically but why I have chosen IA max? So IA max, this quantity is the A compatible instrument that maximizes this Hollywood quantity. And again, IB is the B compatible instrument. So we basically, we are using this instrument compatible with the observable everywhere. So, if eavesdropper uses any other instrument, I prime B, the information leakage will be greater than or equal to this J of C. So we will consider this quantity as my information leakage in this context. Okay. So basically, if I take this A observable to be a projective measurement, then this channel for the non-selective measurement will be a parent channel in this sigma C of it. Okay. So what will be the modified context of compatibility or incompatibility? So this is my context. Rho is the state. A and B are POVM. So B is a POVM because eavesdropper can have any measurement, and A is a projective measurement, which I consider. And then this JC is this quantity. So the difference in the Hollywood quantities, and that will turn out to be of this form. So this is the modified measure of context of incompatibility. Incompatibility of physical context. This is the modified version of IPC. So let us look at this relation between this modified version of IPC with the original version of Martin's et al. So what you can do is you choose this context, okay, and you have these according to Martin's et al. So here this A and B both are projective measurements, rank 1 projective measurements. So as we have mentioned, this I of C, the information leakage according to Martin's et al. Is I of NA of rho minus I of NBA of rho, and which is nothing but the Feynman entropy of the final output state minus Feynman entropy of Alice's output state. So even for the same context, if I consider the JC, the modified IPC, this will be, as I said, is Feynman entropy of the Alice's output state minus Feynman entropy of the final output state plus average of Feynman entropy of the final output state minus average of Feynman entropy of Alice's output state. So where this IA and IB, as I said, these are parent instruments. So one can show with little bit calculation that J of C, that means this modified measure of this IPC is related to the original IPC by this relation. Okay, right? So this is important for us. So you see that J of C will be 0 when these projective measurements they commute. So A and B as an observable they commute, as observables they commute. They will be 0 because measurement of A will create an ensemble which will not change under the measurement of B. Okay. So both I of C and J of C they vanish when they are these A and B are commuting observables. But when this rho is maximally mixed state, we know that IC is 0 for maximally mixed state. But JC is not necessarily 0 because of this term. Because this term NB of rho y, S of NB of rho y is not necessarily 0 because NB of rho y can be a mixed state. So this tells you that only in the case where the observables are compatible in the PVM case, then only this information content is 0. Otherwise, it is not 0. In fact, as I told you, this J of C is always non-negative in the general scenario. So let us take this example. So let us take the system Hilbert space to be 2-dimensional, and let us take the initial state to be maximally mixed state. And now let's assume that Alice chooses a projective measurement, one of the two projective measurements, is measurement of sigma z or sigma x at random with equal probabilities. Then she will generate these two ensembles, with half probability this projection on 0, which is the eigenstate plus 1 eigenstate of sigma z, and half probability projection on 1, or half probability plus, this is the plus 1 eigenstate of sigma x, and half probability of minus. So these are the two ensembles that Alice will generate because of choice of random choice of sigma, measurement of sigma z and sigma x. So the average information content, according to the Martins et al. Work, will be basically this. Why 1/4? Because Alice can prepare this ensemble in sigma z basis, and Bob and eavesdropper can also measure in sigma z basis. And Alice can prepare in sigma z basis, Bob can measure in sigma, eavesdropper can measure in sigma x basis, so on and so forth. So these are the 4 terms, and you can show that this is 0. Whereas this JC average, the modified version of IPC, you can show that this is basically half, which is not 0. So one can detect information leakage using this modified measure, which is not possible using the measure of Martins et al. So let me briefly describe, very briefly, about this memory effect. So basically, what we have considered so far is Alice has a system on which she is performing measurement, and that system is transmitted to Bob. Let's now assume that Alice has some kind of correlation, maybe entanglement, with some memory system which we call as M. So in that case, how will this IPC change in the presence of that memory? So why this question is important? Historically, it was this work of Mario Beta et al. Who showed that in the presence of memory, the total uncertainty of 2 measurements, they get reduced. So the question is, with the help of memory, whether IPC can get reduced. That is the question. So how will you deal with this memory? So let's say that Alice has a state rho in AM. A is Alice's system, M is the memory system. This is the initial state. And on this initial state, Alice performs measurement of some observable with outcome X. So this will give the post-measurement average state, Px rho in AMX. And for this rho AMX, what is the information content? According to this, this Martins et al. So what you do is, you'll have to take the conditional, phenomenon entropy. So log of D, D is the Hilbert space of Alice's system, minus entropy of A given M, and that is basically this quantity, log D minus S of rho M plus S of AM plus S of rho M. So, so this is the quantity that Alice can measure after preparing this answer. Okay. And then she sends this system A to Bob, because memory is not in her hand. Okay. So then Eve can perform measurement of some observable B, and then rho AM will change into this state because of the action of this channel in B for the observer. So that is called rho, let's call it at rho A prime M. And again, the information content due to this memory will be, as I mentioned earlier, log D minus S of A prime given. And what is the information leakage? Information leakage, basically you take the difference of I memory rho AM minus I memory rho prime AM. If you take that, it will be this one, S of rho A prime M minus S of rho AM. That is the information leakage. Now, let's look at whether it has been reduced or not because of the presence of memory. So, IC is the information content without memory. That means on rho A, if I consider, and ICM is the information leakage in the presence of memory. So if you take this difference, it will turn out to be basically the difference in the coherent information. Sorry, it should be less than or equal to 0. So what is this coherent information? So this I coherent M greater than A is nothing but S of rho A minus S of rho AM. This is the coherent information as we get to see in the quantum information carried out by a quantum channel. So this is the difference in coherent information, and this is less than equal to 0 because under the channel action, coherent information gets reduced. Under the channel action, we have got this rho prime n, so therefore this will be less than equal to 0. In a similar manner, if you argue, you can show that the difference in the modified version of IPC, JC, minus modified version of IPC in the presence of memory, it will be just opposite to this quantity. And this is, of course, greater than equal to 0 because, under channel action, coherent information does not increase. So you see that, again, there is a drawback in the measure or in the treatment of this Martins et al. Whenever we have memory, and this is actually according to Mario Betta, that under the action of memory, your information content, it should decrease, it should not increase. Just like in the case of uncertainty relation. So, so you see that without memory, there is some drawback in the work of this Martins et al. In the presence of memory, also there is drawback. So which basically our approach address. So that's it. That is the conclusion. So conclusion is that we have basically improved this measure of physical context is from the work of IPs, this Martins et al. By introducing the POVMs and by incorporating the Holevo bound, namely bound, tight bound on the accessible information about an ensemble. Okay, so thank you for your attention.
For this beautiful talk. So, you take your questions. Any question? Comment?
Yeah, maybe this is very mathematical and this was the last talk, so yeah.
Sivashish, may I ask a question? Sorry.
Yes, sure.
Yeah, thank you for the nice talk. I would like to understand what it means that Alice has to find the maximum instrument, the instrument that maximizes the Holevo quantity. What does she has to do? Does she have to do a projection measurement of a non-degenerate observer, or how does that work?
No, the thing is, Alice will have to perform a measurement in such a way. So Alice's state is this rho, initial state, on which she performs a measurement. Okay, and that will create some ensemble. So for that ensemble, what is the maximum classical information content? That is the Holevo bound.
Yes, and is that not if the, I'm not sure, but what is the, when is it maximal? What measurement does she have to do?
Oh, what measurement does she have to do? Okay, so
yeah.
Okay, so it depends. It depends upon. So once you have this ensemble, which I have been, so let's take this ensemble Px rho x. Okay, P is the probability, rho x is the state. Now, what measurement one can perform to extract the maximum classical information on that? Okay, so that we don't know whether this will be a projective measurement or a POVM, because we'll have to perform measurement. We'll have to maximize over all possible measurements.
Yeah, but isn't it if you perform a measurement that leaves the system in a pure state, given a certain measurement result, then the von Neumann entropy of that is 0. Okay, so basically you get the second term, this minus term is 0, so you have the just the von Neumann entropy of the initial.
Yeah, that is
of
true.
the initial.
But
Yeah.
how would you know that S of rho, which is the average state, will be maximum in that case? You know, this average state will change also by the choice of your measurement, right?
Okay. Okay.
So
yeah,
yes,
but that could also be no. I think that's also maximum. I mean, okay. I don't know. It was a question, right? So,
yeah.
What measurement does she have to do in order to you know, to maximize the Holevo quantity? And then you say if she has done this, then we can detect the eavesdropper best. Is that not your argument?
Yes. So the thing is that if Alice performs the best measurement to maximize the Holevo quantity, and if eavesdropper, well, on eavesdropper we don't have any control, but the idea is eavesdropper should perform such a measurement which will give rise to minimum information leakage. Okay, so eavesdropper will choose that kind of measurement which will give rise to the second Holevo quantity to be minimum. I mean, the ensemble produced by Alice on which eavesdropper perform measurement. So this measurement will give rise to a Holevo quantity which is minimum. That is what eavesdropper will do. I mean, if I assume that the eavesdropper is rational.
Yeah, but can I ask, I mean, the eavesdropper also, I mean, it doesn't help the eavesdropper if he doesn't do anything, because then, of course, he also,
yes, of course.
You know, so he has to also pull some information out of it.
Yes.
But in order to do both, it would be, of course, ideal if his instrument would commute with the instrument of, or if his observable would commute with the observable of.
Exactly, exactly. But
he doesn't know that observable.
Doesn't know what
yeah.
it is. Yes, yes. And regarding your first question, you know, I told you that this, if you take a classical quantum state, the sum over x, px, then projection on x, tensor product rho x, then that will give you to this Holevo quantity, right? The mutual information,
Yeah.
in that state, classical quantum state, will be the Holevo quantity for the ensemble, right? So in that sense, actually, you are right that you will have to perform a projective measurement, rank 1 projective measurement.
Okay. Yeah. Okay. So how does this help me now? So what you are doing, how can I now use this in order to detect eavesdropper better? So I know now what Alice has to do, and then what do? I have to measure this quantity JC, or
yes. So the ensemble that, of course, you know, we don't have any control over that eavesdropper. So once the you know, state is received by Bob, so Bob will have to check, as we do in QKD, that you know, whether the state has been changed after Alice's measurement or not. So what we have given here is basically a measure of you know, information leakage. How eavesdropper will be detected, that we are not we have not given any you know, prescription for that.
Okay. Thanks.
Yeah, Shivashishta, I had I think slightly silly question, but do you think the kind of approach that you're taking, this can in some sense also connect to error correction or something? So supposing if there is like preferable set of measurements or something that could,
like
in sense, allow, like, if you think about information leakage or loss to not happen in some system. I don't know. It's just something just.
Maybe you are right. Yeah, one may see that one may do that. You know, in error correction, basically, you know, what we do is we have to detect error first and then correct it. So for Now, this part, as I said, we have not given any prescription how to detect eavesdropper. What we have given is how to measure the information leakage.
Yeah, Shiva.
Hello.
Yeah, I have a related question. What Himat is asking.
Yeah.
I have slightly related similar question. Say, for example, from this information leakage, can we infer is it because of some Eve doing measurement, or is it because environmental decoherence?
So at this stage, I cannot say anything about that because, yeah, so it can be due to environmental decoherence, it can be due to eavesdropping, yeah, because we have not given any prescription for detecting the eavesdropper. Yeah. So for us, basically, it is inert to the presence of environmental noise or eavesdropping.
And as a slightly related question, can one think about thermodynamics, like maximization of entropy, being minimization of the Hollywood information?
Well, there are some relations of derivation of, there is a derivation of Hollywood quantity from thermodynamic principle, namely second law. People have done that. So yeah, so this relation is there.
Okay. Thanks. Very nice talk.
Thank you.
Any question? Any more? If not, so let us thank Professor Ghosh once again for this nice talk. And also, we'd like to thank the other two speakers of this session. Thank you very much. So I can hand over the charge to the organizers. Is there anyone?
Hello. Yes, sir.
Okay.
Thank you. Thank you so much, Professor Paul, for chairing this session, and thank you all the speakers of the session for such nice. So I request everyone to be there and turn on their cameras for 2 minutes. We actually want to take some screenshots for this conference, photographs actually. Yeah. So.
Hi, Chandru.
Oh, Chandru, how are you?
Was secretly
put on the light. Nice to see the familiar faces. Hi, Thomas, how are you?
Oh, sorry, I was muted. The moment we see all our colleagues, our face glow. It
Yes,
gives
yes,
us,
yes.
Santa.
Hi.
Oh, Thomas. Okay.
Trish. Thank you. Thank you very much.
At least Quest has done one good thing. It has united many of us together. Thomas, we have this project from SCRB, our Department of Science and Technology, called Quantum Enabled Science and Technology Project. Most of us are part of that. So we are getting to see each other more frequently, largely because of that.
So Banerjee, Subhashish. So when is our grand dinner, conference dinner?
Yeah. Since you people are not here physically, I think in your name I will go and have it with the student volunteers. It is due you actually.
Shubhashishta, you can order it on Zomato.
Yeah, I think that is.
Everyone can have it.
How do I send it to Thomas, for example? Zomato. So, functional South Africa, so I know what it is, but I don't know. Yeah, but convey my thanks to all of you. So it has been really nice, but it's not just my effort. I think all of you have made it possible to come together and share your thoughts together. And I'm really happy, and I would be much more happier to host you people sometimes physically. I hope to see you all soon.
Same here.
So I'm told that I have to put my camera on. So yeah, so I certainly hope that we get to see each other physically sometimes. So this is not.
So maybe we can all unmute and just give a hand to the organizers for doing it.
Thank you.
Just
Thank
unmute yourself.
Yeah.
Thank you, Shubhashita and your team. Yeah.
Thank you.
It was a pleasure. Okay. Bye.
Bye bye.
So see you all. Let's hope things will get better and we'll get to see each other soon.
Yeah.
Bye.
Okay, bye.
Okay, bye.
Bye, everyone.
Everyone just stay for a minute. Narayan sir will join us shortly and we'll get a photo and
Just wait for a minute. Just wait.
So you're not taking the photo?
I didn't shave also. They didn't tell me. They're taking a photo. Oh, yeah. You should clap for him. He and this guy here they have been the real backbone of this conference. This is Thomas, you see, and this person here, Roy. Roy, show yourself. Raise your hand. These two boys have been the people who have really handled this and made it possible.
Yeah, thank you. Thank you so much, the two of you.
Thank you.
So is it done or?
Okay, thank you.
Okay.
Is it done? The photo is taken now?
Yeah, that's it.
Bye, Sandeep. Bye, Narayan.
Okay. Yeah.
Okay, these two guys. Okay then. Bye.
Bye.
Bye. Good night, everyone.
Sorry,
Good night.
Sandeep, I missed
From
your
South
talk.
Africa.
Okay, it was recorded. I think you can attend it even now.
Oh, sure. Okay.
Can we see the talk?